As you start overloading constructors, you often notice that the code used to initialize objects in these constructors is very similar. Many times, only the initialization values of the data members is what changes. One common source of program errors is duplicated code, so we want to minimize the amount of duplicated code in our programs. C++ allows us to use delegating constructors. The idea is that we can now call another constructor of the same class in the initialization list of a constructor. The syntax is really simple. After the parameter list, we write a colon, and then we follow it with the call to the constructor we wish to call. Let's see an example with the player class. Here's the declaration of the player class as we've used previously. We've got the 3 overloaded constructors. And here's the code for the overloaded constructors using initialization lists. Notice how similar the initialization lists are. In this example, the only differences are the values used for initialization. Rather than write these initializer lists over and over in our code, we can simply delegate initialization to another constructor. Let me show you how. In this example, the first constructor is the 3-argument constructor, and we use a constructor initialization list as we did previously. But when we define the noargs constructor, instead of writing another very similar initialization list, we simply call the 3args constructor with the initialization data we need. We call the constructor by providing the constructor name, which is the same name as the class, followed by the arguments to the constructor. In this case, the noargs constructor is the delegating constructor, since it delegates object initialization to another constructor. In the last example, we do the same thing, but we delegate to the 3arg constructor and provide name val, 0, and 0 as arguments. It's important to note that this only works in the initialization list. You can't call the other constructors from the body in the delegating constructors. Also, you can't delegate to another constructor and provide initialization values to class members. Let's update the player class in the IDE to support delegating constructors now. Okay, so we're back in the IDE, and I'm in section 13 workspace in the delegating constructors project. So what we've got here is the player class again, and we've got our same 3 overloaded constructors, and what we've got down here from line 21 all the way down to line 32 are our implemented constructors usually using constructor initialization lists. As you can see, a lot of this is very duplicated. So what we're going to do is we're going to refactor this so that instead of using constructor initialization lists, we're going to use delegating constructors. Now, what we want to do is we want to delegate everything in this example to this 3args constructor. So what can we do? Well, what we can do is we can replace that initializer list with a delegation. So we can simply say player, and we'll say none, and 0, 0. Okay. So let me delete the rest of this. And that's basically it. So what's going to happen here is, let me replace that parenthesis with a curly. So what's going to happen here is we're going to call the constructor from this constructor. That's the whole idea with delegating constructors. This noargs constructor is the delegating constructor now. So what we're going to do is we're going to call the player constructor that has those 3 arguments, which is this guy right here, the one with the initialization list. So this guy is really going to do all the work for all of these constructors. We're simply just going to delegate the work to it. We'll do the same thing here. We'll call player, and we'll pass in name val and 0, 0 again. And I'll delete the rest of this, and I think I put a parenthesis again. So I'll replace that with a curly here. And there we go. So in this case, we're calling the same idea. We're calling this 3arg constructor from here. Now, let's put some output statements in here just to see exactly how this works in the chaining that takes place. So what I'm going to do in the body of this constructor here, I'm simply going to say cout, and I'm going to say no args constructor. That's this one. And we'll have an end line. And then what I'm going to do is I'm just going to copy and paste that one line of code into each one of these constructor bodies here. And in this case, this is the 1arg constructor, which just expects the 1 string. And this guy here expects all three. So I'll just write 3 arg. And that's 1 arg. Okay, so that's it. Now we've got our constructors implemented. We're using delegation here in this context. And we'll just run our main now. And the idea here is the same. We're going to create the same objects as we did before. We've got an empty, which is a player object. And that's going to use the no args constructor, right? Because I'm not supplying any information. So it's going to come up here. And then rather than initialize it here, we're just simply going to delegate the construction of this object to the constructor that expects 3 args, this guy. Okay, so that's what we're going to do. And what we'll do is we'll put breaks on all of these constructors so we can see when they're being called. And we'll also put a break right there. And let's step through this. And let's see, we've got an error. I'm missing a terminating character. Okay, I probably have that all set now. Let's try that again. Okay, so let me put the output window over here so we can see it. And we'll walk through this. And remember, when we're in the constructors, we're going to use the this keyword, which is really a pointer to the object that I'm creating. And like I said, I'll talk about that a little bit later in the course. So we're right here on line 38. We want to create that empty object right here. So it's going to call this no args constructor. So let's step through it. You can see I'm right here now. Now what we expect is, we don't expect this one line of code to execute in the body. What we expect is to be thrown down here, right? Because that's what I'm doing. I'm delegating. So I'm going to, there we go. Now we're at line 32. This initializer list is going to execute and initialize my object. That's done. If I look at this, you'll be able to see none 0, 0, which is exactly what I expected. Now I execute the body of this constructor. So this is going to say 3 args constructor. And I spelled constructor wrong, but that's okay. I'll fix it when I save the files. So 3 args constructor just executed. Now I'm not done. I need to come back to the constructor that called it. And I'm going to execute this body right here, no args constructor. So let's do that. See, we're back now to line 23. And we execute that one line. So you can see here that the no args constructor called the 3 args constructor, which is exactly what we expected. Okay, so now let's do this one right here. I'm creating the frank object, and I'm calling that 1 arg constructor, this one right here that expects a string. So let's step through it. There I am. I'm at the initializer. I'm delegating to the same one here, the player constructor that has the 3 arguments. It's initialized. Now I'm going to print out 3 args constructor again. Now when I come back here, I still need to execute the body of this constructor, which I do here. So in this case, the top case, the no args constructor called the 3 args constructor. In this case right now, the 1 arg constructor called the 3 args constructor. Okay. Now we'll basically do this last one right here, the villain. And for this one, we're just doing this guy directly. We're just running this constructor right here. It's going to initialize those 3 values and simply print out 3 args constructor. And there's the output, and we're done. Okay, so that's an example of delegating constructors. It's pretty straightforward. Many times you'll have an example that's really, really simple like this. And this example will simplify even further in the next video, where we'll use default parameters. But you can always find a way to use these delegating constructors, and they're very, very handy to use. And the nice thing about this is, whatever my initializer is here, and if I've got to run some code, remember that if this guy delegates to this guy, both those bodies are going to be executed. When we learned about C++ functions, we learned that we can supply default values as parameters to functions. The same applies to class methods and class constructors. In many cases, we can reduce the number of overloaded constructors by providing default constructor parameters. The same rules that we learned when working with default function parameters apply to constructors. Let's continue working with our player class. We can actually just have one constructor that does everything that we did with the 3 constructors previously. You can't always have default parameters in class design, but many times you can. Here's an example where it makes perfect sense. Notice that the player class now has only a single constructor, and that constructor has 3 arguments: the name, health, and XP of the player. But in this example, we're providing default parameter values for all the parameters. For the player's name, the default is the string none, and for health and XP, the defaults are 0. These default parameters are declared in the constructor declaration in the class as shown. Now, when we implement the constructor, we can implement it exactly as we implemented the 3-argument constructor in the previous videos. Here you can see the implementation for the single constructor. Notice that you don't supply the default parameters here. We can simply use an initializer list to initialize the class attributes, and the compiler will take care of providing the default values as needed. This is very handy and results in less code to write, which means less code to test, which means less code that could have errors. Since this single constructor is doing the job of several constructors, we have to be careful not to declare ambiguous constructors. For example, what would happen if we implemented a no-args constructor, in addition to the one we see on this slide? Well, we'd get a compiler error because the compiler wouldn't know which one to call. In this example, we're creating empty, frank, and villain objects as we did before. But take a look at hero. We didn't have a 2-args constructor in the previous version of the player class, but we do in this version. That's pretty cool. Now let's modify our existing player class in the IDE so you can see how this works. Hi, so I'm in the IDE and I'm in the section 13 workspace in the default constructor parameters project. And what we've got is the player class as we defined it in the last few videos, where we've got our 3 constructors, and here we're using delegating constructors, and down here we're using an initializer, a constructor initializer list right here on line 32. What I want to do is I want to simplify this. I want to get rid of some of these overloaded constructors and use default parameters instead, as we did with the slides. So what I want to do is just get rid of all these constructors right here. I just want to end up with one single constructor, and there it is, player with 3 arguments. And what I'd like to do is supply some default parameter values for these. Now, you can't always do this when you're doing class design, but sometimes you can, and when you can, you should, because it really simplifies your code. So in this case, I'm going to default the name of the player to none. I'm going to default the health value to 0. I'm going to default the XP value to 0. Okay, so that's what we've got now. There's my 3 default parameters. Now these 2 constructors go away, so I'm just going to get rid of them right here. And this constructor, which is our 3-arg constructor that matches the signature for this one, we really don't have to do anything to it. These default parameters will automatically be supplied by the compiler when we need them. Okay, so now what we've got is same code we had before. Now I'll put a breakpoint here. It's just the only constructor being called, so we'll definitely see it being called. And I'm going to create an empty object here. So again, it's a player object, and I'm not supplying any initialization information here. So what's going to happen is all 3 of those default parameters will be substituted, and I'll end up with an object none 0 0, which is exactly what I want. In the case of Frank, I'll end up with Frank 0 0 because the none will be overridden by the Frank. In the last one, all 3 of my initializers will be supplied, so it'll be villain 155. Now, there's another one that we've got here as well, which is this one. Let's just say player hero. And suppose I want to say this is hero, and it's 100 for the health. Now in this case, that hero object will have the name hero, 100 for health. Since the XP wasn't supplied, the XP will get the value of 0. Now this is a constructor we didn't have before. We didn't have a 2-args constructor. Okay, so let's run this and we'll walk through it. And I'll put the out screen over here. The output screen will be real simple. We'll just get this 3-args constructor message being displayed all the time. That's the only constructor we have. Okay, so let's start here. Here's my player empty, right? This is a no-args constructor that's going to be called. Well, we don't have a no-args constructor, but we've got this constructor that expects 3 arguments, and we're telling the compiler to default those 3 if it has to. In this case, it has to. So what it's going to do is it's going to provide none 0 0 and call this guy right here. Okay, so let's step through this and we'll see. We're in the constructor now. You can see that that constructor did indeed get called. We're on line 20 right now. And we're going to initialize it. We're going to display 3-args constructor over here. And then we're back to main. At this point, empty should have none, 0, 0, which is exactly what we've got. Now, in the case of the player, Frank, I expect it to have Frank 0, 0. So let's walk through that. There I am at line 20 again. I'll step through it a couple more times. Now we'll see 3args constructor again being displayed. I'm back in my main, and if I look at Frank here, we see Frank 0, 0, which is again what we expected. Now the hero object, we expect to have hero 100 and 0. So let's walk through that. We're in that constructor right now. We're in the initialization list, and we'll print out the 3args constructor message one more time. We're done initializing that object now. So if we look at hero, we should see hero 100, 0, which is again exactly what I expected. Now in the last case, I'm providing all 3 of the initializers. So what we expect is villain 155, right? None of the default parameters here will be used. So let's try that out. We'll walk through it, and we're back in main now. And if we look at villain, we'll have villain 155, just what we want. Okay, so that gives you an idea of how we can use default constructor parameters, which is really, really handy. It'll definitely simplify your code. As I said before, you can't always use these. Sometimes it really doesn't make sense to provide default parameter values. You really want, the user to explicitly provide all of them. But sometimes you can, and when you can, they come real handy. Now, just before we wrap up this video, let's see what happens if we supply a constructor and C++ has an issue with ambiguity. So in this case, remember, we're handling all of these types of initialization here, right? 0 argument, 1 argument, 2 arguments, and 3 arguments, all with a single constructor. So what happens if I decide to do something like player, no args constructor, and I implement that? Well, hopefully you'll see the problem. When the compiler sees the code on line 28, it doesn't know what to do. It could call this default constructor, or it could call this overloaded constructor with the 3 default parameters. It's not going to guess. It's just going to give you a compiler error. So let me debug this or build it and run it, and you'll see the error so you can see it. In case you get it, you'll know what it's talking about. It says right here, error call of overloaded player is ambiguous, which is exactly correct. In this video, we'll learn about the C++ copy constructor. When objects are copied, C++ must be able to create a new object from an existing object. In order to do this, it uses something called a copy constructor. There are several use cases where a copy constructor is used. For example, if we pass an object by value to a function or method as a parameter, then we need to make a copy of that object. The same is true when we return an object by value from a function or method. And the last common use case is when we want to construct a new object based on an existing object of the same class. C++ must provide a way to accomplish this copying. So C++ uses a copy constructor. We can provide our own copy constructor, and we can define exactly the semantics we need for object copying. But if we don't provide a copy constructor, the C++ compiler will provide a compiler-generated one. Let's look at some of the use cases in more detail so you can see exactly when an object copy is required. The first use case is when we pass an object to a function or method by value. Remember, the default mode of passing data in C++ is by value, which means a copy is made. So in this example, we have hero, which is a player object. And then we have a display player function that expects a player object by value. So when we call this function and pass in hero, the function parameter p will be created, and it will be created as a copy of hero using the copy constructor. Notice that p is local to the display player function. So when p goes out of scope, the destructor will be called as well. In this use case, we have an enemy object, which is a player. We also have a function, createSuperEnemy, that creates and returns a player object. Notice that the player object and enemy is created in the function and then returned from this function. Since we're returning an enemy by value, a copy of the enemy object is made by the copy constructor. The last use case we'll look at is when we want to explicitly create a new object from an existing object. In this example, we have a hero object, and we want to create another object called another hero, based on hero. In this case, a copy is made using the copy constructor. So now you can see where copy constructors are used. Now let's see what they do. If you don't provide a copy constructor, C++ will generate a default copy constructor that will do member-wise copy. That means that it'll go through the class attributes and copy them from the source object to the target object. For attributes that are objects, then their copy constructors will be called. In many cases, this is perfectly fine, and the default copy constructor is all you need. But if you're using raw pointers, then only the pointer will be copied, not the data that it's pointing to. This is referred to as a shallow copy rather than a deep copy. I'll defer shallow versus deep copying until the next video, where we'll look at a specific example. So, best practice with copy constructors are always provide a user-defined copy constructor if you're using raw pointers. Always implement the copy constructor with a const reference parameter. Use the standard template library classes as member attributes. They already provide copy constructors. Or you can avoid using raw pointers as data members if possible, or use smart pointers. So what does the method signature look like for a copy constructor? The syntax might look strange at first, but it's pretty straightforward. First, it's a constructor, so it has the same name as the class. And in the parameter list, we have a single object passed in of the same type. We pass that object in as a reference and a constant. Why by reference and constant? First, if we pass it in by value, then we have to make a copy of it. That's the whole point of the copy constructor. We would defeat the purpose and end up with never-ending recursive calls. And as a constant, because the semantics of copying means that we're copying the source, we're not modifying it. So the const prevents any modification to the source object. The last two statements are the prototypes for the player and account copy constructors. Note that they're exactly the same except for the names of the classes. So how do we actually implement the copy constructor? In the next video, we'll look at the case where we have raw pointers as data members, and we'll do a deep copy. In this video, we'll just concentrate on shallow copies. In the body of the copy constructor, we do whatever we need to initialize our new object. Remember, we have access to source, so we can reference any attributes we want from source. But rather than write assignment statements in the constructor body, we can use a constructor initialization list as we've done before. Here is the implemented player class copy constructor. Notice that we're initializing the newly created object attributes in the initializer list based on the source object's attributes. Pretty simple and intuitive. Of course, any code we write in the constructor body will be executed immediately after the new object is initialized. And here you can see the copy constructor for the account class. Again, we're initializing the newly created object based on the existing source account object. Now let's head over to the IDE. We'll write a copy constructor for the player class and step through the code so you can see exactly when it's called. Okay, so I'm in the IDE now, and I'm in the section 13 workspace in the copy constructor project. And what we've got here is that player class that we've been using all along. I just made a couple of little changes to it. I created 3 getters here, and we're going to use those getters in a display function, which we'll write in a little bit. And they just return the name, the health, and the XP. We've got our single 3-arg constructor here with default parameters as we've done before. And it's implemented right down here using our initializer. Okay, so that's all we've got. We've created 4 objects down here. Now, the first thing we want to do is let's write the prototype for the copy constructor. And it looks like the name of the class, which is player in this case, and a single object in the parameter list. And it's a const player by reference. And we could just leave it like that, or we can put source in here. It doesn't really matter. So that's it. That's all we need to say. Obviously, we need to implement that, and we'll do that in a minute. And the other thing I want to do here is I want to write a destructor. And basically, I just want to know when this thing is going to be destroyed, because it's going to be very important so that we understand the life cycle of these objects. So again, how do we write a destructor? We put a tilde in front of the destructor name, which is the name of the class, no parameters. And in this case, I'm just simply saying I want to output that the destructor is being called for, and we'll just put a colon here, and we'll do that for that name. That way we know which object is actually being destroyed. Okay, that's it. So now we've got our destructor. So what we need to do now is implement that copy constructor. And I'm going to do it right down here, right after our constructor. So what do? Well, we start off by writing player, scope resolution operator, player again, and we're going to implement the same prototype basically, right? So it's const player by reference source. And now what we can do is we can create the initializer list if we like. And how are we going to initialize this? Well, I want to initialize the name attribute to what? To this object's name attribute, in which case it would be source dot name. I want to initialize the health attribute to source dot health. Remember, I'm making a copy, so I'm copying these values over. And the XP to source dot XP. That's it. Now we implement an empty body for that copy constructor. And what we'll do is in the body, we'll write an output statement. We'll say cout, and we'll write something like copy constructor. And we'll do something like made, let's see, we made a copy of what? We made a copy of source name. And we'll put an end line there. Okay, so that's it. That just tells us that it'll tell us what we've made a copy of. That'll come in handy when we're stepping through this and we can understand what's going on. Okay, so now we've got our copy constructor set up. Now let's create a function that expects a player by value. And we know that that's one of the use cases where the copy constructor is called. So let's do that. Let's write just a regular function and we'll call it display player. And it will expect a player object. We'll call it P. And remember, it's expecting it by value here. That's the default way of passing parameters around. So this implies a copy. And in here, all we're going to do is, and I'll just copy the code that I've got over here so I don't have to type it all in. And what we'll do here is just create those three output statements that displays p.getName, p.getHealth, p.getXP. So it's just going to display those values for P. Okay, now I'm going to put some breakpoints all over here just so we can see what's being called. We won't do it in the destructor because we'll see that being called. It'll just print out destructor called. And what we've got now is we've got an empty object, Frank, hero, and villain, which are all objects. And these are just regular constructor calls happening here. So what we'll do down here is, actually, we'll do it right here. What we'll do now is we'll say something like display player. I'll leave an extra line here. We'll say display player, and we'll pass in empty. Empty is an object. So what's going to happen is a copy of that object will be made. Okay, so what I'm going to do is, again, I'll put a breakpoint right there, and let's debug this, and we'll step through it. And I'll move the output window just over there. Okay, so let's step through this, and you can see that right now we're on line 26, and that's because that's empty player object is being created here. And we should see that print out that constructor right there. So we've just 3args constructor for none. Remember, that's the default, none, 0, 0. And we'll step through again, and now we're just about to call this display player function here. We'll look at empty, which is the object we just created, and it contains none for name, 0 and for health, and 0 for XP. Okay, so we're just about to call this function right here. Now, before we pass any information in, we have to make a copy of it, right? Because we're doing pass by value or pass by copy. So I've got empty, which you can see right here. I need to make a copy of empty, and that's what P is going to be. Now, P is local to this function. So again, it's a copy of empty, and it's on the stack, right? So let's step through, and what we should see is we should see the copy constructor being called because a copy needs to be made right now. So let's step through. And there you go. You can see we're right on line 31 and we're in the copy constructor. What are we doing now? We're making a copy of empty, and that copy is going to be called P. So let's step through again. We just did the initialization, and now it's going to say copy constructor made copy of none. That's exactly what we did. We made a copy of that object whose name is none. Okay, now I'll step through one more time. Now that P has been created. You can see P right here. It's a local variable to this function, and it's none00. It's a copy of empty. There are two different objects, but they have the same values right now. Okay, let's walk through this. We just displayed the name, the health, and the XP. Now what should happen is P is going out of scope right now, right? We're going to leave this function, so that stack frame needs to be cleaned up. So the destructor for P should be called. The destructor for the copy, not the destructor for empty, but the destructor for that P copy. So let's do that. And there you go. You can see the destructor has been called. And now we're back in main on line 46. And from this point on, we're just constructing objects as usual. Okay, so hopefully that's clear. You can see it's these little nuances, and using the debugger to step through things really makes things very nice to follow. So let's do another example here. I'm going to stop the debugger here. And what I'll do is we'll create that empty. Well, you know what? Let's create a different empty. In this case, let's just create something called XXXX with 150. That way we know what those values are. And what I want to do here is I'm going to get rid of that breakpoint right here. I want to create another player object. Okay, and I'm going to call it my new object. And I'm going to create a copy of that empty object. Okay, so again, let's see what's going on here. I've got empty is a player object, and I'm setting the name to a bunch of X's, the health to 100, the XP to 50. Then I'm creating another object. It's called my new object, and I'm creating it from empty. So I want a copy of empty. This will call the copy constructor. That's the whole idea. I'm making a copy. Okay, so let me put a breakpoint there, and let's run this debugger through again. Okay, so now we're here constructing that empty object right over here. So let's just walk through that until we get to that other breakpoint on line 44. And that's where we're at now. So at this point, empty has been created. If I look at empty up here, you can see I've got the bunch of X's, 150. So now I'm right here on line 44. This is a constructor, right? I'm constructing or initializing or instantiating, the jargon's all the same, a my new object, which is a player. In this case, from this object that I've already created, that's where the copy comes in. So when I step through this, I expect the copy constructor to be called again. So let's do that. And there we are. We're right in the copy constructor in the initializer, and I'm going to walk through that. It says right here, I made a copy of that original XXX6X object. I'll step through again. And now we're right back to where we started before. Okay, so hopefully that gives you some insight into these copy constructors and how they work. They really make a lot of sense. The syntax is a little wonky sometimes, but it's pretty straightforward. Now, one thing that I should mention is right here, we're using the initializer list to initialize that new object. We could change this if we like and just do something like use a delegating constructor here. Right? So we could delegate source.name, source.health, and source.xp. And I need a little colon in front of that just like before. So what we're doing there is we're doing the delegation. And the same exact thing should happen. We'll run the debugger here, and we'll walk through that real quick so you can see the delegation now happening. Before, we weren't delegating because we were just initializing right in place there, right? So at this point, let's walk through it until we get to line 45 this time, which is where we're at right now. So now I'm going to call the copy constructor again to make a copy of this empty object we just created. So let's step through it. Right here, I'm in the copy constructor. But now, rather than use this initializer, I'm going to delegate the construction of this object to my constructor, which is this guy right up here. So in this case, when I walk through it, You can see control will transfer up to here on line 25. And that's exactly where we are now. Now we're in the regular 3arg constructor, and it's going to say 3args constructor. Remember, the first one was for empty. This is for the copy of empty. So we've got the two objects alive now. And when I'm done, I'm going to come back and say made a copy of it. Okay, so there you go. There's the copy constructor, and you can see how we can delegate from that as well. In this video, we'll look at the difference between a shallow copy and a deep copy in the context of the copy constructor. First, we'll assume that the object we're copying has a raw pointer. When the object is constructed, we'll likely allocate storage for the data that that pointer is pointing to. And then when we're done with the copy, we'll release the memory as per best practices. But what happens in the copy constructor? We can do a shallow copy or a deep copy. Let's see what that means. Let's first look at doing a shallow copy and the problems we can run into. A shallow copy is the default behavior provided by the compiler-generated copy constructor. It basically does member-wise copying of all the object attributes. So you end up with the newly created object and the object being copied, both pointing to the same area of storage in the heap. So what's the problem? Well, the problem comes into play when one of those objects is destroyed and its destructor is called. When this happens, the object's destructor releases the memory allocated on the heap as it should. However, the other object is still pointing to this released area and thinks the area is still valid. This could lead to subtle errors. The best thing that can happen is that the program crashes while in development so that you can fix the error. But we'll learn how to do a deep copy and avoid the error completely. But first, let's walk through an example that has a class with a pointer attribute that does a shallow copy so we can really understand the problem. Here's the class we'll use in this example. The class is called shallow, and it has a single data attribute called data that's a pointer to a single integer. This class is about as simple an example as we could write that demonstrates the problem with a shallow copy. But any class that has a raw pointer as a data member will have the same issues. This class has a constructor that expects an integer, a copy constructor, and a destructor. Let's see how these are implemented. Here's the code for the constructor. Notice that the constructor allocates storage for the integer and stores the passed-in integer d where that data pointer is pointing. Since we allocated this storage dynamically, then we must be sure to release it in the destructor. Let's do that now. Here's the destructor. It simply frees the storage that was allocated by the constructor as it should. It also displays a message to the console. Okay, so now let's implement the copy constructor. Here's the copy constructor. This copy constructor is user-defined, but it provides the same semantics as the default compiler-generated copy constructor if we hadn't provided this one. Notice that in the initializer list, we simply copy the pointer. This is member-wise copy. Now we have a problem. In this case, the source object and the newly created object both point to the same area and heap that was allocated for the data. But why is this a problem? Well, the problem comes into play when we make a copy of a shallow object using the copy constructor that's doing a shallow copy. Suppose we have a function display_shallow that expects a shallow object by copy. We make the copy with the copy constructor as usual, but when that local object s goes out of scope, its destructor is called, and the destructor releases the storage in the heap that s is pointing to. You see the problem now. The object that was copied into this function still points to this now released storage, but it thinks that the storage is valid. So all kinds of bad things can happen now. Here's a sample main. We create object 1 as a shallow object. Object 1 will be created and an integer will be allocated on the heap and 100 stored in it. Now we call display_shallow, and a copy of object 1 will be created inside that function. And when that function is done, the copy of object 1 will be destroyed. Since object 1 and the copy that was just destroyed pointed to the same memory area, object 1 now points to invalid storage. If we try to access that storage from object 1, our program could crash. Also, when the destructor for object 1 eventually gets called, it will try to release memory that's no longer valid and will probably crash. Let's head over to the IDE and we'll walk through this example and I'll draw out exactly what's happening. Okay, so I'm back in the IDE. I'm in the section 13 workspace in the shallow copy project. And we've got a program, and the class is called Shallow. It's the same one that I put in the slides. I made a couple little changes in the main just to streamline it a little bit. Anyway, this program does a shallow copy in the copy constructor, and I'll walk you through that right now. But first, let's just run it. And I'm going to run it without the debugger so you can see that it does indeed crash. And there's the crash right here in Windows. And it's a bad crash. Okay, it's not the kind of thing we want. So the point of this, this video is to try to understand exactly why this is crashing, why we need a deep copy, and why we've got to be really careful when we use raw pointers. So let's take a look at the class. The class is Shallow. It's got a raw pointer here to a single integer. We could have created an array of integers, a pointer to some sort of object. It doesn't really matter. In this case, it's about as simple as example as you can get. And here we have a set value and a get value that we're using in my main. We have a constructor that just expects the integer. And what it does is, you can see the source code for the constructor right here on line 21. It allocates storage on the heap dynamically for that one integer. And the integer is D, it's being passed in. Then I'm just dereferencing the pointer and storing that integer where data is pointing. Really, really simple. Okay, the destructor, let's take a look at that. Obviously, whenever we allocate storage in the constructor, the best practice is to release that storage in the destructor. That's what we're doing here. And in this case, we're just displaying destructor freeing data so that we can see when it's being called. We're going to step through this in the debugger, so we will definitely be able to see when it's being called. And then we've got the copy constructor. In this case, we're doing a shallow copy. And you can see right here on line 27, in the constructor initialization list, all we're doing is we're copying the value in that data variable, which is the pointer, from source to this, which is the object we're creating right now. So it's copying the pointer, not what it's pointing to. What's going to happen is both these objects, when we copy them, will be pointing to the same area. And I'll show you that in the debugger. Then we've got a real simple function right here called display shallow, which we pass in an object by value. So we're going to make a copy of it. And that's where the problem shows up. And again, I'll walk you through that. Okay, so let's debug this, and we'll step through it so we can see exactly what's going on. And I'll move the output window over here to the right so we can see our constructors and destructors being called. All right, so I'm right here on line 42. And here we're just doing a regular constructor call, and we're passing in the integer to us. So this constructor right here on line 21 will be called. So let's step through this. And you can see now we're on line 22. We're going to allocate the new integer on the heap. We just did that. And now I'm storing 100 into that area. And I'm back to line 43. So at this point, obj1 has been created. It's right here. And you can see that data is a pointer to an integer. And we just stored 100 where that integer was pointing. Okay, now we're going to run into a little bit of a problem. This is where the deep copy is necessary rather than the shallow copy. And I'll do another video after this where we'll do a deep copy, and I'll explain how that exactly works. But let's walk through this. We're going to call display shallow, which is this function right here on line 36. And this is just a regular function. It's not a member function. And we're going to pass object 1 into it. Well, we're doing that by value. You can see right here, there's no pointer, there's no reference, it's just by value. So we need to make a copy. So what we expect is that C++ needs to make a copy. So it's going to call the copy constructor to do that. And let's do that right now. So we'll step through it. You can see right here, we're in the copy constructor, and we're doing that shallow copy. So at this point, you can see, let me just step one more line. Okay, so what we've got now is, let's take a look over here. We've got source. Now remember, source is what's being passed in. So source in this case is obj1. So we've got, so obj1 right here has a pointer data that points to an area in memory, and we stored 100 in there. Now the location of that memory is right there, Foxtrot 00. So I'll just write that in there, those last 3 hex digits. So it's Foxtrot 00. That's where that data is on the heap. Okay. Now look what happened. I just made a copy of obj1, but I didn't copy what it's pointing to. I only copied the data. So if you can see as I expand this, which is right here inside here, this is the new object we're creating, this right there, you can see that the address of that pointer data is exactly the same. Right? So what we just did, we just created a copy of this that's pointing to the same area in memory. So let's walk through this a couple more steps, and then we'll just keep going here. Great. Now we're here. We've just created the copy. So what we just did was we created a copy, and it's called S. It's right here. Now S has a pointer called data, and guess what? It's pointing to the same area in memory as obj1. So what we just did was, yeah, sure, we made a copy of obj1, absolutely, but we didn't make a copy of what that data pointer was pointing to. Ideally, what we would want with a deep copy is for S to be pointing to its own copy of that data over here, but that's not what's happening here. Okay, and what we can see is, let me clear the screen real quick. What we can see here is that if we look at the S right here, that's that local variable. You can see that Foxtrot 00. It's pointing to exactly the same memory location. So here's the problem. Right now, S is just about to go out of scope. So again, let me draw that one more time just to be very, very clear here. We've got obj1 pointing to this area right here where it's got 100. And again, that's the data attribute that's pointing, right? And then we've got S, which is also pointing to that area. Well, now S goes out of scope. What happens when S goes out of scope? We get the destructor called, right? So let's walk through that so we can see that destructor being called. It's out of scope right now. Boom, there's the call to the destructor on line 32, and the destructor deletes data. So what did the destructor just do? It freed up this area in memory right here. So as far as the C++ runtime system is concerned, this is no longer valid memory, right? We just deleted it. So this guy right here now is pointing to invalid memory. Now, hopefully you can see that that's a big problem here. So what's going to happen? Well, let's keep going. We're going to destructor freeing the data. Now we go back to main right here. And notice where we're at right now. At this point, this is now gone, right? Because all that's been cleaned off the stack. And I'll take those X's off just so you can see what's going on here. This is the situation we've got. We've got obj1 now has a pointer called data that's pointing to an area on the heap that has 100 in it, because that hasn't changed, but that memory is invalid. So now if we try to make a copy of obj1 and call it obj2, again, this calls the copy constructor again. Let's see what happens here. Let's walk through this. Again, copy constructor gets called because we're making a copy. And what did we just do? Well, we just copied it again. So now we've got two objects pointing to invalid data. And I'll walk you through this. And we're back to main here. So what I've got now is I've got obj2 right here pointing to that same invalid data. Yeah, that's not good. And you can obviously see what's going on here. You can see obj1 and obj2 are pointing to exactly the same memory locations. Right here, you can see Foxtrot 00, Foxtrot 00. That's the situation we've got right here. So this could be problematic in a lot of ways. Suppose that on line 46, I'm setting the data value for obj2 to 100, right? So I'm coming this way, to 1000. So I'm coming this way through this area here. I'm trying to put 1000 in there. Well, what did I just do? Assuming that this worked, right? Assuming that we haven't allocated any other objects and they've reused that space. But what did I just do? Well, I just changed obj1's data 2 to 1000 indirectly without even knowing it, because they're both pointing to the same area in memory. So let's walk through that and you'll see exactly what I'm talking about. Okay. Right now, you can see they're both pointing. Let me refresh this here. Since they're both pointing to the same area in memory, I just changed OB2's data to 1000, but look what happened here with OBJ1's data. Right? It changed to 1002. Of course it did. We're pointing to the same area in memory. Right? Now comes the problem, and this is where the crash comes in, and I'll clear the screen real quick. As we unwind now and start freeing up these two objects, right? I mean, they're going out of scope right here in main, so we need to delete the data for both of them. We're calling both the destructors. Well, that pointer is pointing to invalid data, so when we try to delete it, we're going to have a problem. That's where the crash comes in. And I'll just step through it. You can see the destructors being unwound now. And at some point, we will crash. There's the crash right there. Okay, so you can see what's happening here. You can see how important it is to really understand what's going on with your heap memory when you're using raw pointers. What we'll do in the next video is we'll go over deep copy, and then we'll do another example of this that we just did now using deep copy so you can see how that works better. Now that we know what shallow copying is in the context of the copy constructor, let's look at deep copying. With a deep copy, we don't just simply copy the pointer. Instead, we copy the data pointed to by the pointer. This usually means that we have to allocate storage for the copied data and then perform the copy. With a deep copy, each object will have a pointer to unique storage in the heap, and both areas will contain the same data. You always want to use a copy constructor that does a deep copy when you have raw C++ pointers. Let's look at the class we'll use in this example. It's exactly like the class we use for the shallow copy, except that I named this class deep to be clear. We have a raw C++ pointer that points to a single integer, and here's the class we'll use. This class has a constructor that expects an integer, a copy constructor, and a destructor as before. And let's see how we implemented these methods. Here's the constructor, and you can see that this code is exactly the same as we implemented in shallow. After all, we want to create those objects the same way. The constructor allocates storage for the integer and then stores the passed-in integer d into where that data pointer is pointing. Since we allocated the storage dynamically, then we have to release it in the destructor, so we'll do that now. Here's the code for the destructor. Again, it frees the data that was allocated by the constructor and displays a message to the console. Now, this is where the change comes in. It's with the copy constructor. Let's see the difference. So here's the copy constructor. And this is where things change from the copy constructor we saw previously that does a shallow copy. Here, we don't simply copy the pointer. Instead, we allocate storage for the copy of what we're pointing to and then copy the data itself over. So you can see we're creating a new integer, and then we're copying what the source data pointer is pointing to, which is an integer, into our newly created area on the heap. And we're also displaying a message. Now we have an exact unique copy of the original heap storage in each object. Since we can also delegate object construction from a copy constructor to another constructor within the same class, we can do that as follows. Notice that we're delegating to the constructor that expects an integer, and the integer we're passing in is the one pointed to by data. Now we've made a deep copy of that data pointer, and both source and the newly created object each have an exact unique copy of the original heap storage. So now we'll have that function display deep that expects a deep object by value. We make a copy of S, use it, and then when S goes out of scope, we call the destructor, which frees up the allocated storage. In this case, there is no problem since the allocated storage pointed to by the data pointer in S is unique to S. And finally, here's the main that we used for the shallow example, except we're using it now with the deep example. This code will now run correctly. There won't be any crashes and no problems because the copy constructor is doing a deep copy and we're responsibly handling memory. Now let's head over to the IDE and we'll walk through this example and I'll draw out again exactly what's happening with the deep copy. Okay, so I'm back in the IDE. I'm in the section 13 workspace and I'm in the deep copy project. In this case, we're using a class called deep. It's exactly like the class called shallow that we used in the last video with the exception of the copy constructor. In this case, you can see the copy constructor right here on line 26, and it's doing a deep copy by delegating to our regular constructor. That's really the only difference is we're not just copying the pointer, we're copying the data pointed to by the pointer. So let's walk through this example using the debugger. And let me move that output window over to the right. And right now we're on line 42. So we're just about to create object 1. Now this is just a regular simple instantiation with the constructor here on line 21. So let's step through it. We can see now we're on line 22. We're creating that integer on the heap and we're storing the 100 into it. And now we're back. So object 1 at this point has been created and you can see object 1 right here. You can see data is a pointer to an integer and the integer it's pointing to is 100. And you can see the address that we're pointing to is Foxtrot 98. So this is where we're at right now. We've got object 1 right here. It's got a pointer called data. And it's pointing to an integer on the heap. That's 100. And its address is ending with Foxtrot 98. That's the situation now. So the next thing we want to do is we want to call display deep. Display deep is this function right here. Again, this is a regular function, not a member function. we're passing in a deep object into it by value. So we need to make a copy of it. So when we're in this function, S will be a copy of object 1, which is what we're passing in right here. In order to get the copy, we need to execute the copy constructor. So let's do that right now. You can see the control transfers right here into the copy constructor, and then the copy constructor is going to delegate construction to our regular constructor that just expects a single integer. And that's what's happening here. So now we're creating storage and we're copying that data into it. And now we come back to our copy constructor, we display our message, and we're back now on line 37. So S has been created as a copy of object. Now, let's take a look at S. You can see S right up here, and you can see we've got a data pointer and pointing to 100. So at this point, what's really going on is S right here is an object, and it's pointing to an integer. Obviously, it's using its data pointer to do that. And that integer contains, you can see right here, contains 100, and it is an address Foxtrot Baker 8. So we've got two different areas in the heap. So each one of these is pointing to a unique area. This is really what deep copy is all about, because what's going to happen in a second is when we finish this function right here, we need to clean up S, right? It's going out of scope. So the destructor for S is going to get called, and it's going to free up this area in memory. It's not messing with this area. So when we come back from this function and come back to main, object 1 is still pointing to valid data. This is very, very different from the example we saw with shallow. So let's run through this, and we're right here. You can see we're just about to go out of scope on line 38. And there it is right there. The destructor is being called on line 32. The destructor is going to free up this object right here, which is Foxtrot Baker 8 right here. We'll execute that line of code. My destructor just freed the data, and now I'm right back to main on line 45. So at this point, this has been taken off the stack. It's all been cleaned up. And this is the state that we're in right now, which is exactly what we expect. Okay. Same is true on line 45. Here, what we're doing is we're making object 2 a copy of object 1. So again, we expect the copy constructor to be called here. So let's walk through this. There it is. There's the call. We're going to delegate construction to our regular constructor, which happens here. My data gets written over, and I'm back. Now at this point, you can see that object 1 and object 2 both contain 100, but you can see the addresses they're at. They're completely different memory addresses for that 100. So in other words, object 1 has a copy of 100 in its own area, and object 2 has a copy of 100 in its own area. And in this case here on line 47, if I set that integer value for object 2 to 1,000, and let me do that right now, you can see when I refresh that object 2's data is 1,000, but object 1 data is still 100. Again, really different from what we had with the shallow copy, since they were both pointing to the same place. So that's it. At this point, we'll unwind. So we free up object 1 and object 2, and our program completes with no crashes at all. Okay, so that gives you a little bit of a perspective with shallow copies and deep copies. Later on, we'll do this with smart pointers, but it's really important that you understand exactly what's going on with raw pointers first. In this video, we'll learn about C++'s move constructor and move semantics. These features were introduced in C++11, and they can be difficult to understand, so we'll take it slow and one step at a time. While move semantics is not considered a beginning C++ topic, it's important to understand it conceptually so you can identify it in code when you see it. One of C++11's most pervasive features was probably move semantics. And to really understand move semantics, it's important to be able to tell whether an expression is an L value or an R value. If you need a refresher about L values and R values, please refer to the L values and R values video in section 12 of this course. But a useful rule of thumb is that when you can refer to an object by name, or you can follow a pointer to get to an object, then that object is addressable and it's an L value. and R values are everything else. But in the context of move semantics, R values refer to temporary objects that are created by the compiler and objects returned from methods. As you can see in this slide, when the expression 100 plus 200 is evaluated, the compiler stores 300 in an unnamed temporary value. This value is not addressable, so it's an R value. The R value is then assigned to the L value total. The same happens with objects. However, with objects, there can be a great amount of overhead if copy constructors are called over and over and over again, making copies of these temporary objects. And when we have raw pointers and we have to do deep copies, then the overhead is even greater. This is where move semantics and the move constructor comes into the picture. R value objects are the objects that move semantics addresses. We know that copy constructors are called whenever the compiler needs to make a copy of an object. We also know that if our class contains a raw pointer, then we must implement deep copy. However, this can be computationally expensive since we have to allocate space for the copy and then copy the data over. The C++ move constructor moves the object rather than copies it. This can be extremely efficient. Move constructors are optional. If you don't provide them, then the copy constructors will be called, but it's a good idea to use move constructors for efficiency. Finally, when you run your code and step through it in the debugger, you might not see move constructors being called. In fact, sometimes you may not even see the copy constructors being called. If you experience this, it's probably due to something called copy elision. Copy elision is a compiler optimization technique that eliminates unnecessary copying. Compilers are really smart with their optimizations now, and one of the common techniques is called return value optimization. That's when the compiler generates code that doesn't create a copy of a return value from a function, making the code much more efficient. So let's start by talking about R value references. We've already seen L value references, which are references to L values. Well, R value references are references to R values. In the context of move semantics, think of R value references as references to those temporary objects that we were talking about. L value references are declared using a single ampersand like we've done, but R value references are declared using 2 ampersands. Let's see some examples. In this example, we'll see the difference between an L value reference and an R value reference. First, we declare X as an integer and initialize it to 100. In this case, X is an L value. It's addressable, and it's got a name. Now we can create LREF as a reference to X. And since X is an L value, this is an L value reference. We can use LREF to refer to X. Nothing new, this is stuff we've seen already. But now let's see what an R value reference looks like. RREF is declared as an R value ref to an integer with a double ampersand operator, and we set it to refer to 200. Since 200 is an R value, this makes RREF an R value reference. Now we can actually assign 300 to RREF, which stores 300 into the R value of where RREF refers to. In other words, we just changed that temporary variable. Notice that if we try to assign an L value to an R value reference, we get a compiler error, which makes perfect sense. So now let's look at L value references in the context of function parameters. This is what we've been doing all along up to this point in the course. We have an integer X, we initialize it to 100. X is an L value. Now look at the function func. It expects an L value reference, as denoted by the single ampersand. So it wants an L value. If we call func and pass in X, then this is okay since X is an L value and num will be the reference to an L value. But what happens if we call func with 200? Well, 200 is not an L value, it's an R value, and the compiler will generate an error. You can see the error message below that the compiler generates. Now let's look at R value references in the context of function parameters. We again have defined X to be an integer and initialized it to 100. This time we declare func as a function that expects an R value reference, and we denote that with the double ampersands. So it wants an R value. If we call func and pass in 200, this is okay since 200 is an R value, and now num will be a reference to an R value. But what happens if we call func with X? Well, we get an error message. X is not an R value, it's an L value. So the compiler generates the error, and you can see the message it generates below. Now we can overload these functions and have both of them in our code at the same time since they have unique signatures. And the compiler will call the correct function depending on whether the parameter is an L value or an R value. We're going to take advantage of this when we define the move constructor. So now let's see how this works with a move constructor in a class. Here I've created a class named move, and it has a raw pointer as a data member. This class is similar to the shallow and deep classes we used earlier in this section. The rest of the class methods are pretty standard, and we've seen them before. Notice that we've included a copy constructor that does a deep copy. We have not defined the move constructor yet. We'll do that soon. But first, let's look at the copy constructor. Here's the code for the copy constructor. Again, pretty standard deep copy. We allocate storage, and then we copy the data. Now we run a simple main that creates a vector of some move objects, and we call the vector vec. And we push back two move objects. Now notice what's happening in the argument list. Move 10 and move 20 are creating temporary objects. They're unnamed, so they're going to be R values. What happens is that the compiler is going to use the copy constructor to make copies of these guys. So here's the sample output from that program. You can see constructors and destructors and copy constructors being called. In fact, you can see that the copy constructor is doing several deep copies, which can be inefficient. Now, let's add the move constructor to the class to make it much more efficient. So what does the move constructor actually do? Well, instead of making a deep copy like the copy constructor does, instead of making a deep copy as the copy constructor does, it simply moves the resource that's on the heap. And the way we do that is just to assign the pointer from the source object to the current object. You might be thinking, isn't that what default member-wise copy is? And yes, it is. But now the difference is that we null out the pointer in the source object. So what we have now is an object who owns the data on the heap and then the original object with a null pointer to that data. This is real efficient since we're not doing a copy at all. Before we implement the move constructor, let's look at its syntax. As you can see, it's very similar to the syntax for a copy constructor, but it's got two differences. First, there's no const qualifier for the parameter source. There can't be because we need to modify it in order to null out its pointer. And second, the parameter is an R value reference, and you can see that with the double ampersands. You can see in the last two declarations what the move constructor prototype might look like for a player class and the move class. So here we're adding the move constructor prototype to the move class declaration, and now we need to implement it. Notice how simple the implementation is. We simply copy source.data to data. That's a simple copy of a pointer data member. Again, we're not copying what it's pointing to. We're not doing a deep copy. Then we null out source.data. This step is really important. Otherwise, we end up with the equivalent of a shallow copy and not a move. That's it. Many resources that describe the move constructor say that it steals or pilfers the data and then it nulls out the source pointer. And that's really a good way to think about it. That's exactly what it's doing. Now we've got our same program, and when we execute it, instead of the copy constructors being called for those temporary objects, the move constructors will be called because there are values. And it's going to be much more efficient than doing deep copies. So let's take a look at the output now. As you can see, there are no copy constructor calls at all, and the move constructor is indeed being called. You can also see when the destructors are called for null pointer. That's destroying the object that we just moved and set its data pointer to null. So there you go. That's a basic introduction to R value references in the move constructor. I know it's complicated. You'll probably have to watch this video a few times, but don't worry. Everybody goes through this. It's a difficult topic to understand. We'll see move semantics again in the next section of the course when we overload the assignment operator to do both copy and move. There's so much more to move semantics in the move constructor that are better left for a more advanced course, but now you know the foundations and you'll be fine when you learn about them. So let's head over to the IDE and run this program and see it in action. Okay, so I'm in the IDE. Again, I'm in the section 13 workspace in the move constructor project. And what I've got here is that class move that we used in the slides. It's got a raw pointer to an integer. It's got get, set methods, and your typical constructor, a copy constructor, a destructor. Now you'll notice that I've got a move constructor here, but I've commented it out because I'm going to run this first with only the copy constructor so you can see what's going on. And right here's the copy constructor on line 17. Here's my implemented copy constructor. Again, I've commented out the move constructor. We'll uncomment that out in a moment. And here's my destructor. My destructor looks a little different because if my data is not equal to the null pointer, then I'm just saying what I'm destroying. Otherwise, I'm just saying that I'm destroying null pointer. And that's important because it will let us know if we are destroying those objects that we just moved. And it'll be really easy to see when it says null pointer. Okay, so here's my main. I'm creating a vector of move objects, and I'm simply calling pushback, and I'm supplying move in here. Now you'll notice there's no variable name there, right? So that's going to create a temporary object. And a temporary object is an R value. So in this case, it's going to use the copy constructor. Once we put the move constructor in, it's going to use that. So let's walk through this example and you'll see what's happening. So I'll start the debugger. And I'll move the window over here to the right. And this is where we're at right here. So first thing we need to do is we need to construct this object, right? We need to create that temporary object, and we're going to use the constructor to do that. So we'll step through here. You can see the constructor being called here. It's going to allocate that object on the heap and store whatever we passed it into it. We're going to display constructor for 10. And now we're in the copy constructor because remember, we just created this temporary, right? So this temporary now needs to be copied into the vector. So we're in the copy constructor. We're here. We're going to construct the copy. So we're going right back here. We're delegating to the constructor. We're going to create another 10. And it says here, we just deep copied that 10, which is exactly what we did. Now we're back here and we need to destroy that copy we made. So the destructor will be called right now. You can see data will be pointing to 10. And we're going to destroy that copy of 10. That's it. That's pretty much exactly what's happening. You can see that we're using copy constructors just like we've used all the time. Now, the fact that this is an R value, that comes into play when we use the move constructor. Now, I'm going to stop this and I'm going to uncomment out all of these here so you can see what's happening. It might be a little surprising. So what I've done is I've pushed back 10, 20, all the way through 80. Remember, these are all creating temporary objects, so they're going to be copied and copy constructed so that the vector can push them back. Remember, the vector makes copies of these guys, so it's going to make a copy of the temp. That's one of the problems. That's why it's so inefficient. But it's even worse than that, because if we run this without debugging it, let's just build and run. Let's take a look at what we just got here. I'm going to scroll all the way to the top. I'm at the top now. So you can see that I've created that 10, right? Then I've copied it. I've done a deep copy, and then I'm destroying it. I'm doing the same thing for 20. So you can see all these deep copies. But if you count them, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9 down at 10. About 15 deep copies. That's much more than you would expect, right? When you look at the code, I don't think you would expect that many. I mean, there's only 8 pushbacks here. Well, what's going on is that the vector is actually growing behind the scenes. And when the vector grows, those objects need to be copied to the new storage. Remember, the vector is using contiguous storage. So it's making copies of the objects behind the scenes as well. So you can see that a lot of times there's a lot of copying going on behind the scenes that we're not aware of. So that's the version with the copy constructor. Now what we'll do is we'll uncomment out the move constructor. And you can see what the move constructor is doing. The same thing that we did on the slides. The move constructor is simply copying the source data and nulling out the pointer. Really, really straightforward. And I'll uncomment out the prototype here. Okay. Now what we'll do is we'll debug this again. And we'll walk through that very first one so you can see what's happening. So I'm right here on line 55. I need to create that move object, right? That's a regular constructor to create that. That creates that temporary R value. So let's walk through there. I'm going to create that 10 object, that 10 move object. Now notice what happened. The move constructor got called. That's the move constructor right there with the double ampersand. So it got called rather than the copy constructor. Why? Because this is an R value temporary. Now what we're going to do is we're basically going to steal the data and null out the pointer to the source objects, right? So we're going to move it rather than copy it. So We're here, we're sourcing, we're nulling out the source data, and you can see the move constructor got called. Now look what happens when I go to delete that object, right? The one that we just moved, the source. We're here in the destructor, just like we would expect. But if you look at the object we're destroying, notice it's a null. The data's a null. That's the one we just nulled out, right? So in this case, I'm simply saying destructor freeing data for null pointer. So that's really obvious which one is being destroyed. And then at this point, I'm back here. Okay, so you can hopefully see the difference here, how much more efficient this is. And I think you'll really see the difference in efficiency when we just run it without the debugger. So let me just run that without the debugger. And you can see here, again, I'll scroll all the way to the top. You can see that as you scroll down here, there is not one single copy constructor being called. So we're doing no deep copies. We're only moving resources using the move constructor. Okay, so there you go. That's an introduction to move constructors and move semantics. And I think this is a pretty good example that you can walk through and understand what's going on. As we've stepped through our code in the debugger, you've seen an identifier named this in the debugger pane. This is a reserved keyword that contains the address of the current object. So it's a pointer to the object that's currently being used by the class member methods. The this keyword can only be used within the scope of the class. In many other object-oriented programming languages, we use the word self instead of this. But in C++, we use the keyword this. All member access is done via the this pointer. However, C++ allows you to use member names directly, and behind the scenes, it's actually using this pointer. This can be used by the programmer, and in many cases, we must use it. We can use it to explicitly access data members and methods. We can also use it to determine if two objects are the same. We'll use this in the next section when we overload the assignment operator to determine if we're assigning to ourselves. Of course, since this points to the current object, if you dereference it, you'll follow the pointer and work with the current object. Here's an example of one way to write the setBalance method for an account class. Notice that the name of the parameter is BAL and the code in the body of the method is balance equals BAL, which assigns the value of the parameter BAL to the class data member balance. We don't have to write this arrow balance, but that's exactly what the compiler is doing for us behind the scenes. Now suppose that the name of the parameter was balance. Now in the method body, the assignment statement balance equals balance would use the parameter balance for both of those identifiers instead of the data member balance. That's because of scope rules. Now this statement would not accomplish what we wanted to do. So in order to refer to the data member balance, we need to explicitly use this arrow balance. Finally, suppose we have a compare balance method in the account class that compares the balance of one object with another. We could check to see if we're comparing the same objects by comparing this and the address of other. If they're the same, then we're dealing with the same object. In this example, it wouldn't make much difference in our code since we're simply comparing balances. But if our compare logic is involved or computationally expensive, then a quick check to see if the objects are the same could help performance. We'll use the this pointer again in the operator overloading section of the course. In this video, we'll learn a little bit more about the const qualifier in the context of class methods. We've already learned that we can create const variables which can't be changed. And we've also seen how we can pass references and pointers into functions as const, and they can't be modified while in the function. Well, in this video, we'll learn how to create const objects and see what happens when we pass constant objects to methods that don't expect a const. Using const correctly in parameters, as well as method declarations, is the basis for const correctness in a program. In this example, we're creating a const object named villain. Now, once villain is created, we can't change any of its attributes. That's the whole idea with it being const. So what happens if we call member methods on a const object? Let's look at calling a setter method that changes the object. Obviously, this can't be allowed since the object is declared as const. And in fact, this produces a compiler error. The compiler complains that you're passing a const object as this to a method that could change it. But what about the output statement? In this case, I'm not modifying the const object. I'm simply getting a copy of its name for display. Well, this won't compile either. In fact, you get the same error that you get when you called setName. So what's up? Well, the compiler assumes that the getName function could potentially change the object, so it gives an error. But we need a solution to this problem, since we would like to call the getter methods and other methods that are public that don't modify the object. Here's another example. Again, we define the villain object and it's a constant, so it can't change. Now we have a displayPlayerName function that expects a reference to a const object. Again, we get a compiler error. Here the problem is that when we call p.getName in the displayPlayerName function, the this pointer isn't expecting a const object, so getName could potentially change the object. The compiler is being very careful not to allow a const object to lose its constness. So what's the solution? The solution is actually very simple. We need to tell the compiler that specific methods will not modify the object. And all we have to do is put the const modifier before the semicolon in the method prototype. That's it. Now the compiler will not only allow this method to be called on const objects, it will also produce a compiler error if you try to modify any of the object attributes in the method. The idea of class methods having const qualifiers is part of what's referred to as const correctness. Const correctness can get pretty complicated, but this video serves to give you a basic idea of what it is and how important it is. Now you can see that the call to getName works just fine, but the call to setName is still not allowed, since setName is not a const function. Remember, since you're telling the compiler that getName is a const member function, then if you write code in the body of getName that modifies the object, you'll get a compiler error. That's const correctness in action. Let's go to the IDE and see this example in code. Okay, so I'm in the IDE. I'm in the section 13 workspace in the const in classes project. And this is basically the player class. Again, you can see we've got our private attributes, some public methods, and so forth. And this is the real method that we're interested in this example right here. It's a simple getter that returns the name. So you can see getName is the name of the method. It returns name, which is a string. Simple as that. That's the one we're going to have to fix so that we achieve const correctness with this program. So let me go down to, and you can see I've got constructor, copy constructor, all the normal stuff. I'm going to comment this function out because we're going to use that one in a minute. But this is what I've got so far. I've created a villain object that is a player type, and it's constant. I've also created a hero, which is a player type. Hero is not constant. So what does this mean? This means that I cannot change any of villain's attributes. So here's a real simple way to tell that this actually works. If I take that XP attribute that's private and just make it public for a minute, and then I come down here again, and I'm just going to say something really simple like villain.xp is 1,000. It should let me do that, right? Because XP is public, but it won't because villain is constant. So if I try to compile this, I'll get an error right here. It says assignment of member player XP in a read-only object. It makes a lot of sense. That's actually a really good compiler error. It's telling you that that object villain is read-only. You can't change any of it, right? That's what that const right there does. So let me undo what I just did here, and I'll make XP private again. Okay, so let's do a couple of things now. Let's come down again to our main here, and I'll remove that line right here. So we're right back to where we started. We've got the villain, and we've got the hero. Now, obviously, I should never be allowed to change villain, right? So doing something like villain.setName to supervillain, that should never be allowed, because if you look at the setName method right up here, it is actually changing that name attribute. So if you try to compile this, you would expect an error, and you do get an error. And the error message is saying passing const player, that's what this is right here, villain, as this argument discards qualifier. So what it's telling you is that you're passing this in as a constant, but the class is not expecting a constant, and it's going to be able to change it. Now you'd get the same error if you called the getName function. So let's try that on villain. You may not, this one may not seem so obvious as to why, but let's say we did something like that. I'll just put that in an output statement. So we'll say something like cout. There we go. Something like that. I'll comment this one out because we know that one should never work, right? Ever. No, even once we're const correct, that should never be allowed. But now we're here. So I'm saying, villain, get me your name. That should work when you really think about it, right? Because it's not changing the object. It's simply returning that string and display it. But it won't work. It's going to give you an error. And the error is, again, same error. Passing const player as this argument discards qualifier. So what's going on? Well, that getName method could change the object, right? There's no reason I couldn't write some code in the get method right here that changed one of those attributes. And the compiler can't guarantee that at this point, so it's going to throw the error. The fix will come up in a little bit, but now what if I did something like this? What if I did the same output statement, but I did it with hero instead of villain? Let's compile that. There you go. You get a clean run, right? That makes sense because hero is not const. So the compiler doesn't really care if you change hero in that method or not. Okay, so we'll make all this const correct in a little bit. So there you can see some of the issues here. Now, suppose that I'm going to comment all this out and then I'll uncomment it in a little bit. But now suppose we have this function right here. And this is not a member function. It's just a regular function. It's called display player name. And it expects P, which is a reference to a const player object, right? And all we're doing is getting that player object's name and displaying it. So let's call that method. So we'll call display player name and we'll pass in villain. And what we'd expect it is to print out villain, right? So let's compile that. We get an error. Error passing const player as this argument discards qualifier. It's like the problem's right here, right there. And okay, you know, we can sort of understand that error. But now let's try this with hero. And we'll just replace villain with hero here. And I'll comment this line out so we're definitely sure what's causing any errors if we get any. So look what's happening here. Hero is not a const, right? So I'm going to pass hero into display player as a const. That means this function can't change it, right? That's the problem. When I call p.getName, as far as p.getName is concerned, that's a const. It can't change it, right? But there's no way to guarantee that. So this is going to give me the same error as before. There's the error again. Okay, so what's the fix? Well, the fix is pretty simple. The fix is we come up here to our class and we come to that method getName. And we want to tell the compiler, hey, compiler, I guarantee, and you double check for me, that this method getName is not modifying the object at all. And you do that with the const qualifier right there. You put a const right after the parameter list. If you've just got a prototype, you just put it like right before the prototype, right in there before the semicolon. That's it. Now you've just told the compiler, I guarantee that I'm not changing that object in this method. So now the compiler's happy and all of this stuff will work now, right? Let's uncomment all of these out. And I'll uncomment this guy out as well, because that should work as well. And that's it. So now if we run this, we should get a clean run. Villain, hero, just what we expect. Okay. Obviously, this will never work, right? That should never work because we don't want to set anything in villain. That should never be allowed. So I'll just leave that commented out. And then the other thing that's important to understand is once you define a method here as const, you can't mess around with those attributes in here. I can't say xp equals 100, right? Because now you're just violating what you just said you were going to do. It's no longer const. So if I compile, I'm going to get an error right there on that line, right? You're changing something in a read-only object. So this is const correctness. It can get pretty complicated when you're passing things all over the place as const here, non-const here, and so forth. But the rule of thumb is all your getters should be const. Basically, any method that you have in your class that doesn't modify the object should be const. Okay, so that's it for the const correctness. In this video, we'll learn about static class members and how to use them in C++. In a C++ class, we can have both static data and function members. When we declare class data members as static, we're telling the C++ compiler that these data members belong to the class, not to any specific object. So they're extremely useful to create class-wide information. For example, suppose we wanted to know how many player objects we have active in our application at any point in time. We could create a global variable and then increment it and decrement it in the code whenever we create an object or delete an object. This is really hard to do though, since we really can't be sure when constructors are called and when destructors are being called. So a better solution is to create a static variable that's part of the player class, and then we can manipulate that variable directly within the player class. And then whenever we need to know how many player objects there are, we can simply ask the player class. We don't even need any objects. In fact, if the player count is 0, this means that there are no active player objects at all. So how could we modify our player class to support this? Let's start with the player class. We'll create a player.h file with the class specification and a player cpp file with the class definition. Now we need to add a static data member to the class. We can do this very easily by adding a private static int named numplayers. We'll initialize this to 0 a little bit later since we can't initialize it right here. We also would need to declare a static class function that returns an integer. It will return the static integer we just declared, and you can see that at the bottom. It's called getNumPlayers. Now let's head over to player.cpp. This is where we want to initialize the static integer numplayers to 0. Notice that the syntax might look a little strange. This is where you define that variable and assign it to 0 in this case. This must happen exactly once, and it typically happens in the .cpp file for the class. Finally, we implement the static function getNumPlayers. Since this function is static, it only has access to static data members. It does not have access to non-static class data members. So in this function, we simply return numplayers. Pretty easy. There's only one part left to do. We need to increment and decrement the number of players whenever we create and destroy objects. The best place to increment the player count is in the constructor. In this case, we simply increment numplayers by 1. Be careful though if you have many overloaded constructors, since you might have to increment numplayers in more than one place. Basically, anywhere you create an object. We only have one constructor in the player class, and we're delegating to it from our copy constructor, so this is the only place we want to increment numplayers in this example. Our original player class didn't have a destructor. It used the compiler-provided default destructor, since it was all we needed. However, now we need to define our own destructor and decrement the number of players count when the object is destroyed. That's it. We're all set. Now we can use our player class and simply call player getNumPlayers, and it will return the number of active player objects. I created a simple helper function named displayActivePlayers, and anytime I need to display the number of active players, I simply call it. Now look at the main. The first statement is displayActivePlayers, and it will display 0. As we add and remove player objects, we'll call displayActivePlayers, and it will display the current number of active player objects. Let's head over to the IDE, and we'll take the existing player class through the process of providing this behavior. Okay, so I'm in the IDE, and I'm in the Section 13 workspace in the Static Class Members project. And what I've done is I've created a basic player class, and you can see here I've got 3 files, player.h, player.cpp, and main.cpp. And right now we're looking at player.h. You can see we've got our include guard here. We're included string because we're using strings inside the player class. And it's a basic player class that we've been using all along. It's got the string name, the integer health, the integer XP, and we've got a getter here and some constructor that uses default parameters, a copy constructor, and a destructor that does nothing right now. And the CPP file implements the constructor, the copy constructor, and it's got an empty destructor right now. So what we want to do is we want to go to the player.h file. And what we want to do, as I said in the previous slides, is to know how many players are active at any time. So we need a counter type variable. We can't add that to objects because each object would have their own copy. So we want to use static variable at the class level so that we now have a variable that applies to the entire class. So we'll define that right here. We'll make it private, and we'll just say static int, and we'll call it numplayers. Simple as that. Now, you'd think that you could initialize it right here, but if you try that and try to compile, you'll get a compiler error that says that C++ forbids in-class initialization of non-constant members. And you can't do that. So we'll get rid of that and we'll initialize it in a second in the CPP file. So that's my static variable that, remember now, this does not belong to any object. This belongs to the class. And then we need to implement a static class function, and we'll do that down here. And we'll just say, I call it static. It's going to return an int, and it's going to be called get numplayers. Simple as that. Now, one thing to remember, because this function is static, it only has access to static variables. That makes sense. It doesn't have access to any object variables. Any of these guys, name, health, XP, those belong to specific objects. Static only belongs to the class. So this is a class function, and it only has access to that static numplayers in this example. Okay, we could have a lot of other static functions if we like, but we only need the one in this example. So that takes care of the header file. I'll save that, and now we'll go over to the .cpp file. Now this first thing we want to do is we want to initialize that static variable here. And the syntax looks something like this: int the class name and the name of the variable, numplayers, and here we can initialize it to 0. And now you can see that if I compile and run, now I get a clean run from that. So that's initialized. It only happens once, and the best place to do that is in the CPP file for the class that you're defining. Okay, and then the last thing we'll do is, well, not the last thing, but the next thing we'll do is we'll implement the int player get numplayers function. And it's, let me do that again, get numplayers. It's that function right here. And we're going to implement that function so that it returns the number of players. It has access to that. It's a static variable. And that's really all we care about. Now, remember, we already defined that as a static method right here in player H. You can see it's right here. So we don't have to say static again down here. That's it. Now, what do we need to do? Well, we need to increment and decrement the number of players depending on when we construct or destruct things. So this is the only constructor I have. Even when we've got a copy constructor that we create a copy of an object, we're still delegating to player. So right here, I want to increment the number of players. And in the destructor, I want to decrement the number of players. So that will take care of the semantics that I want. So at that point, this CPP class is done, and we can now head over to the main class and test some of this. So the first thing we'll do in the main class is we'll write a real simple function, and we'll just keep calling that function whenever we want to display active players. It'll just save us a lot of typing. So we'll call it void display active players. It doesn't expect anything. And all we're going to do in here is we're just going to do an output statement, and we'll say something like active players, colon. And so now, how do I know how many active players there are? I don't have any objects to call. That's the whole point. I can simply say player, and we need a scope resolution operator, and now we can call the static method, get numplayers, right here. That's going to return the integer that represents that static data member that we had in the class. And we'll just supply an end line here. Okay, so now let's go to main and let's call that method. Let's just call display active players. All right, we'll put a breakpoint in here so that we can walk through this, and let's run this. And we have an error, display active players. I can't find it. Players, I spelled it wrong. Let me put an S up here, and now we should be good to go. So let's step through it through the debugger, and I'll move this output window here over to the right again. And so what do we expect here? Well, we're going to call display active players, and display active players is simply going to ask the player class to get the number of players. At this point, we have none. There's no way we could have done this if we had an object, right? Because there are no objects. So in this case, we're calling player and asking the player class to give us the number of players. And we expect this to display 0. When we walk through it, we get active players 0. just exactly what we expect. Now let's create an object, and let's create a player, and we'll just call it hero, and we'll give it the name hero, and we'll default everything else. And then we'll call display active players again. So at this point, we have one active player. So let's debug this. We'll step through it again. And right now, again, we're displaying active players. We're going to get back a 0. I'm going to create my player object. It exists. You can see it right here. So we expect that we've got the number of players is 1. And if you look right here in your local variables pane, you can see that we've got that num players static variable right here. And we have access to it here, so it's nice because you can actually see it. So at this point, we run it, we get back the 1, which is exactly what we expect since we do have one object. Okay, so now let's do another example here. Let's create a local block here, and we'll create another player, and we'll call that player Frank. And again, we'll default it to Frank. And then we'll display active players right in here. And then we'll display it again when we leave the block. Now, what we expect to happen here is we expect that this Frank object will be created in this local block. We'll display now, we'll have 2 objects, right? We'll display 2 objects. Then it's going to go out of scope and be destroyed. So when we get back to here, it's going to display 1 less again. So let's do that one more time. We'll run through the debugger, and we'll step through this one line at a time. Here we go, display active players. We expect, I'll expand this here. We expect it to display 0, which it does. I just created the hero, and I want to display the active players. I have 1. Now I'm here, I'm creating Frank, and I'm displaying active players. I've got 2, and obviously I can refresh over here, and I can see in both places that I've got 2 players. That's that static data member right there. Okay. Now we expect Frank to go out of scope, so the destructor will be called. Right, it just got called, so if we refresh now, we've got hero, and we're back down to 1, and we display back down to 1. Eventually, we'll destroy hero again as well, and we'll get down to 0. Now, let's do just one more little piece of code here, and what we'll do is we'll do it right here at the bottom. Again, we'll say player. We'll create an enemy, which is a pointer to a player, and we'll create a new enemy. And we'll just call him enemy and make him pretty strong. Okay. And right now what we'll do is we'll display active players. And then we'll delete enemy. And we'll display the active players one more time. Okay, so let's walk through this one last time. And you can see how useful using these static data members is. So I'm displaying active players. I get back a 0. I create player. I display active players again. I get back a 1, which is what I expect. I create Frank. So that gives me 2 objects. And when I display them, I get the 2. Frank just got destroyed. So I'm going to display 1 again. Now here, I'm going to create that enemy object on the heap since it's a dynamic allocation. And I display active. I've got 2 again. I'm going to delete enemy. I'm back down to 1. And at this point, the hero will be deleted and I'll go back to 0. Okay, so there you go. There's a real simple example that's using the multiple files here to declare some static data members, a static class function. And we've got a pretty useful little technique that's used a lot. Sometimes you really need to know how many of your objects are out there, and this is a really easy way to do it. In this video, we'll discuss another way to create objects in C++ using a struct or structure. The struct comes from the C programming language. In C, we create structs as a container for data, much like a record in many other programming languages. C++ also supports structs since it has to be compatible with C. However, it adds the ability to treat structs very much like classes. Everything you can do with classes, you can do with structs. The only difference is that the members of the structs are public by default, whereas the members of a class are private by default. Here's a simple class declaration for a person class. It has a string attribute called name and a method called getName that returns that name. By default, class members are private. So if we create a P object that's a person and try to access name or call getName, the compiler will give us a compiler error saying that we don't have access to those private elements. Now let's see the same as a struct. Here we have person declared as a struct. We have the same attribute and the same member method. But now when we create the person object P and try to access its attribute or member function, the compiler is okay with it. That's because the default access for a struct is public. That's it. That's the only difference between structs and classes in C++. But there's a few general guidelines that you can use to determine if you need a struct or a class. It would be appropriate to use a struct when you have passive data. So the struct would act very much like a struct in C. It simply holds data and that data is public. And since the data is passive, you really don't need to create any methods in the struct. As for a class, we've already seen many examples. If your objects are active or they have complex behavior, then you should use a class and implement getters and setters and member methods as needed. These guidelines are very general, but remember, other C++ programmers will likely be modifying and extending your code, so don't use C++ in a way that's very different from what C++ programmers expect. For example, don't use a struct and then make everything private in the struct so it behaves like a class. Just use a class instead. In this video, we'll learn about friends of a class in C++. Friends have always been a controversial topic in C++. The controversy is about encapsulation and whether friends violate encapsulation or enhance it. You can decide where you are on this issue, but friends are indeed part of the C++ language and it's important to understand them. So what is a friend of a class? A friend of a class is a function or another class that has access to private class members. And that other function or class is not a member of the class that it's accessing. In the case of friend functions, these can be standalone functions or member methods of another class. And in the case of another class, the entire class will have access to the private information of the class granting friendship. So as you can see, friends have unfettered access to both public and private data members of a class, but they're not members of the class. It's important to understand how C++ treats friendship in the big picture. First, friendship must be granted, not taken. A class must explicitly declare its friends in its class declaration using the friend keyword. Friendship is not symmetric, so if A is a friend of B, that doesn't mean that B is a friend of A. This must be explicitly granted. Friendship is not transitive. If A is a friend of B and B is a friend of C, then A is not a friend of C, again, unless specifically granted. And finally, friendship is not inherited. So what does declaring a friend look like in C++? Here you can see the case of declaring a standalone non-member function as a friend of the player class. Notice that the player class grants the friendship by declaring the function prototype preceded by the friend keyword. That's it. Now the displayPlayer function has access to everything in the player class. So in the displayPlayer function, we don't have to go through public getters or setters to display the player information or set player information. We can directly access the private class attribute. In fact, we can change them as well if we wanted to, since the object is passed by reference and in this case non-const. Let's see how we would declare a method in another class as a friend. In this case, we're declaring the displayPlayer method of the other class as a friend. That method will now have access to everything in the player class. And that method might be implemented as follows. Notice that it is indeed a member of the other class, but you can use the player class's private attributes directly within it. Finally, we can declare an entire separate class as a friend. In this case, we declare the class other class as a friend of player. So all the methods in the other class will have access to the player class's private attributes. As you can see, friendship is very powerful. It can bypass function call overhead associated with getters and setters and other class methods and allow direct access to private attributes. Sometimes we have classes that use other classes, and writing code using getters and setters becomes long, tedious, and sometimes gives you overhead. However, that shouldn't be the only reason for granting friendship. Friendship should be granted only when it makes sense in the design of your system and then only the minimal necessary friendships should be granted. We'll see friend functions again when we use operator overloading in the next section. Hello everyone, welcome to the Section 13 challenge. Congratulations on finishing up this section. This section was long, it had a lot of information, some of it pretty easy, some of it not so easy. So now we're at the challenge, and what we want to do here is we want to apply some of the things that we've learned. Obviously, we're not going to do everything that we've learned in one challenge project. That would make it a very complex project, but we want to model some objects. We want to model other objects in terms of those objects, and we want to be able to call methods and break up our program into separate files so that we can manage it easily. So let's talk about the challenge. For this challenge, we're going to develop the foundation for a program for movie fanatics. And what we want to do is they want to keep track of the movies they've watched and how many times they've watched each movie. So the program has to support the following. We're going to have a class called movie. Now this models a single movie, which includes the movie's name, the movie's rating, and how many times we've watched the movie. Of course, we can add fields to this like the rating, your rating for the movie. So like 1, 2, 3, 4, 5, depending on how much you like it. Also a note, maybe a little comment area that you could type information about the movie, all kinds of information, maybe who the leading star of the movie is and so forth. You get the idea. But at a minimum, this is what we're going to do. Just the movie's name, the movie's rating, which would be G, PG, PG-13 or R, and how many times you've watched the movie. We're also going to model a collection of movies. And that's what the movies class does. Now notice this is plural because it's modeling a collection of movie objects. We're going to model it with a vector. Now, obviously, the movies class needs to know about the movie since it is a collection of movie objects. However, our main driver should only interact with the movies class. So it's going to create a movies object and work with that. Okay, so here's a simple example of what main could do. So we're going to create a movies object. Then I'm going to ask that movies object to add a movie by providing the movie's name, the rating, and the watch count. I could ask the movies object to increment the watch count for a specific movie given its name. And I could also ask the movies object to display all the movies that it has. Now, obviously, the movies class has a bunch of movies in it. So in that case, it could just ask each movie, hey, display yourself, display yourself, display yourself. And that's kind of what we're going to do. Now, additionally, we need to have a little bit of logic here so that we don't have duplicate movies. So if we try to add a movie whose name is already in the movies collection, we should display an error to the user. And if we try to increment the watched count for a movie whose name is not in the movies collection, we should also display an error to the user. I've created a basic shell, and that basic shell is right here in the Section 13 challenge project. Movie and main have been fully implemented for you with comments. Movies has not. So the idea here is that you would go into the movies.cpp and the movies.h, and I'll talk about the structure in a second, and implement those. Now, the shell is there, so the stubs are all there. Just look for the places where I write, you implement this. The other option is don't use any of my stuff. Do it yourself. Just go based on this description as well as the main, because the main gives you a little bit of insight into the structure. And then implement movie CPP, movies CPP, the H files, all that stuff yourself. Depending on how comfortable you feel with C++ right now. If you're a beginner, just start out with the shell that I'm giving you. If you feel more comfortable and you're a little bit more advanced, then just try it on your own. Okay, so how are we going to structure our project? Well, we're going to have different files. We want to be able to separate our files. So this is what it's going to look like. We're going to have movie.h. That's an include file that has the specification for a movie class. And again, remember, a movie is a model of a single movie. Then we've got movie.cpp, which is our implementation. Just like we've seen before, I've got movies.h, which is our include file for the movies class specification. And then movies.cpp is the implementation. And then finally, I have a main CPP that just has the main driver that creates the movies object and adds movies to it, increments counts, and displays. Okay, so again, this program might sound simple. It's not trivial for sure. It's definitely not trivial if you try to do it 100% on your own. But it's a fun project to do, and it'll really help you with the coding. Now, what I want to do is I want to show you the main, and I've included the main down here in the description, but I'm going to show it to you in the source code. It's the same thing. And I'm going to show you the main for the challenge solution here. So I'm going to double click on that main CPP file. And you can see that there's two helper functions that I've already written, and they're the function prototypes here. And the reason I wrote those is because when I ask the movies object to add a movie, and that movie's already there, I need to display an error message, right? So I have all that if-else logic. So if the movie's not there, add it. If it is, give me an error message, that kind of thing. So I wanted to wrap that up in a helper function so that my main looks really nice like this, just add movie, rather than have all that if-else print out logic all in the main, which kind of gets really ugly and hard to follow. So, but let's walk through this really quickly here. Here's my main, and I'm going to create a movies object. That's the collection. And then I'm going to ask that movies object to display its movies. Obviously, there are no movies in there now, so it should display something like no movies, or you have no movies yet, or something meaningful. Then what I want to do is I want to call add movie. Now, add movie is this helper function that I created right here, and you can see the comment right here. So I'm going to call add movie. I'm going to pass in my movies, right, as a reference. I'm going to pass in the information for the movie. So in this case, I want to add big, which is the movie's name, PG-13, and I've watched it twice. At that point, this function here gets called, and notice what it's doing. It's asking the movies object to add the movie. Okay, so at this point, it's really delegating that behavior to the movies object. And again, the only reason this function is here, right here, is to help us with that error checking so we don't clutter up all the main code. That's it. Now we're going to add another movie, Star Wars, and I'm going to add a third movie, Cinderella. So if I run this at this point, this is what I've got. You can see, I'll move this over so we can kind of line them up. Here's my movies, and I'm going to say display the movies. And it's going to say, sorry, no movies to display. Now I'm going to add a movie, and add a movie. And this is going to say big added, Star Wars added, Cinderella added. And that message is coming right from here. Okay? So now I want to display the movies. So what I can do is I'll just comment this line out. We'll take it one step at a time. That way you'll really understand what's going on. So I'm going to ask the my movies objects to display itself. Well, it's going to loop through its collection and print out all the movie objects that it has. So in this case, we've added big, Star Wars, and Cinderella. So that's what I expect to print out. So let's run this. And here you see again that we added big, Star Wars, and Cinderella like before. Now when we call the display method of the My Movies class, this is what I'm going to get. Big, Star Wars, and Cinderella. So it's going to print out those three movies. Okay, so it's really simple as that. And let's just add a couple of more here and display those two. Now, this is a little bit different now because I'm adding my movie and I'm adding Cinderella. Well, I've already added Cinderella. So I expect this to tell me, sorry, it already exists. Then I want to add Ice Age, which should be okay. And then I want to print those out again. I should only see Cinderella once, right? If I see Cinderella twice, then there's something wrong with my code. So let's run this. And you can see here, big added, Star Wars added, Cinderella added, just like we did before. We're displaying those three movies. Now Cinderella already exists, so we didn't add it again. We did add Ice Age, and then when we display all four of the movies now, that's what we expect. We don't expect to see Cinderella twice. Okay? So, a couple more things. We can obviously, when we watch a movie again, and this doesn't store this information on disk or on file or anything. We'll get to all that stuff later. But right now, it's just keeping it all in memory. So in this case, I'm going to say increment watched my movie. So what I'm saying here is I want to increment the watch count for big. And I want to increment the watch count for Ice Age. Now, if you remember, the watch count for big is 2. And for Ice Age was 12. So now when I display my movies, I would expect to see 3 and 13, right? So let's try that out. So big was 2, Ice Age was 12. Now big is 3, Ice Age is 13. Just like what we expect. And now the last test case here, and this is by no means a lot of test cases, but it's enough to get you started. Now what I want to do is I want to increment the number of times that I've watched this movie called XXX. And that could be anything, as long as it's not in the collection. Obviously, it's not in the collection, so I can't increment it, right? It makes no sense. So I would expect some sort of error message there. So let's run this one last time. And what we get is that last statement, XXX not found. So obviously there's no movie called XXX, so I could not have incremented the watch count for it. Okay, so that's a simple run. You get the idea. Notice there's no user menu where you can say select 1 to add a movie, select 2 to delete a movie. We could certainly add that later, but we need to get this part working first. So now let's take a look at the movie H file, which is our header. And there it is right here. This models a movie with the following attributes. And you can see I've already implemented this. I've got a name, a rating, and a watch, which are strings and integers. I've got a constructor that expects all 3 of those attributes. I've got a copy constructor it's really just empty. I've got a destructor, again, that's empty, that we're not using any raw pointers, so we really don't need these. And then I've implemented the basic getters and setters, set name, get name, and so forth. Notice that these are const correct. So my get names are all const. My get functions, I should say, are all const, as well as my display. So I don't want my display modifying anything, so I'm going to make that a const method. Okay, that's it. Now let's look at movie CPP, which is the implementation. And you can see here I'm implementing the constructor as an initializer list. Here's my copy constructor, which is simply delegating to the constructor. I could have simply used the default that I get for free from the compiler, but I decided to implement it explicitly. So again, just to get a little bit more practice. My destructor is here. It doesn't do anything. And here's the display method. The display method just displays the name, the rating, and the watched for each one of those objects. That's it. Now let's take a look at movies.h. Here's the specification for my movies class. And again, movies is a collection of movie objects. And there's my vector. I have a constructor. I have a destructor. I have the add movie method, which you have to implement. And I have the increment watched method, which you have to implement, as well as a display method. So if we look at the CPP files, those are all in there. Right? I've got no code in my constructor right now, a default constructor. I've got no code in my destructor. And there's my add movie. Right now, it's just returning false. You need to implement the logic in this method. And here's my increment watched, which again returns false. And then finally, we have the display method, which displays those objects. Now, obviously, all you want to do here is just loop through that collection and display each movie object. And remember, each movie knows how to display itself. So just call that movie objects.display method. Okay, so a lot here. Take your time, try to understand the logic. If you have any questions, let me know. And good luck with this. When you're done, check out the challenge solution. Obviously, if you're doing this from scratch, my solution is going to be different from yours, but good luck with it, and most of all, have fun. Hello, everyone. Welcome back to the challenge solution for section 13. If you look through the project, that you really found what we had to implement was basically 3 methods in the movies.cpp file. And if you look at your movies H file, you can basically see what's going on here. We have an add movie method that expects the movie name, movie rating, and the number of times watched. And I want to add that movie to this vector right here, this collection of movies. But I have 2 strings and an integer. I don't have a movie object. So obviously we need to create a movie object. But we only create that movie object and add it if the movie isn't in there already. Okay, and we're deciding that by the name. So that's one thing we've got to do. The other thing we need to do is implement this increment watched. And it's very similar. The user is passing in the name of the movie that they want the watch number incremented by 1. So what do? We search through that vector again right here. And if we find that movie by name, then we increment its count. Otherwise, we return false. And we do that here as well. So if we add the movie, if that was successful, we're returning true. Otherwise, we're returning false. Same here. If we increment the watch count, we're returning true. Otherwise, we're returning false. We couldn't do it because the movie wasn't there. And then the last method we'll implement is this display method, which just basically loops through that vector and prints out all the movie objects. Okay, so why don't we get started? Let's head over to the movies CPP file. That's where we're going to implement these methods. Now you'll notice we have a default constructor. We have a destructor. We don't have a copy constructor. We don't really have anything going on like that. Again, if you look at your movies file, we don't have any raw pointers here. So we're fine with the default behavior of the copy constructor, so we don't have to implement it. Okay, so again, let's go back to movie CPP. We don't really need to implement a destructor since there's nothing to destroy. Unless you want to put output statements in here so that you can see them happening, then you would certainly implement them that way. So let's start with this add movie. Right now it's just returning false, and increment watched also is returning false. And this will actually run right now. If you run this project, that's kind of what you get. Pretty meaningless, but it all works, it all compiles. So that's the next step, is trying to get the functionality right. So let's start with add movie. So we're right here. I'm going to get rid of that return statement. And let's start coding this method right here. So what do we want to do? Well, we want to loop over that collection movies. And for every object in there, remember every object will be a movie object. We want to get the name for that movie object and compare it to this name right here. Okay? And if we find the name in there, that means that that movie's already in there. We don't want to add it again. So we'll return false. Otherwise, we'll add the movie. Okay, so let's take this one step at a time. Let's just use a range-based for loop to do this. And we'll start here. We'll say for. And we'll modify this a little bit as we go. Movie. That's each item in the collection. And we're going to loop over movies. So there's my range-based for loop. Now, we can check for each movie that we're going through. We can get the name for the movie. And if the name of the movie that we're iterating through at each step is equal to the name that's being passed in, that's that guy right here, then what happened? Well, then we found a movie that's in there where there's no sense in adding it again. We just want to return false, and we're out of here right now. We could certainly have some if else logic and so forth, but why bother? At this point, remember, if it's the first one, we're out. If it's the last one, we're out. But in any case, if we find a movie that has the same name as the one we're trying to add, we're going to return false. At this point, I've looped through the entire collection and I have not found the movie. So now what I want to do is add the movie. Well, in order to add the movie, I need to create a movie object to add. So we'll create movie. We can just call it temp or anything we'd like. And we'll construct it given the name, the rating, and the watched. Now we've got an object. We can simply add it to the movies vector. We can push back, and we can push back temp. And at this point, we want to return true, right? Because we were able to add that movie. That's it. Now, there's a couple little things we can do here to make this a little better. First of all, this loop right here that's looping through that collection or iterating through that collection, it's not going to modify the collection. And I want to be sure that it doesn't modify the collection. This will do that, right? Because these are all returned by copy. But it's not very efficient. So what I'd rather do is change this to so that this is a reference right here. But if I just leave it as a reference, then this could potentially change it. So I really want to make this a const. So I want this to be a reference to a const movie at each iteration. So if I try to change it by accident or by mistake or even intentionally, if I tried to change that movie in here, I'm going to get a compiler error. Okay, so that's basically done. Now let's take a look at the increment watched. Again, I'll get rid of the return value since we'll do it from scratch. And what we'll do here is, again, we want to loop through. So this is a little different though, because I want to loop through until I find it, right? And then when I find it, I want to update it. So it's a little different logic than we just had before, but it's the same idea. So let's say for movie, and we could use auto here if we wanted. And I want a reference to each one of those movie objects, because if I find the one that matches, I need to change it, right? So it can't be a const, it needs to be a reference. So I'm looping through, and I forgot that bit movies right here. There we go. So now we've got a range-based for loop. We're looping through movies, and at each iteration, we have a movie, and it's a reference, so we can change it, okay? So what are we doing here? Well, we check to see if the name of the movie is the name that I want to change. So in here, I'm simply going to say if that movie's name, if that movie object's name is equal to the name that was just passed into me, then at this point, I've got the one that I want to update, right? So I can simply call movie, which is the object, and increment watched. That's a method in the movie class. And I want to return true because it was successful. And I'm out. Now at this point down here, what happened was I looped through the entire vector and I did not find any movie with that name. So at this point right here, I simply want to return false, right? Because I'm done. I wasn't able to increment anything because it wasn't there. So that should take care of that. And then the last method that we're going to implement is this display method. So what do we need to do here? Well, let's first check to see if there are any movies at all, right? And notice this is a const method, so that's real important, right? We can't modify that movies object in here. So I'm going to say if my movies dot size, that's the vector size, how many items are in there. If that is equal to 0, then I really have nothing to display. So I'll just say something like, let's output something like, let's say, sorry. I think that's what I had before. Sorry, no movies to display. And we'll put a new line in there, and we'll put an end line in there as well. Okay, so we've just taken care of the case where there are no movies. Now the other case is there are movies. So in this case, what I need to do is basically loop through that movies vector again. And every time I see a movie object, tell it to display itself. It knows how to display itself. So let me just put in one of these lines just so I don't have to keep typing so much. So we've got a header line here, and we'll put another one here, and we'll put everything else in between. That way we've got a nice little separation. So what do I want to do in here? Well, I want to say for my movie, and I could say auto here as well. It's going to figure out what it is. For auto movie, that's my variable name in my movies collection. So every time I see one of these guys, what do I want to do? Well, I want to tell the movie to display itself. It's really that simple. So we're done with this. We've got our logic set up. Now let's compile and see if we've got any compiler errors. We've got a compiler error right here because I forgot my standard namespace. And let's try that one more time. That's it. We're done. Everything's working as expected. Sorry, no movies to display. We add those 3 items. We display the 3 movies. Cinderella already exists. We add Ice Age. Now we display the 4. We don't display Cinderella twice. And we increment Big and Ice Age. So we've got 3 and 13. It was 2 and 12. And then finally, we can't increment that XXX movie because there is no such thing. Okay, so that really is about it. You could add an interface to this. You can add some more attributes to this to extend it and practice some more. What I would suggest you do is go to your movies.h file right here and make this one change. Make that movies not a movie object, but a pointer. So now this movies contains a pointer to a vector. And now you've really got to think about what you're doing, because now we need copy constructors that are doing deep copies, and we need move constructors, and we need to be a little bit more careful and more efficient. So I'll leave this as an exercise to you, but I encourage you to do this. All right. Hope you had fun doing this project. Hey everybody, I'm back. I just realized that when I wrote this line of code here on line 76, I was trying to show you that you could use auto here, but I was a little quick on the gun. We have to be a little bit more careful than just this, because this is just going to create an object by copy, and it's going to be inefficient. So what we really want to do is we want to replace it with const. We can still use auto, but we want to make sure it's a reference to a constant object. And in this case, the auto makes it a movie, right? So we've got, this is equivalent to typing this. And if we do this with auto, I'll save, and we'll build and run. And we've got the same output as before, but a little bit more efficient. In this section of the course, we'll learn about overloading operators in C++. C++ allows the programmer to overload most operators to work with user-defined classes. This is intended to make code more readable and writable by allowing the use of familiar operators in a familiar manner, but with our own classes and objects. First, we'll look at exactly what operator overloading is and some of the basic rules that C++ enforces. We'll start with the assignment operator. The assignment operator is a very important operator in C++. It defines the semantics of what happens when you assign one object to another. C++ provides a default way of doing object assignment, much as it did with the copy constructor that we learned about in the last section. However, many times we want to be in control of what happens during object assignment, and we can overload the assignment operator to do exactly that. For example, when we use raw pointers in our classes, we must provide our own version of the assignment operator. Additionally, we can override the assignment operator to handle both copy and move semantics, as we did with the copy and move constructors in the last section. We'll learn how to do that in this section. We'll also see how we can overload other operators as both member functions and as global functions, and why you would want to choose one over the other. We'll finish up this section by overloading the stream insertion and extraction operators so that we can easily use our objects with C++ streams, just like we've been doing with the built-in types. So let's get started with operator overloading. Before we get into declaring and defining overloaded operators for our own classes, let's understand what they are. We've already seen what operators are and how to use them. We have traditional operators with traditional meanings. These include the plus symbol for addition, the equal sign for assignment, and many more. The C++ operators are defined to work with the primitive or built-in C++ types, such as integer, doubles, longs, and so forth. In fact, we've already seen that the C++ operators are overloaded to work with different types. For example, the plus symbol can add 2 integers, 2 doubles, an integer and a double, and so forth. C++ allows us to overload operators for our own user-defined types. This allows our types to behave and feel similar to the built-in types. When we overload operators, it can make our code more readable and more writable. The only operator that the compiler provides a default implementation for is the assignment operator, the single equal sign. That's because the compiler must be able to assign one object to another. All the other operators that can be overloaded must be explicitly defined by the programmer. So, what does operator overloading look like from the perspective of using the objects? Well, first, let's see how we would write code if we were not overloading operators. Suppose we've implemented our own class named number, and that class can model any kind of number, an integer, a double, a complex number, an irrational number, you name it. If we want to be able to manipulate number objects so that we can add them, subtract them, multiply them, and so forth, we could implement non-member functions or member functions to achieve what we want. So if we wanted to add a and b, then multiply that result by the quotient of c divided by d, our code might look like the first statement. If we wanted to use member methods, then we need objects and method names, so our code might look like the second statement. Are these statements very unreadable and very difficult to write? Maybe. It depends on your perspective, but the point is that we're adding, dividing, and multiplying, and we've been using these operators to do that since we were little kids in school. Why can't we use them now? Of course, the answer is that C++ doesn't know what to do with our user-defined types. In most cases, it makes no sense to add or multiply or subtract your objects. For example, what does it mean to subtract 2 player objects in a game, or multiply 2 account objects? It's totally dependent on what you want to do. In many cases, it doesn't make sense to overload certain operators for your classes. In those cases, don't do it. Only do it if it makes sense. In this example, I would argue that it does make sense since the users of the number class would know the meaning and how to use those operators we would overload. Let's see what our calculation would look like if we overloaded the addition, multiplication, and division operators. Here you can see that our user-defined number class now looks and feels and behaves like the built-in C++ types. Operator overloading is syntactic sugar. Behind the scenes, we're still calling methods or functions. We'll see how it all works in the next video. So, what operators can be overloaded? Well, C++ allows you to overload most of its operators. There are a few exceptions and they're listed in the table. We can't overload the scope resolution operator, the conditional operator, the pointer to member operator, the dot operator, and the size of operator. Remember, just because an operator can be overloaded doesn't mean you should. Don't overload it unless it makes sense and makes your code more usable, more readable, and more writable. So, as always, there are some basic rules that must be followed when you're overloading operators. First, the precedence and associativity of the operator that you're overloading cannot be changed. This makes perfect sense since C++ programmers are already familiar with the precedence and associativity of its operators. The arity of an operator cannot be changed. So if an operator is a binary operator, which means that it's applied to 2 arguments, then this can't be changed. C++ does not allow you to change the way that the current operators work with the built-in types. C++ doesn't allow you to create new operators that are not currently used by C++. And finally, C++ allows you to overload operators using global functions or member methods. However, there are several operators that must be implemented as member methods, as you can see. Notice that the assignment operator must be implemented as a member method. Let's wrap up this video by looking at some examples where operator overloading could be used. The left column shows examples of using operators with the built-in types. For example, we can use plus and equals for addition of integers, doubles, and longs in assignment. We also use the insertion operator with many built-in types so that we can easily insert values into streams. Now take a look at the right column. Here we have examples of using operators on user-defined types. The first is std_string. We can use the plus operator to concatenate strings, and we can compare strings using less than, greater than, less than or equal to, and so forth. In this section, we're going to create our own version of a string class named myString, and we want to be able to overload some operators to concatenate my strings, compare them, assign them, and so forth. The last example is the player class. Does it make sense to overload operators for the player class? Maybe. It depends on what we're trying to achieve. For example, suppose we want to compare two player objects, P1 and P2. We might only care about their health attribute, and this would do just that. What about comparing two player objects with the equality operator? Are we comparing names, health, XP, all of those attributes, or just some of them? That's one of the issues with overloading operators. We can make the operator mean anything we want. So we want to make sure that when we do overload operators, it makes sense and the users of the class know about it. Finally, it would make sense to overload the stream insertion operator so that we can insert player objects into a stream. So let's look at the class that we'll be using in this section of the course. We're going to add overloaded operators to this basic class called myString. myString models a string and will implement it behind the scenes using a raw C-style pointer. I chose to include a raw pointer because it will allow us more practice with our copy and move constructors, and we'll also have to think about copy and move assignment when we overload the assignment operator. Right now, the class contains a noargs constructor, a constructor that expects a C-style string or literal, a copy constructor, a destructor, a display method that displays the string, and two getter methods. The first one returns the current length of the string, and the other returns a pointer to the string. That's it. At this point in the course, you should start feeling pretty comfortable when you see a class declaration such as this. Now, let's head over to the IDE and we'll take a closer look at this class and how it's implemented so that it's clear what it does before we extend it by overloading operators. Okay, so now I'm in the IDE. I'm in the section 14 workspace. I'm in the myString-start project. This project really doesn't do much. It's just a beginning project that initially implements that myString class that we're going to extend throughout. But I want to take a few minutes to go over that class to make sure that you 100% understand it. And I encourage you to walk through it, set some breakpoints, step through it using the debugger, and be sure that you really understand what's going on in this class. The idea with this class is that I want to model strings. Now, we already have a standard string class, I know. Let's do it ourselves. That way we really learn how to implement one of these things. So what we're going to do is we're going to create our own myString class. And here's an example of how you would use it in a main. Here I'm creating empty, which is just an empty myString object that's going to call a noargs constructor. Here I'm going to create Larry, which again is a myString object. And I'm going to initialize it to that string Larry using an overloaded constructor. And then finally, I've got another myString called Stooge, and I'm initializing with Larry. So there we have a copy constructor call. And then all I'm doing is calling the display method for each one of those objects, which is going to display empty string, Larry, and Larry again, since we copied it. Okay, so let's take a look at the class. This is the same class that I showed you in the slides a minute ago. What we're doing here is we've got our myString class. You can see it right up here. And we're implementing a string behind the scenes as a pointer to a character. It's basically the way a C-style string works. Now, we could have done this a lot of different ways. I chose to do it this way. That way we can play around with raw pointers a little bit more, understand the copy constructor, understand the move constructor, which we'll do soon, and understand the assignment operators. We've got a destructor, we've got the display method that displays the contents of this string, basically the string itself and its length. And then we've got a couple of getters. Okay, so let's go through these and see how they're implemented, and I'll walk you through a couple of examples. And let's take a look at my string CPP. Okay, so here you can see that I'm using behind the scenes the C string library, which I need. I've got IOStream simply because I'm doing some output. And here is my string.h. I need to include that because this is what I'm implementing, right? That's my spec. Here's my implementation. So here's my noargs constructor. You can see it right here. Remember, the noargs constructor gets called when code like this executes. Let's say my string, and let's say just A. Right, so we're providing no construction information here. So the noargs constructor gets called. You can see it expects nothing. And what we're doing here is we're creating an object called A. And let's just put A right here. This is that object. It's just a blob right now. And it has in it a pointer called str. That's the one we really care about. Now, if we create an empty object, we could simply set that pointer to null pointer and we're done with it. I don't want to do that. I want to set an empty string to an empty string that looks like that. In other words, a single character with the null terminator in it, rather than a null pointer. That just makes it easier later. If we ever display or print out an empty string, it'll be fine. We don't have to check for null pointers later. Okay. So what are we going to do here? Well, we're going to allocate space for one character. Notice the brackets, they're important here because we're going to delete characters in that manner as well. So I'm going to allocate one character. Remember, all this is happening on the heap. This is happening on the stack. And I'm going to assign that address to str. So str is pointing there. And then all I'm doing is dereferencing the pointer and putting that terminator in there. That's my empty string. If you try to display this, it will just display nothing. Okay, so that's my noargs constructor. Now let's take a look at the overloaded constructor here that expects a C-style string, right? Or a string literal. So in this case, this will be called with statements like this. My string, let's call this, again, let's call this A again, and we'll just say hello. Notice this, the quotes and the curlies. Okay. At this point, you can see what's being passed in. So this constructor matches, and this is the constructor that executes. In this case, I'm checking to see if by any chance somebody sent a null pointer here. If they did, I'm just going to create an empty string. I'm just going to double check that just to be safe. Normally, this else is going to execute, and I'll show you what's going on here. Again, we're going to create that A object. It's right here. It's got an attribute called str. That's the only attribute it has, actually. And what we're going to do is we're going to allocate this many characters on the heap. How many characters is that? Well, I'm going to figure out what the length of hello is, right? That's what S is. S is hello. I'm going to figure out what's the length of S and add 1 to it because I need an extra character for that terminator. Well, the C string functions in C string right here, there's one called strlen that does exactly that. So what I'm doing is I'm just calling std_strlen, which is going to return 5. I'm going to add 1 to it, and I'm going to allocate 6 characters on the heap. And then I'm going to call std_stringcopy to copy S to str. So at this point, it's going to copy hello here. It's going to put the null terminator. Those are my 6 characters, and I'm going to point to it. So you can see I've indeed made a copy. Okay, we never messed with hello because it's const and it's not mine, so I don't want to mess with it. Okay, so now let's make a copy constructor. Let's go through that real quick. You can see it defined right here on line 25, right here. Now, when does a copy constructor get called? Well, remember, we've got an existing object and I want to copy it and construct a new object from it. This is not an assignment, it's a construction. So what I've got is, let's say I've got that string object again, my string, and let's call it A, and we'll use hello again. So there's that object. Now I want to create a new object. I'll just say my string, we'll call it B, and I want to create it based on A. So there's my copy. That's my copy constructor being called. Also, a copy constructor, as you know, gets called if you pass an object by value to a function, lots of different places. So let's see what's going on here. In this case, this refers to the object that I'm creating. And source is that guy right there. So source in this case is that A object, hello. Okay, makes sense? Good. So I'm creating the object. I'm setting str, right? So here's that new object I'm creating. It doesn't even have a name yet, but let's just call it this because it's being pointed to by that pointer. It's got str again, just like before. And what I want to do is I want to copy that hello to this guy. And I want to do a deep copy. I don't want to share this. So what do? Well, again, I want to allocate space. How much space? The length of that source object's string, right? A.str in this case, which would be hello. So 5 plus 1 is 6. Again, I'm going to allocate 6 characters on the heap. Remember, these are unnamed. It's all on the heap. Then I'm going to do, and again, I used std start string length to do that. Now I'm going to do std string copy to copy the source string to the string. Again, a deep copy. So in this case, I'm copying over hello, the null terminator, and this guy's pointing to that. That's it. So that's where we're at right now. The rest of the functions you shouldn't have any issues with at this point in the course. Let's go through them anyway. Here's my destructor. Obviously, remember this, you're responsible for deallocating the memory that you allocate. So I've allocated some memory in the constructors. I've got to be sure to deallocate it in the destructor, and that's exactly what I'm doing here. I've got a display method. This is a member method, and the display member method just simply displays the string, which is a C-style string, and the length separated by colon. And then I've got some getters. One just returns the length of the string, which I'm determining every time dynamically. I'm asking what the string length is. We could have had, let me just come back, and let me do this one first. And the string returns the pointer, so I can print it, and it returns it as a const. We could have added another attribute here called length, and we could have maintained that length of that string all along, but I chose not to do that. I'm just going to keep it as simple as we can, and that's it. So let's take a look at the main, and we'll run it. There's my main. Give me an empty my string, create Larry, and then copy Larry. So when I run this, you see the run says display the empty string, and it's displayed right here. Obviously it's empty and its length is 0. Display Larry, there's Larry and its length is 5. And there is Stooge, it should be Larry because I used a copy constructor. Again, I did a deep copy, and there's a 5. Okay, so that's it. That runs through this program. As I said, you may want to step through it until you become really, really comfortable with it. It's a very, very straightforward program. It's using everything that we've learned so far. And what we're going to do now is start by overloading the assignment operators. In this video, we'll learn how to overload the copy assignment operator. The assignment operator is used by C++ when it assigns one object to another object. Don't confuse assignment with initialization. Initialization is done by constructors when we create new objects. The statement myString s2 equals s1 is not an assignment statement. It's an initialization statement because s2 hasn't been created yet. C++ allows us to use the assignment operator in this context, but this assignment is really equivalent to myString s2 from s1. As shown in the comment, it will invoke the copy constructor. Notice the statement s2 equals s1. This is assignment since s2 has already been created and initialized previous to this statement. So, an assignment occurs when an object has already been initialized and you want to assign another object to it. C++ provides a default way of assigning one object to another, and if you don't provide your own overloaded assignment operator, then C++ will provide a compiler-generated one for you. This is very similar to what it did with the default copy constructor. The behavior for the default assignment is member-wise assignment, which means shallow copying. If your class doesn't have raw pointers, then the default assignment operator will probably be just fine. However, in my string class, we have a raw pointer, so we'll overload the assignment operator so that it deep copies the pointed to data on the heap. So how exactly do we overload the copy assignment operator? First, the assignment operator must be overloaded as a member function. So we can provide a method prototype that has the general pattern shown in the top declaration. We then simply replace type with the name of our class. Notice that the name of the method is operator equal. That's how we declare methods that overload operators, the keyword operator followed by the operator that we wish to overload. So for the myString class, the overloaded assignment operator method returns a reference to a myString object. This is important since we want to avoid extra copies if we return by value. And we also want to allow chain assignments such as P1 equals P2 equals P3. We'll define this method in the next slide, but once it's defined, we can write code like S2 equals S1, which assigns object S1 to object S2. That's very readable and writable code, and it feels exactly like if we were assigning one of the C++ built-in types. But now it's working with our own user-defined classes. That's pretty easy and pretty neat. The compiler will actually convert the S2 equals S1 assignment statement to S2.operator equal and pass in S1 behind the scenes. Let's see how we would implement the copy assignment for the myString class. Here's the code for the overloaded copy assignment operator. It looks complicated, but it really isn't. We'll break this down into the basic steps over the next few slides. Remember, the object on the left-hand side of an assignment statement is referred to by the this pointer, and the object on the right-hand side is being passed into the method. I've named the right-hand side object RHS for right-hand side to be clear. Since we're assigning the right-hand side object to the left-hand side object, we must make a deep copy of the right-hand side object's attributes and copy them over to the left-hand side object. So, what does this mean semantically? Well, the left-hand side object, or this object, will be overwritten. So we need to deallocate anything it refers to on the heap. Then we have to allocate space in the left-hand side object for the right-hand side object's data, and then we finally copy the data over to the left side from the right side. Let's go over this code one statement at a time, since I know it can be hard to follow when you're first learning this. The first thing we want to do is check to see if we're doing self-assignment. For example, P1 equals P1, or assign P1 to itself. We can easily check for that by checking the address of the left-hand side object, which is in the pointer this, and comparing it to the address of the right-hand object. If they're the same, then we really don't want to do anything, and we just return dereference this, which is the left side object. If we don't have self-assignment, then we need to deallocate storage for this string since it's pointing to a string on the heap. We need to deallocate the storage, otherwise when we copy the new data over, we'll orphan this memory and end up with a memory leak. Now the left side object is ready to be assigned from the data from the right side object, but we haven't yet allocated storage on the heap for the deep copy. So we need to allocate enough storage on the heap that's the size of the string in the right object plus 1, since we need the space for the string terminator. That's it. Now we can do the copy. We can perform the copy by copying over one character at a time until we see the null character. But since we're using a C-style string, we can simply call the string library method std_string_copy, which copies the string from the right-hand side object to the left-hand side object. That's it. We're done. All we have to do now is return the left side object so we can support chain assignment. This may seem like a lot at first, but it's a pattern or idiom that we always use in C++ when we're doing deep copy assignment. In this case, we only have a single raw pointer. If your class has multiple raw pointers, then don't forget to deep copy each of them. Let's go over to the IDE and step through copy assignment using the debugger so you can see exactly how this works in live code. Okay, so I'm back in the IDE, and in this case, I'm in the section 14 workspace, and I'm in the myString-copy-assignment project. What we want to do now is, we've got our myString class, and it's really basic right now. It's only got the constructors, the copy constructor, the couple of getters, and the display, just as we've seen before. And what we want to do is we want to add the copy assignment operator. We want to overload that and add it to the class. But before we do that, let's talk about the semantics of exactly what we're trying to achieve. So I've written 4 lines of code right here in my main. I've actually got a lot more in the main, which I will uncomment out later. So let's talk about these 4 lines of code and talk about it in the context of assignment. You can see what's going on here. I'm instantiating my object A. It's a myString object, and I'm initializing it to hello. So when this line executes, I will have something like this. I'll have my A object. It will have an str attribute, which is a pointer. Hello will be allocated on the heap. Remember, there's a null character there at the end, so this is really 6 characters big, and that str attribute will be pointing to it. So that's the condition that I'll be in after the construction of the A object. Then when we create the B object, we'll be in a situation like this, where this will be B, this will be str again. In this case, I'm pointing to an empty string because that's the how we defined our noargs constructor. So we'll be something like that. Remember, the empty string consists of a single character with the null character in it. Then we're going to execute this code right here, B equals A, or assign A to B. In this case, this is assignment because B already exists. B has been instantiated. So what we want to happen is a couple of things. First, we want to be sure that we're not assigning to ourselves B equals B or A equals A. That's easy to do. Then what we'll do is we really want B to contain that hello, right? But we don't want this situation like we had with a shallow copy. We want to create a copy of that hello string on the heap. So in order to do that, there's a couple of things I need to do. First of all, I need to deallocate this, right? And this could be a lot bigger than just an empty string. This could be a very large string. So I want to deallocate that. Then I want to allocate space for 6 characters, right? Because I'm copying hello in there, and hello has HELLO and the null terminator. I want to be in this situation. I want to copy hello over. And at this point, what we've got is this kind of situation. All this is gone now. That's been deallocated so we don't leak memory there. And this is where we want to be with B. Okay, so that's where we're headed. You can see the steps that we need to do visually here. We're going to do them in code next. Now, this example here is also an assignment because we're assigning something to B, and B already exists. In this case, it's a little bit different because we don't have an operator equal that expects a character pointer, right? Which is what this is right here, a C-style string. So what we need to do is we need to construct a temporary object using the overloaded constructor, just like what we did over here, and then assign that temporary object to B, and then that will eventually be destroyed. The temporary object will. Okay, so that's it. That's where we're going. Let me clear this, and we'll start writing the code now. And then once we're done, we'll walk through this example. So let's start with our header file. What we need to do is we need to write the prototype here, and I'll leave a little bit of extra space so it's really clear, for the overloaded assignment operator. So we know it returns a myString object by reference. We know that the name is operator equal. That's just the way we name operator methods in C++. That just tells the compiler that you're overloading the equal or assignment operator. What does it expect? Well, the right-hand side. Remember, the left-hand side is this. It's a pointer to the current object. The right-hand side is simply going to be a constant myString reference. And I'll name it right-hand side. We don't have to provide a name here in the prototype. And I'll just say copy assignment. That's our prototype. Again, be really sure that you understand this. We're overloading the equal operator or the assignment operator. The left-hand side is the current object. The right-hand side is what we're assigning. And we want this guy const because we really don't want to mess with it. It's not our object, so I don't want to mess with it at all. Also, remember, this is not construction. This is assignment. That left-hand side already exists. Okay, so now let's write the code for that copy assignment. Now, I've made a little room here so that I can put in the code, and we've also got some breakpoints, so I've already gone ahead and put one in. So what we'll do is we're now going to implement that. So myString, right, we're returning a reference, and this is operator equal. What does it expect? Just like the prototype, const myString reference right-hand side. Okay, now the first thing I want to do is I just want to do a little output statement so that we know when this is being called. So I'll just say std_cout, and we'll just say something like copy assignment. And we'll do std_endline. Perfect. So what do we need to do first? Well, first thing we need to do is make sure that we're not assigning to ourselves. That's simple enough. If this, now remember, this is a pointer to the current object. So and a pointer holds an address. So if this is the address of the right-hand side, in other words, we're really the same object, then all I want to do is just return this. Okay, and we need to dereference this in this case. Remember, if we just say return this, this won't compile because then that means that this guy would be expecting a pointer back, but we're not. We're doing a reference back, not a pointer. Okay, so we're going to pass up the reference back. That's it. Now we start doing the real work. First thing we need to do is, remember that this object is the one that's being copied into. So it may be pointing to something, right? That str attribute may be pointing to a string. Actually, it is pointing to a string, even if it's just an empty string. So what we need to do is just delete and make sure you use the brackets here because it's an array of characters we're deleting, str. Okay. If this makes it more clear, then feel free to use the this keyword right there. It's all the same. Then we're going to say str equals new character. We need to allocate that array of characters on the heap. And how many characters do we need to allocate? Well, we're copying the right-hand side object's data into it, right? So the right-hand side object has an str attribute. So however big that string is, +1, because we need space for the string terminator. So how big is this going to be? Well, it's going to be, take the string length of, not str, right? But right-hand side str. And since we're a member method, we have access to that. And we want to add 1. Perfect. So now we've allocated the space that we need on the heap. The only thing left really is to copy that string over from the right-hand side and then just return. So let's do that. So we'll do stud string copy to str. Again, you could say this str if that's clearer. From RHS, right-hand side string. So that's the string copy. The string copy function simply copies one character at a time until it hits the terminating character. It copies that as well, then it's done. And the last thing to do is just return the object that we just copied into, the left-hand side. That's it. Let's go and run this. But before we do that, let's actually debug it. So I'm going to go back to my main and let's start the debugger. So this is where we're at. Let's step through this so we can really understand what's going on here. At this point, I'm on line 10. I'm constructing or instantiating that A object, right? And I'm providing some initialization information, this string. So in this case, I'm going to call the overloaded constructor. So let's do that. Let's step through. There is the call to the overloaded constructor that expects a character pointer just like we expect. It's not null. So we're going to skip the if part. And we're right here. So how many characters are we allocating for this guy? Well, whatever the string that was being passed in by +1 for the null terminator. And then we're just copying it over. So let's step through this. And when we get back here, you can see that A right here, that str attribute is pointing to the string hello, exactly like we expected. The B object, same idea, except we're calling a no-args constructor since we're not providing any information. And when we get back, we expect B's string attribute to be an empty string. So let's do that. There you can see the no-args constructor. It's simply creating one character and putting the null terminator in there. So at this point, you can see that A is hello and B is that empty string right here. Now's the assignment. I'm assigning A to B. So let's step through this. We expect operator equal to be called. And that's exactly what happens right here. We're on line 38 of the copy assignment overloaded method. We display copy assignment. We're going to check for self-assignment here. We don't have self-assignment, so that will be skipped. Now we're going to delete the left-hand side object's string on the heap. So we're deleting that. And at this point, we're going to copy, and you can see that the right-hand side is hello. And the left-hand side right now is just pointing to garbage, right? Because we've deleted that, so it's invalid memory. We're really pointing anywhere right now. So what we're going to do is simply replace that with an area that I'm creating on the heap that's going to store the string that I'm just about to copy. So let's do that now. And then we're going to copy that string over. So at this point, I'll refresh here, and you can see that right-hand side was still hello, and now this is also hello. And there you go. And you can see from the addresses, they are indeed two unique areas in memory. I'm returning the object by reference, and that's it. I'll refresh this side again, and now we've got A and B, and they should be the same. A is hello, B is hello, and there again, two different areas in memory. Okay. This example here, what's going to happen is on line 14 is we're going to call the overloaded operator again to create that object. And then once that object is created, we'll assign it over. So that temporary object is going to be assigned over. So let's just walk through that really quickly here. And you can see right here, I'm calling the overloaded constructor, which is going to create a temporary object. And now that temporary object will be assigned. So you can see the assignment operator being called now. So I'll walk through that again. We delete what we're at. We move it over. And we get rid of the temporary object. That's the destructor being called right there. That's it. So we're done here. You can see A is hello and B is now. This is a test. And as we unwind, we're going to call the destructor for B and then the destructor for A, and our program is done. Okay, so that gives you an idea of the assignment operator, the copy assignment operator. It's pretty straightforward. And what I've also done is I've created some other test cases here that you can walk through and learn from. And what I'll do is I'll just uncomment them out and then I'll run the program really quickly. So what I've got is I've just got some examples of creating more objects and assigning objects to vectors and so forth. And you can see that when we do things like s equals changed, we're going to create a copy assignment. And that's exactly what we want. We don't really want to create that guy using the conversion constructor and then use a copy constructor to copy stuff over. We're just doing assignment, and we don't want to do anything related to shallow assignment, right? We want to do deep assignment. Otherwise, we're going to end up with all kinds of problems. So I'll run this, and there's the output. You can see that we've got copy assignment happening. We've got Larry a bunch of times. And like I said, you can run through this and walk through it yourselves. It's real important that you step through a program like this and you can really, really understand what's going on. But you can see that copy assignment is called all over the place here because that's exactly what we want. Okay, so now in the next video, what we'll do is we'll do move assignment, which is pretty powerful, and it'll take care of assigning temporary values much more efficiently than copy assignment. In this video, we'll overload the move assignment operator for our myString class. Remember, the copy assignment operator that we just overloaded in the previous video works with L-value references. The move operator that we'll overload in this video works with R-value references. Again, think temporary unnamed objects. You don't have to provide a move assignment operator, and if you don't, C++ will use the copy constructor by default. But as we said when we talked about the move constructor, move semantics can be much more efficient, and it's not a lot of extra work to provide a move constructor and a move assignment operator. First, let's see when the move assignment operator will be used. In the code snippet in this slide, you can see that we create a myString object S1 that's basically just an empty string. Now we assign the myString object with the string Frank to it. Notice that the myString object initialized to Frank must be constructed, and once it's constructed, it has no name. It's a temporary object, so it's an R value. That means that when we assign it to S1, the move assignment operator will be called since we're providing an R value reference. Let's see how to do this syntactically. You'll notice the move assignment operator declaration is very similar to copy assignment, but there are a few differences. First, we use the double ampersand operator in the parameter list to tell the compiler that the right side object is an R value. So the right side value will be an R value reference. Second, the right-hand side object reference can't be const, since we'll be modifying that object when we move the data. So the declaration for the myString class returns a myString object by reference and expects an R value reference to a myString object. You can see that in the two assignment statements on this slide, the move assignment operator will be called because the right-hand side of the assignment statements are R values. So let's look at the code for the move assignment operator for this example. As you would expect, the code is very similar to the copy assignment, with the exception that we're not deep copying from the right-hand side object. Instead, we're simply stealing the pointer and then nulling out the right-hand side pointer. Again, you can see from this code how much more efficient this is compared to copy assignment. Let's walk through this one step at a time. First, we check for self-assignment as before. And if we're self-assigning, then we return the left-hand side object and we're done since there was nothing to do. Otherwise, we again deallocate the storage pointed to by the left side object since we'll be overriding this and we don't want a memory leak. Now the left-hand side object is ready, so let's move the pointer over. First, we steal the pointer from the right side object and assign it to the left side object. This is simply a copy of a pointer variable. We're not doing a deep copy here. Then we null out the pointer on the right side object. This step is critical. Finally, we return the left side object. Now let's head over to the IDE and compare the move assignment operator to the copy assignment operator in live code. Okay, so I'm back in the IDE. I'm in the section 14 workspace in the mystring-move-assignment project. Now what I'd like to do in this project is add a move assignment operator to our mystring class. This can be real useful when we're assigning R-value references. So let me give you an example of how this would work. Here we've created an object A, and it's using an overloaded constructor that's expecting that character pointer. And we're just constructing a simple object A that's got that string attribute pointing to hello on the heap. Now at this point, we want to use assignment. Remember, A already exists, so now this would be assignment, not initialization. And what I want to do is construct another mystring object off of the initialization string hola. At this point, that temporary object has no name, so it's an R value. If we don't provide any move semantics, then it's going to use a copy constructor or a copy assignment operator to do what it needs to do. And if I run this right now, remember, I don't have any move constructors, I don't have any move assignment operator implemented. So if I run this at this point, you'll see that it's using copy assignment, using copy assignment. Now, we really could use move assignment here since we've got those R value references, and that's what we'll do. Okay. So let's go over conceptually what's going on here again. At this point, we've created that A object, and it's on the stack. It's got the str attribute, which is a pointer. And once this object has been constructed, that pointer is pointing to the string hello, which is on the heap. And again, remember, it's got that null terminator at the end. So this is the situation once we instantiate A. Now what we want to do is we want to assign to A the object that we created right here. So let's create that object. That object gets created exactly the same way as we created A, right? It's using the overloaded constructor, but it doesn't have a name. It's an unnamed temporary object. So I'm just going to leave it right over here like this without a name. It's got an str attribute, and it's pointing to hola, which is on the heap. So that's the situation like right now. Now what we want to do is we want to assign this guy over to this guy. But we really don't want to do the overhead of copying because we don't need to. This temporary object will be destroyed soon. So let's just use move assignment so that we can steal that pointer and not have to make any copies of anything or copy anything over. Okay, so let's do that. How does this work? What are the semantics? Well, the first thing we need to do is deallocate the space here, right? We need to call delete for this guy because we're not going to use that. That's the whole point. I want to assign to it. So we're going to get rid of that. And what that's going to do, it's going to leave us in this situation where we're no longer pointing to that area. And then what we want to do is we want to steal the pointer. So I want to make this pointer here point to hola. And then once that's done, what I want to do is not delete this. I don't want to delete this information here, right? I don't want to deallocate that because I'm using it now over here. All I want to do is just null out that pointer. So that's what I'll do. I'll just null this pointer out. So this guy is now null. You'll notice A is now, the string attribute in A is now pointing to the correct string on the heap, which is what I want. This guy has been nulled out. So when it gets destroyed by the destructor, it won't delete anything out there on the heap because it's not pointing to anything on the heap. So once this gets destroyed, we're right back to here, which is exactly where we want to be. And the same is true with this statement right here. A is bonjour. We'll create a temporary object. There's the str, and it's going to be pointing to bonjour. Right? Now, when we assign over, we'll do the same thing. We want to deallocate that storage right here. So we want to get rid of this. We want to move the pointer, right? We just want to steal this pointer and let it point over here. And then what we want to do is set this pointer right here to null. Right? So we just move the data simply by just pointing to it from a different place. This will be destroyed, and that's the effect that we want. Okay, perfect. So now let's write some code for this. And you'll see it's actually a little bit simpler even than the copy assignment. First things first, let's go to the header file And you'll notice that I've already implemented a move constructor. Okay. I just wanted to be complete there. So the move constructor has been implemented, and it's about as dead simple as you can get. Let me show you what the move constructor looks like. It's right here. Remember, this is a constructor now. This is not an assignment. So this is actually creating a new object based on an R value reference. So you can see right here on line 35, I'm stealing the pointer, right? So I'm taking the source object's pointer and moving it right to str. And then I'm nullifying the source object's pointer. So that's it. We just stole the pointer. That other object will eventually be destroyed. Let's write the move assignment operator. So let's go back to our header file, and we'll do it right here. And we'll do something like my string reference, because it's the same idea here. We're overloading operator equal. We don't want to be const here because we do need to modify that right-hand side's string attribute to null it out. So it's simply going to be my string, 2 ampersands here because we want an R value reference, right-hand side. That's it. And we'll call this guy move assignment. All right, so now let's go implement that method. So we'll go to my string cpp file, and right underneath the copy assignment right here, I'll just put it right here under move assignment. And you can see I've already set some breakpoints just to save a little time. So let's implement this here. So what do? We're going to return a my string reference, and it's part of the my string class. We're overloading operator equal, and we're expecting a my string R value reference. Okay, that's it. So first thing we do is, as usual, let's just put a string out on static out, and we'll just say something like using move assignment. That way we know that we're actually in here, and we'll put an end line here. Perfect. Now, let's check for self-assignment. I'll scroll up just a little bit here. We'll check for self-assignment. So we're going to say if the current object, right, the address of this object is equal to the address of the right-hand side object. If that's the case, I've got self-assignment. So all I want to do is just return this. In the case that we're not doing self-assignment, remember the conceptual drawing I just drew. So what do we want to do? We want to delete str from the current object. We want to steal the pointer. So we want to assign the right-hand side's pointer to the left-hand side's pointer. And we want to nullify the right side pointer. This one's really, really important. If you forget to do this step, then there's going to be problems, because what's going to happen is when that temporary object gets destroyed, it's going to take this data with it. So you want to be sure that this is pointing to nowhere. So right-hand side dot string equals null pointer. That's it. We return this. Okay. Now, we'll step through this in a second, but let's run it first. And now you can see the difference in the run. Using move assignment, using move assignment. That's exactly what we want. And then we've got two destructors being called for null pointers, right? Which is, again, exactly what we want. All right, so let me put a breakpoint here. And let's walk through this using the debugger. So I'm going to go back to my main here, and I'll start the debugger over here. All right, so this is where we're at. Right now, we're about to call the overloaded constructor to create the A. That's pretty standard stuff now. Here we are. We don't have a null pointer, so we're simply going to allocate space for the string, copy it over, and we're done. So now A is hello, and you can see the address of that string attribute right here. Now what we need to do here is first construct that temporary object, and then call the overloaded assignment operator, right, with an R value reference, because that's exactly what this is. This is an unnamed object. So let's walk through this. So first we're going to create the object using the overloaded constructor right here. So we'll walk through that, allocate the space, copy it over. It's done. Now notice that the move assignment operator gets called right away. That's exactly what you expect, because we have an R value reference here, which is a temporary unnamed object. So we display using move assignment. We check for self-assignment, which we don't have. We delete this str, right? Remember, this is this object right here. So we're going to delete that and deallocate it. We're going to steal the pointer, and then we're going to nullify that other pointer. Now the temporary object is being destructed right here. And we do have a null pointer now because we nulled it out. You can see it's 0 right there. So this will print out calling destructor for null pointer. We'll delete the area. And that's it. Now if we refresh, you'll see that A now is hola. So we did exactly what we said we were going to do. Here it's the same idea. First, we're going to construct a temporary object based on that string. So let's do that. Here we are, we're in the overloaded constructor, and that's going to create a temporary object with bonjour in it. Then we call the move assignment again because we have an R value reference. And what we're going to do here is we're just going to steal that bonjour pointer. First, we delete what we're pointing to, right? So hola's gone. Then we steal the bonjour pointer and we set that temporary object's pointer to null. We return the object, and then we're going to destroy that temporary object again, the one that we just stole the pointer from. We'll delete it. We're back, and you can see now that A is bonjour. We'll unwind now, and we'll destroy A. There you go. And you can see over here that we've got 2 move assignments, 3 destructors, 2 destroying just null pointers, temp objects, and then the final one destroying the actual A object that we created. That's it. So you can see it's pretty straightforward, and we'll see that in the main driver here, I've got a lot more code. And if you recall that code running from before, so I'll run this code again in the main now that I've uncommented it. And if you remember when we ran it before, it was using copy constructors and copy assignment. Well, in this case, when we run it, we're going to see a lot more move semantics going on. So I'll scroll up here, and you can see that we've got move assignment, move assignment, move assignments, move assignments, move constructors. So this version is much, much more efficient. And if, again, walk through it, check out the statements, use the debugger if you like, and really understand what's going on. But it's very, very straightforward. In the case of our values, we really want those move assignments and move constructors just to make our code so much more efficient. Welcome back. So we've learned how to overload the copy and move assignment operators. Now let's look at some of the other operators that C++ lets us overload. C++ allows us to overload operators as member methods or as global non-member functions. In this video, we'll use member methods to overload operators. And in the next video, we'll overload the same operators using global functions. So let's start with unary operators. Unary operators work on one operand. Those operators include the increment, decrement, unary negation, and the bang or not operator. Notice the basic method declaration in bold. In the case that we have to return a new object from the method, we'll return the new object by value. Also notice that unary member methods have an empty parameter list. This is because the object we're working with is referred to by the this pointer. So here you can see the prototypes for the unary operators if we wanted them to work with our hypothetical number class. Also notice that we can overload both the pre and post decrement and increment operators. C++ simply provides an int that isn't used in the parameters for the post increment. At the bottom of the slide, you can see how we can use the unary operators as we do with the built-in types and what methods are being called in the comment section. Suppose we wanted to overload the unary minus operator to work with our myString class, and we want to make the string lowercase whenever it's used. So we can create a myString object named Larry1 with the initializer string uppercase Larry. Then we can use the unary minus operator on Larry1 and store the result in Larry2. Now Larry1 will still contain the uppercase Larry string, but Larry2 will contain the lowercase Larry string. This is a simple example of unary operator overloading using member methods. However, the question is whether this makes sense. We're programmers, we can make anything happen in code. Does it make sense for the unary minus operator to make the string lowercase? It depends on the context of the application and the design. Personally, I'd prefer a method named lowercase or lowercased or toLower, since that's very explicit. But this might make sense in another design. Let's see how the code might look. Here's the code for overloading the unary minus to make a string lowercase. Notice the method header. We're returning a new object that will be the lowercase copy of the existing object. We're overloading the operator minus. We expect no parameters to this method, And it's a const method since we don't want to modify the current object. We want to create a new object based on it. So the first thing we do is allocate space for an area in memory on the heap where we want to store the lowercase copy of the current object string. Then we use the stdstringCopy function to copy the string over. Then we simply loop through the characters in the copy and convert each character to its lowercase equivalent using the character function toLower in the cc type header file. Once we have the buffer lowercase, then we construct a temporary myString object using this lowercase string as the initializer. Finally, we delete the buffer we created in this method so we don't leak memory, and we return the newly created lowercase object. We could certainly write more optimized code here, but I wrote this method to show each step explicitly. So that's the general pattern for overloading a unary operator using a member method. Now let's see how we can implement some binary operators also using member methods. As we know, binary operators are applied to two operands. These operators include addition, multiplication, division, the equality operators, and many more. The pattern for overloading these operators is very similar to the way we overloaded unary operators, except that now we have a single parameter in the method parameter list. I've named this parameter RHS, which stands for right-hand side. That way it's very clear that RHS refers to the parameter on the right-hand side of the operator, and the this pointer points to the object on the left-hand side of the operator. Notice the overloaded addition and subtraction operators return the newly created sum or difference objects by value. Also notice that the equality operators return Boolean values, which makes sense since they're comparing things. You can see in the bottom of the slide how these operators might be used in our hypothetical number class. Now let's see how we can implement the equality operator in the myString class. In the case of myString objects, we want to compare the strings to see if they're the same. We don't want to compare the pointers. Instead, we want to compare the strings that the pointers point to. Rather than write all the code ourselves, we can use the stdstringCompare function in the cstring header file, which compares C-style strings exactly as we need. When we call that function with two C-style strings, it will return 0 if the strings are equal. So this method becomes almost trivial to implement. We compare str from this object to str from the right-hand side object. And if the result is 0, we return true, otherwise we return false. That's it. Now we can write code like if s1 equals s2 to compare two myString objects for equality. What if we wanted to write an overloaded equality operator for the player class? Well, we'd have to decide what we want to compare. Are we comparing the names of the two objects, or the health, or the XP, or everything? This would be an important decision, and the programmers using the player class would have to be clear as to what's being compared so they can use it correctly. Now let's wrap up these slides by overloading the addition operator for the myString class. Suppose we wanted to overload the binary plus operator for the myString class so that it concatenates the strings from the left-hand side and right-hand side objects into a new object. Then we could use this as in the example code. First we can create myString objects Larry and Mo and Stooges. Then we can write a statement like Larry plus Stooges, which will concatenate the string Larry and the string in Stooges to create a new string. Larry is one of the three Stooges. Notice that we can also use C-style strings on the right-hand side. This is because we have a myString constructor that can construct myString objects from a C-style string. That's pretty cool. The only limitation to overloading operators as member functions is that the object on the left-hand side must be an object of the class you're using. For example, the last statement in this slide won't compile since the left-hand side operand is not a myString object. We can get this to work in the next video when we implement operators as non-member functions. Okay, so let's take a look at the code for this method. It's probably exactly as you would expect. We allocate a character buffer large enough for both of the strings plus 1 for the string terminator. Then we allocate this buffer on the heap. First, we copy over the left side string with stdstringCopy, and then we concatenate the right side string with stdstringcat. We create the new object that will contain the concatenated string using the buffer as the initializer. And then finally, we deallocate the local buffer area so we don't leak memory. And then we return the newly created object by value. You can see that first this looks complicated, but the more you do it, patterns evolve that are very, very similar. Great, so let's head over to the IDE and implement these operators for the myString class as member methods. Okay, so I'm back and I'm in the IDE. I'm in the section 14 workspace. in the mystring-operator-methods project. In this project, what we're going to do is we're going to overload 3 operators as member methods. And the ones we're going to overload are right here, the equality operator that allows us to compare 2 objects, as we can see here, the negation operator, the unary minus operator, which in our case, we're going to make whatever string we want to negate lowercase. And finally, the concatenation operator that'll take 2 string objects and make a bigger string object from it that contains those 2 strings put together, just like we've done before using the regular string class. And you can see we can extend this so we can have Mo plus blank plus Larry plus blank plus curly, and this is a C-style string right here. So it'll be pretty flexible. Okay, so why don't we start? We're going to implement them as member methods. So let's go to our header file and create our method prototypes here. In the case of the concatenation and the unary minus, where we're going to make things lowercase, we're going to return myString objects. So we'll create a myString object, and it's going to be returned by value. We want to create a new object, right? We're going to take those 2 strings, make a new one, return it. We're going to take that 1 string, make it lowercase into a new one, return it. We're not going to change anything that we've got going on already. So let's do the operator minus first, okay? So it's going to be the operator we're overloading, again, is operator, followed by the operator we want, which is minus in this case. And what are we going to be passing into this? Nothing. That's a unary operator, so we've already got what we need to the left side of the dot. It's important to understand that when we're overloading operators as member methods, unary operators take no parameters, binary operators take 1 parameter, because this is already a parameter on the left side. And we want this to be const. And this will mean, let's say, make lowercase version of the string. All right, now let's do the concatenation operator. This is a binary operator, so we need 1 parameter in this parameter list, and that parameter will be const myString reference, and we'll call it right-hand side. Important that it's const because we really don't want to mess with that. And then the last one is the equality operator. It will return a Boolean, a true-false value, and it will be operator 2 equal signs. It's binary, so it's going to expect a const myString reference, right-hand side, and we want this to be a const method as well, so I don't want to change anything. Actually, I want this one to be const as well. That's it. So those are the 3 prototypes. Now what we'll do is we'll go to the mystring.cpp file, our implementation file, and we'll implement those methods. So let's do that now. Okay, so I'm going to put them right here, right after the overloaded assignment operators. And why don't we start with the overloaded equality operator. So that one is, again, bool. It returns a Boolean. It's part of my string class. The name is operator 2 equal signs, and it expects on the right side a myString reference to a constant. We'll call it RHS, and the method is a const method as well. Okay, so what do we do here? Well, we want to compare those 2 strings, right? The string in this and the string in right-hand side. So all we really need to do is just simply say return, and then we can call string compare, which is a C string function that compares 2 C strings. This is what we've got. So str is one of them, and right-hand side.str is the other one. And if that returns 0, we'll return the value there. Okay, so simple as that. We could use an if-else statement if we like, but this works just as well. So that takes care of that, and this will be, let's see, equality. Now, let's do make lowercase. And in this case, we're returning a myString object by value. It's part of the myString class. There's my scope resolution operator, and it's operator minus. Nothing in the parameter list because it's a unary operator, and it's const because we don't want to change our current object again. Now, what do we have to do here? Remember, we need to make a copy of whatever is in the current object, make that lowercase, and then create a new object from it. I need to allocate space to create that copy so that I can make lowercase. I don't want to change the object because I can't, right? And I don't want to. It's a const method. So what do we do? Well, let's create a temporary area in memory called buff. and we'll create a new array of characters there. And how big is that going to be? Well, it's going to be as big as the length of the string in str plus 1. Okay. And again, we're using stood string length here, given that string. So if it's Frank, I'm going to get back 5, allocate 1. And this is a brand new pointer to an area on the heap that I just allocated. It's local to this function. So when we're finished with the function, we need to get rid of that and deallocate it. So now what do I do? Well, at this point, I need to copy the string that's in str to buff. Okay, now we've got a copy of that string. So what we can do now is we can just simply loop through that and set I equal to 0, and we can go while I is less than, let's say, the string length of str, or the string length of buff, actually. So they're both the same right now. And we're going to go by 1. That's it. And now inside the loop, what we want to do is we just simply want to say buff sub I equals the lowercase version of it, right? So stood, and we're going to do toLower, which is a function in the CC type header file. So we'll say toLower, and toLower what? Well, the character itself, buff sub I. That's it. Now we've got what we need. Buff now contains a copy of that original string, and we've just made it lowercase. So what do we want to do now? I want to create a new object, a temporary object, right on the stack here, based on that information. So I'm going to say my string, we'll just call it temp, and we'll initialize it from buff. Now we want to return temp, and then we'll be done. But there's one thing we need to do, and it's really easy to forget, and it's this is one of the benefits of using smart pointers, which we'll talk about later on in the course. Right here, I allocated this area in memory. I've used it right here. I'm done with it. I need to deallocate that space. Otherwise, I'll leak that memory. So I want to be sure that right here, I delete buff. And that's it. That takes care of that. And then the last method is the concatenate method, which again is really straightforward. We're going to create a new string from it. So by value, it's a myString method. We'll call it operator plus. And it expects something on the right-hand side, which is myString. By reference, we'll call it RHS as usual, and it's a const method as well. That's it. So what do we do here? Well, same idea here, right? I just need to allocate an area in memory for characters. We'll call it buff again. And how big is this going to be? Well, this needs to be, since we're concatenating, it has to be the length of this string plus the length of the right-hand side string plus 1. So that's all we're going to do. We're just going to say new char, how many? Well, the length of str plus the length of right-hand side's str plus 1. That allocates the storage on the heap that I need. At this point, I need to copy the first string and then concatenate the second string to it so I can build the bigger string from it. So we'll say stood string copy into buff from the left-hand side string, which is str. Then we'll do a stood string cat to concatenate again into buff from the right-hand side's str. Perfect. So what we've done now is we've just copied one string and concatenated the other. At this point, we've got the information we need in buff to create that new temporary object that I'm going to return. Same thing we did up here. So we'll build that object. We'll call it temp. And we'll build it with the buff information. Remember, delete buff. We're done with it now. And return that temporary object. So that's it. We should be done unless there's any typos. So let's compile and run. And you can see here we've got a copy constructor being used. Larry is 5, Mo is 3. We got back false and true, exactly what we expected. We get Larry, uppercase, Larry, lowercase l. Then we have Mo and Larry, Mo, Larry, and curly. So everything looks great. All right, so there you go. That's an example of implementing these three overloaded operators as member methods. You'll get a lot more chance to practice this when we get into the challenge exercise. What we'll do in the next video is we'll do these same three operators, but we'll do them as non-member functions. In the previous video, we saw how we can overload operators using class member methods. In this video, we'll learn how to overload operators using non-member or global functions. Since these are not member functions, we no longer have a this pointer referring to the object on the left-hand side. So since we very often need access to private attributes in the objects, you see these non-member functions declared as friend functions of the class in many applications. This isn't absolutely necessary since we can still use getter methods to access attribute values, but as I said, you often see them implemented as friends. I'm going to declare these overloaded operator methods as friends when we head over to the IDE. So in the case of unary operators, a single object is in the parameter list, and in the case of a binary operator, two objects are in the parameter list. So let's overload the unary minus operator to make a string lowercase as we did in the previous video. We want to provide the same functionality we did before, and our use of the unary minus operator would look the same. Let's see how we can do this using a non-member function. In this slide, I'm assuming that this function has been declared as a friend to the myString class since I'm directly accessing the private attribute str. Notice first that this is not a member function. It's a regular C++ global function. The function returns a myString object by value, and it's named operator minus. And it expects a single parameter. In this case, obj is a myString object reference. Now the code is essentially the same as it was in the member version, except that the string data is in obj.str rather than in this str. We allocate storage on the heap, copy the object string data, loop through and make the copied string all lowercase. Then we create a new myString object using the lowercase string as the initializer, deallocate the temporary storage, and return the newly created object. Of course, you can't have both the member and non-member versions of this overloaded operator at the same time, or the compiler wouldn't know which one to use. You can only have one or the other. You probably already figured out that overloading binary operators as global functions is basically the same, except that now we have two arguments required by the function. The first argument is the left-hand side object, and the second is the right-hand side object. Here you can see some example prototypes for some operators. Notice that they all have two parameters in the parameter list. I've named the first LHS for left-hand side and the second RHS for right-hand side. Then at the bottom of the slide, you can see how these operators can be used and the functions that C++ will call when it uses them. Let's see how we can overload the equality operator as a non-member function. Again, I'm accessing a private attribute str in the myString class, so I'm assuming this function is a friend of the myString class. The code is almost the same as it was for the member version, except that now I have an LHS object instead of the this pointer. So we compare the left-hand side string to the right-hand side string using string compare as we did before. It's as simple as that. Finally, let's overload the binary plus operator so that we can use it to concatenate two myString objects. We create Larry, Moe, and Stooges as myString objects as we did previously. Now when we use the plus operator, notice the methods that the compiler is calling in the comments. Also notice that each is called with two arguments as we expect. Finally, remember that with the member version, the left side argument had to be an object of the class type. With non-member functions, this isn't the case. Either one or both arguments can be of myString type. However, if you have two string literals, that won't work. C++ assumes primitive pointer and not objects. So let's implement concatenation as a non-member function in the next slide. Here you can see that the function operator plus returns a myString object by value. It also expects two myString objects, left-hand side and right-hand side. Notice that they're both constant references since we don't want to modify them. The code now is exactly as it was for the member version, except that whenever I need the left-hand side object, I use LHS instead of the this pointer. That's it. Again, both the member and non-member versions achieve the desired result, but remember, you can only use one at a time. Let's head over to the IDE and overload some binary operators as non-member functions. Okay, so we're back in the IDE. I'm in the section 14 workspace, and the project is mystring-operator-functions. This is the project where we're going to implement those three overloaded operators, the equality operator, the unary minus operator, which makes the string lowercase, and the plus operator, which concatenates two strings. And this time we're going to implement them as non-member functions or global C++ functions. First thing we're going to do is we're going to make them friends. We don't have to make them friends, but it's going to be a lot easier to write the code because I don't have to call those getters all the time. So we can do that right in the class. Remember, the class has to grant friendship. So we'll write the function prototypes here, and we'll start them off with friend. And we'll do the first one. The first one is returns a Boolean. The operator is the equality operator. And remember now, since this is not a member function, we need two parameters, right? This is a binary operator. So the first one will be const mystring ref LHS for left-hand side, and const mystring ref right-hand side. Right? So that's one function prototype. We'll do the next one for the unary minus. So again, friend, this will return a mystring object by value. The operator we're overloading is the minus operator, the unary minus, and it expects a single mystring ref. And we can call this obj. We can call this anything we like. I think I called it obj in the slides, so I'll call it obj here. And then we've got another operator that we want to overload. In this case, it returns a mystring object by value again. And this is the concatenation operator. So it's going to be the plus operator. And it's a binary operator. So we've got const mystring ref left-hand side and const mystring ref right-hand side. Okay, so there we go. It doesn't really matter where you put these friend declarations in. It doesn't matter if you put them in the private area, the public area, it doesn't matter. So there we go. Unless I have any typos, that looks pretty good. Now what we'll do is we'll go to the mystring.cpp and implement those. We can really implement them anywhere, but since they really add to the interface of the class, it's common practice to implement them right in here in the .cpp file. I'm going to implement them here at the end. So let's do the first one. Let's do the equality. And again, this is a regular function. It's not a member function. So we're going to say bool operator double equal sign for the equality. This is a binary operator, so it expects the same prototype we did before. Mystring ref left-hand side, const mystring ref right-hand side. Okay, so now we'll write the code. We're going to return. We're going to call stud string compare. And what are we comparing? We're comparing the left-hand side's string to the right-hand side's string. See the difference between this one and the member function. The member function, we really didn't have this guy here. That was the this pointer. So we did this str, or simply str. But here we've got those two objects, so that's what we're going to do. So we're going to compare this to 0, and that's what we're going to return. And that should be done. Great. Now, let's do the make lowercase. Notice, again, this is not a member function. If it was a member function, it would look something like that, right? It's not. This is just a regular global function. So here's make lowercase. Make lowercase returns a mystring object by value. It's operator minus the unary operator we're overloading. And since it's unary, there's going to be one parameter in this parameter list, and it's going to be a mystring ref. We'll just call this obj. I think that's what I called it in the slides, and I'll stick to that name. That's it. Now let's write the code again. Again, it's the same code we had before. We need a buffer area, and what we're going to do is we're going to allocate a new array of characters in that buffer area. How big? Well, we're going to ask std_strlen to give us the length of, again, what is this now? It's obj.str. Right, now we have access to that because we're a friend. And we're going to add the 1 for the string terminator. Now that we've allocated the space, we're going to string copy into the buffer from obj.str. Again, that function copies one character at a time, and then when it hits the terminator, it copies that as well and stops. That's it. Now we'll loop through just like we did before. So we'll go from an unsigned int I equals 0 while I is less than, we'll say string length of buff by 1. And for each iteration, what we'll do is we'll just simply say buff sub I equals, we'll call stood to lower, and we'll make the buff sub I lower. That just makes it a lowercase character. Right? So now we've got what we need to build our temporary object, temporary to this function that we're going to return. So my string temp, we'll initialize it from buff, and we'll return buff. We'll return temp. Now, obviously, we allocated space in here, which we're done with, so we need to delete buff. That way we don't leak memory. And I think that should do it. Again, if we have some typos, I'll fix them once I compile. And then the last one we'll do is the concatenation. So now let's implement this one. It's going to return a myString object. The operator we're overloading is the addition or plus operator, which means concatenation in this context. And we've got, it's a binary operator, right? So we've got those two objects again in the parameter list, the left-hand side and the right-hand side, both references. Okay, so now what do we do? Well, let's allocate the space. Remember, the space needs to be big enough to hold both those strings since we're going to concatenate. So we'll just simply say char buffer again, and we'll create a new character array. How big is it? Well, it's the length of left-hand side string plus the length of the right-hand side string plus 1. That way we've got enough space to put both strings in there. Now what we do is we just copy the first one over. We use string copy into buff from the left-hand side object. And then we concatenate on the end of that using string cat from the right-hand side object. Again, we've got what we need to create our object that we're going to return now. So we'll create my string, and we'll just call it temp, and we'll initialize it with buff. And let me get rid of that space in there. Perfect. Again, we return temp. But before we do that, we've got to be sure that we delete the buffer so we don't leak memory. And that should do it. So let's give this a compile. And we've got a compiler error here. I need one more colon there. And I've got an extra parenthesis. And let's see what else we have here. Char. And that should do it. There's my run. So what we're doing is we're creating a string Larry, which is Larry with an uppercase L, and we're displaying it. There you can see it. Then we're using the unary minus operator right here, and we're negating Larry. What that means is just make Larry with all lowercase letters. And in this case, we're assigning right back to Larry. So what happened here is that you can see Larry prints out right here, and we're using move assignment. So Larry has got a lowercase L now. And then we've got some comparison operators that we're testing out here. So Larry right now is Larry, and Mo is Mo. Are they the same? No. Is Larry the same as Stooge? Yes, because I assigned Larry to Stooge, as you can see, so they're the same. And then we've got a few more test cases here, which are real simple. Here, Larry plus Mo displays Stooges is Larry plus Mo. So when I display Stooges, you see here Larry, Mo, right? No space between them because I didn't provide one. Here, two Stooges is Mo plus space plus Larry. And I display that. There you see Mo and a space and Larry. And then finally, we're going to change some of these concatenators. So we have Mo space, Larry space, curly. And we've got Mo, Larry, and curly. Notice Larry still has that little lowercase L. And curly is a C-style string, and it works just fine. Okay, there you go. You'll have some more time to practice these in the challenge exercise, where you'll be able to do some overloaded member functions and some overloaded operators as member functions and others as non-member functions. The last operators we'll overload in this section are the stream insertion and extraction operators. This will allow us to insert and extract our MyString objects to and from streams exactly as we've been doing with all of the other built-in types. You can see in this slide what the code would look like if we could simply insert our own user-defined objects into an output stream. This makes our classes feel and behave more like a built-in C++ type. Of course, we can also overload the stream extraction operator so that we can read data from a stream and assign them to our own objects. Here you can see that we're reading data into Larry and Hero. In this example, and the one on the previous slide, we're using cout and cin, but we can use other streams as well as redirect cin and cout to files and so forth. Before we start, let's see why it really doesn't make sense to implement the insertion and extraction operators as member methods. Remember, when we overload an operator as a member method, the left-hand side object must be an object of the class we're overloading. This means that we would have to write Larry on the left-hand side of the output statement. While this will work, it would be very strange for C++ programmers to use in this manner, since it's not the way we use these operators with other values. The same is true for the extraction operator. So we're going to overload these operators as non-member functions. Let's overload the stream insertion operator first. You can see that this is a non-member function named operator insertion operator that has two arguments. The first argument is an output stream object by reference. This is typed as std_ostream. The second parameter is a reference to the MyString object whose data we want to insert in the output stream. Notice that the reference is constant. Also notice that the function returns an output stream reference. This is important because we want to be able to chain insertions as we normally do. It's important that we use ostream references and we don't copy the stream. Then comes the easy part. Put whatever data you like in whatever format you like on the output stream as usual. If this function has been declared as a friend function in the MyString class, then you have access to all the private data members. Otherwise, you have to use the public getters to get the information you need. And finally, the last step is to return the output stream reference. That's it. As you can see, it's very simple and very useful too. Now let's see how we can overload the stream extraction operator. Let's start by looking at the function signature. The name of the function is operator extraction operator. The function has two parameters. The first is a reference to an input stream whose type is iStream. And the second is a reference to the object we want to extract data into. Notice that since we're going to modify this object, we don't want it to be a const. So depending on the data we want to read, we can get the data from the input stream and either store it locally or store it directly in the object. In this case, we allocate a large array of characters that will hold the data we want to construct a MyString object. Then we simply create a temporary MyString object and assign it back to the object that was passed in. This assumes we have copy or move overloaded assignment operators and they're implemented correctly since we have a raw pointer. Finally, we return the iStream reference so that we can chain assign. We can do all sorts of error checking and setting and getting the state of the input stream so we have control of the data we're extracting as well as not overrunning the size of the buffer we created. Now let's head over to the IDE and implement these two operators in the MyString class. Okay, so I'm back in the IDE. I'm in the section 14 workspace in the MyString-insertion-extraction project. And what I've got here is I've got the MyString class again, and I've gotten rid of all the operators that we've overloaded previously, just so it's a bare bones class again. And the reason I did that is just to make this a little bit more readable. And what we want to do here is overload the insertion and extraction operator so we can use these objects with streams really easily. So here's a sample main that's going to test this. And you can see here I'm creating Larry and Mo as my strings and Curly as an empty string right now. And I'm outputting enter the third stooge's first name. I'm reading from standard in this case cin, into Curly. So we're overloading the add operator right there to work with my string object. Then I'm displaying the three stooges are Larry, Mo, and Curly. Again, we're using the insertion operator here that we're going to overload. And then we're going to grab all three of the stooges' names. So we say enter the three stooges' names separated by a space, and we'll type in whatever we like. They'll be stored into Larry, Mo, and Curly, and then we'll display them out again. Okay, so pretty simple, and you can see this main driver here looks nice now. We don't have all those .display methods that we had before. Cool. So let's go to MyString header file. And let's get started here. First thing we want to do is I'm going to implement these as friend functions. So the class is going to declare them as friends. So why don't we do that first? And what we can do here is just simply say friend and provide the prototype. So we're returning a std_ostream reference. We'll do the insertion operator first. So we've got a reference. The operator we're overloading is the insertion operator. And it's a binary operator, so we've got two parameters here. The first one is a std_ostream, and we can call this anything we like. We can call it OS or out. Typically, those are the names that are used. And we've got a myString, a const myString reference. And we'll just call that right-hand side. We'll stick to that naming convention. So that takes care of that prototype. And now we'll do the extraction operator. So same idea, friend. In this case, we're returning an input stream by reference again. And the operator is operator. And we'll be doing the extraction operator. And again, we've got two parameters. The first one is the input stream by reference. And we'll just call that in. And we've got a myString object also by reference, called it right-hand side. Notice how this one is not const, because I do want to modify that object based on what I'm reading in from the input stream. Okay, so that's it. Those are our two function prototypes. And now what we can do is we can go to the implementation file, our myString.cpp file, and we'll actually write these. I'm going to put them all the way down at the bottom here. That way I've got a lot of room to work. So let's say that this is the overloaded insertion operator. Let's do that one first. All right, so same type of function prototype, right? std_ostream reference. The operator we're overloading is the insertion operator. And we've got the same two parameters that we had before. We've got an ostream reference. And we called it OS, I believe. Yes, we did. And a const myString class by reference. Right-hand side. There we go. Okay, so now, this is probably one of the simplest methods to implement. All we're doing is we're putting on OS. Remember, this is a friend, so we can simply say right-hand side's str. That's it. If this wasn't a friend, we could use the getStr method. And then we're going to return that output stream. That's it. Pretty straightforward. Now let's overload our extraction operator. And we'll do the prototype again here. So it's a std_istream reference. The operator we're overloading is the extraction operator. And we also have two parameters, right? The first one is a std_istream reference. And we'll just call that in. And we've got the myString ref right-hand side. Again, this one can't be const because we're going to read into it or change it. That's it. So now we're going to get a string from the input stream. We need to store that somewhere. So let's create a pretty big size buffer here. And we'll do this dynamically on the heap, and we'll just store 1,000 characters. That should give us plenty of room. We could certainly do this in different ways so that we don't overrun this buffer, but let's just do it like this because it's a simple example to understand. Now we get whatever's in the input stream and we store it in buffer. Right, now we've got the buffer, it's got the data we want, and what we want to do is we want to update this right-hand side objects string based on this data, right? So there's a lot of ways to do this. One of the simplest ways to do it is just to say RHS equals myString and initialize it with buff. Okay. Now, depending on whether you've got copy assignment or move assignment, that's what's going to happen here. We've got both. So this is going to use move assignment, which is super efficient. We're just going to steal that pointer. When we're done, we make sure that we delete this temporary storage that we created in buff. And we return the input stream. Remember, this is going to return it by reference. And that's it. We should be done. Let's run this and see if we have any typos. And we do. I spelled operator incorrectly, I believe. I sure did. I'll fix that real quick. Let's see if there's any other errors down here. I think they're all related to that same error. So let's run this, and here we go. Enter the third stooge's first name. Well, the third stooge is Curly. Notice we used a move assignment, which is what we expected. That move assignment happened when I copied that object out. Now it says enter the three stooges' names separated by a space. Well, let's just give them different names. Let's say it's Frank, Jim, and Joe. So you can see three move assignments there, and it says the three stooges are Frank, Jim, and Joe. So there you go. We've overloaded the insertion and the extraction operators to work with our classes, and it really feels like it's part of the type system now. All right, so that's it for this section. The next part is the challenge exercise, so I'll see you there. Hello everyone, welcome to the Section 14 challenge. Congratulations on finishing up this part of the course. I'm in the Section 14 workspace, and you can see that I have a challenge project, and this is the basic shell that I want to talk about now. There's also a challenge solution 1 and a challenge solution 2, and I'll talk about those projects in just a second. So the whole idea with this challenge is for you to overload operators for the MyString class. Now I'm providing a basic MyString class that's got all the constructors, your move constructors, your assignment operators, and I've even overloaded the insertion and extraction operators just to make it easier for you to test your code. So let's talk about this challenge. The purpose of the challenge is for you to gain experience overloading operators, and I would recommend that you do this challenge twice. That's why we have two solutions here. The first time, do it by overloading the operators using member functions, and then start a new project and do the same thing, but this time use non-member functions. Okay, so let's talk about some of the operators that you could overload. Now, I'm just giving you an example here. You can certainly do whatever you like, whatever makes sense to you, as crazy as you like. This is just to learn, so be as creative as you like. But here's a couple of examples. We've already done the unary minus. We've already done the unary minus in the slides and the examples. All it does is makes a string lowercase. Here's the example for equality. We want to compare two strings, S1 and S2. Now, obviously, this will call S1 dot operator, the equality operator, with S2. Right? And this is assuming the member method. So remember, all of these operators that we're talking about get mapped to some function, whether it be a member function or a non-member function, just as we talked about in the class. So that's the equality operator. Then we're also going to have the not equal operator, which just checks to see if two strings are not equal. So in the case of S1 being Joe and S2 being Frank, this will return true because they're not equal. Then we've got the less than and greater than operators, which just test strings lexically. So, for example, if I've got Frank and I've got George, Frank will be less than George since F is less than G. You get the idea. Just basic string comparison. We can also do the greater than and equal to or less than and equal to. I'll leave those up to you if you choose to do them. We've got concatenation, which we've already done. But again, I haven't done any of these so that you can get experience doing them. I'd recommend that you try to do them by yourself without going back to the slides and looking at the code we've written. That way you get a little bit, better feel for how to overload the operators and how they work with the code. We've got the plus equal operator. This is an interesting operator because it's S1 plus equals S2. So this is the same as S1 equals S1 plus S2. Okay. Then I've got this operator here, and this one may be a little confusing, so I'm going to take a second to talk about it. The idea here is that we have S2 times 3, and this is an integer here. And the idea would be if I have S2 being ABC, then S2 times 3 is going to give me 3 copies of ABC. It's going to repeat that string, whatever it is, n times, where n is this guy right here. So this can be a pretty handy operator. So S1 equals S2 times 3. What's going to happen is you're going to get ABC, 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 and then it gets assigned to S1. Okay, so the last one is the star equal operator. Here we're going to repeat the string on the left-hand side n times. So it's really simple. So if S1 is ABC, then S1 star equal 4 gives me 4 ABCs. Not 5. We're not really assigning back to the original S1. If you want to do that, that would be perfectly fine. But in this case, it's really easy to think, repeat S1 4 times and store it right back in S1. So it's pretty handy. And then the last operators we'll talk about are the increment and decrement operators. I haven't really talked about them too much in this class, but I'll talk about them now. And the idea here is that, remember, these are increment and decrement operators, and we have pre and post versions of each one. Now, assuming that we've got member versions, and that's what I'm talking about here, member method versions of these are the semantics for this. You'll notice we have operator plus plus, and then we've got operator plus plus with an int. Okay, that int is not used. It's not even named. It's just a placeholder. And the compiler is using that behind the scenes to be able to tell the difference between these two prototypes, if you will, because otherwise they'd be exactly the same and it wouldn't know which one to call. Okay. So this guy right here is the pre-increment. And the way that this works is the semantics are really clear. You do whatever you want increment to do. I'm making it make all the characters uppercase in the current object. And then you return this because you're actually modifying that object before you go back to the caller, right? That's what pre-increment does. Now the semantics for post-increment are a little bit different. And let me just scroll up just a little here so you can probably see it a little more clearly. Here we go. Now the semantics for the post-increment are a little bit different. We need to make a copy of what we've got now. Then we call operator plus plus. Notice that this doesn't have an int in there, right? So we're calling pre-increment. That's really important. If you call post-increment, you're going to end up with a recursive loop here, and you're never going to get out of there. So what we're doing is we're incrementing, we're doing a pre-increment, and then we're returning this temporary object that we saved, which is the old copy, right? And that's exactly what the whole idea with post-increment means. So that's the semantics of that. And then the rest is pretty straightforward. Have fun. Think of some other operators that might be useful. It doesn't matter if they make sense or not. This is all about learning how to overload operators, so be as crazy and creative as you want to be. Some hints. Take advantage of the stood string compare function for the equality operators. Remember that guy returns 0 if they're equal, negative something or positive something if they're greater than or less than. I'll let you guys look that up so you can learn about it. Another thing is the plus equal and star equals operators should return a ref. Okay, that's really important because we want to be able to chain and we don't want extra copies. Finally, when you're doing plus equal and star equal, rather than duplicate all your code again, use plus and star. We've already used those operators. We've already implemented them. And if you do that, these operators, when you go to overload these operators right here, the code really becomes almost trivial. It's just a line or two of code. It's really, really straightforward. One more thing I want to mention is when you do your increment and decrement operators, make sure that the pre-increment right here returns a ref, and make sure that the post-increment does not return a ref. It should return a myString by value. Okay, so that's basically it. Let me go over the myString class so that you can see where the starting point is. This should be really familiar now after this section. There's the myString class. You can see that I've overloaded the insertion and extraction operators as friend functions. Here's my string class, and it's got nothing that you wouldn't expect, right? It's got all the constructors, the move constructor, the assignment operators, both the copy and the move, and your getters and your display. You shouldn't even have to use display anymore because now we've got this guy right here. Okay, so that's about it. If you look at implementation, again, it's exactly like we've done in class. The one thing that I have done is I've commented out these output statements using copy assignment, using move assignments, but I left them in there in case you want to uncomment them and trace your code, or you can use a debugger to trace your code. I'll leave that up to you. The last thing is, here's the main. Here's a real sample main, and I've commented the entire main out so that you can uncomment as you go or create your own test cases. And here's some simple test cases for this. By no means these are exhaustive, but they'll certainly begin to test your overloaded operators. So let me go through a couple of them. You can see right here, I've got a string A Frank, I've got a string B Frank. They're the same string, right? So in this case, I'm comparing A to B. I expect that to be true since they're both Frank. And I'm asking, is A not equal to B? Well, that's false because they are equal, right? So what you see over here in the comments is what I expect as output. Now we create B as George. Remember, A is still Frank. Are A and B equal? No, they're not. Is A not equal to B? That's correct. Is A less than B? Well, A is Frank, B is George. The F comes before the G, so this is true. Is A greater than B? This is false. You get the idea. So these are just some sample test cases that you can use along the way. And then I've got some other ones that are testing the negation operator right here, the unary minus, right? So S1 is Frank, and then I'm just saying S1 equals minus S1, which makes S1 lowercase. So when I output it, I expect Frank in lowercase. There's my concatenation operator. Right now, Frank is lowercase. That's S1. I'm just adding a bunch of asterisks to the end, displaying it. That's what I expect. I'm doing it again, but this time I'm using plus equal, which just means add these dashes to the left-hand side. Well, the left-hand side is this guy right here. So you can see the dashes being added right here. Okay, here's another example. S2 is 1, 2, 3, 4, 5. And what this says is repeat S2 3 times and then store it into S1. So when I display S1, I'm seeing 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 3 times. And I think there's a couple of more test cases down here that we can talk about. And again, I encourage you to come up with your own test cases and write some tests that really test this and exercise the code so you can be sure that it's working correctly. Here's another one. S3 is A, B, C, D, E, F. And the semantics of this one just says, hey, repeat whatever's on the left 5 times. So whatever's on the left is A, B, C, D, E, F. So we're going 1, 2, 3, 4, and 5. Okay. Now here's some tests with the increment operators. I haven't done the decrement operator. I'll leave that totally up to you. We already have a unary minus that makes it lowercase, but you could do whatever you like. Remember, we're programmers. We can do anything. So you can make that decrement operator behave however you like. So let's take a look at this. My string S is Frank, and then I'm doing an increment, in this case, a pre-increment. Remember, when we have plus plus S or S plus plus all alone on a line, it means exactly the same thing, right? The pre and the post don't mean much. It's just increment S. So in this case, you can see S is Frank with a capital F. Then I'm saying pre-increment S. At this point, when I output S, I expect all uppercase characters, which is what our semantics say. Over here, I'm decrementing S using unary minus, so I'm putting it right back to lowercase. You could do something like minus minus S if you like to do the same thing as the unary minus, but again, I'll leave that up to you guys. And now I've got result, and here I'm saying result plus equals, pre-increment S. And remember, S right now is Frank, lowercase. That's what S is. So I want to pre-increment S. That means I want to make S uppercase and then assign it. That's what the pre-increment does. Make S uppercase, then assign it. So when I display both those values, I expect them both to be uppercase, and that's what's happening here. And let me scroll up just a little bit, right around line 54. And in this case, we're doing a post increment. Again, here it's the same as the pre-increment, so I expect Frank to be uppercase. Now I make Frank lowercase again, so S is Frank in lowercase. And now what we're doing is result equals S post incremented. So what we do is first we assign S over to result, then we increment S. So when I assign S over to result, result should be lowercase Frank, and you can see it is right here. And S should be now uppercase Frank because I just moved it over. Okay, so there you go. That's a quick intro to the challenge. This could be a pretty long challenge. Take it one step at a time. Do the operators, do the easy ones first. I would suggest to do the equality operators first because they're pretty straightforward. And then make sure that you do your star operator, which means repeat in this case, and your concatenation operator. Do those before you do plus equal and star equal. That way you can take advantage of them and really make the code much, much simpler. Okay, so I'll be back. Have a go at this, and when you're done, you can come back, and solution 1 will be the version where we've got member methods, and solution 2 is the version where we've got non-member methods, or basically non-member functions, global functions. All right, so have fun. Good luck. Hello, everyone. Welcome back. I hope you had fun with this challenge. It can be a very tough challenge sometimes. You've really got to understand what's going on with returning references, returning values, const correctness, and so forth. So let's go through this solution. I'm in the section 14 workspace in the challenge-solution 1 project. And here's one possible solution to this challenge. There's obviously a lot of different ways to achieve the same result. First thing is, I'm in the mystring.h file, and you can see here the prototypes for the operator member methods. Remember now, this is the version where we're implementing all of these operators as member methods. So right away, we've got a little bit of an advantage in the sense that since we're member methods, we have access to all the private information. So here we go. We've got our unary minus that makes the string lowercase. We've got our concatenation operator. And remember, because we've got member methods here, this will expect nothing, right? There's nothing in the parameter list for a unary operator because this object is the operand. In the case of a binary operator, there's only one item to the right in the parameter list, not two. With non-member functions, it's different. We'll have two. Here is my equality operator, my not equal operator. You can see they return booleans, less than, greater than. If you chose to do less than or equal to, greater than or equal to, that's great. And then I've got my plus equal operator that expects a right-hand side string, obviously. And then the left-hand side we're assigning back to. That's my concatenate and assign. There's my star or repeat operator in this case, where I want to repeat a string n number of times. There's the star equal operator. And then we've got our pre-increment and post-increment operators that will simply make a string uppercase. Notice the pre-increment returns a reference. The post-increment returns my string by value. Okay, so there you go. And let's go and see the implementations for these. And they should be really straightforward. It's pretty much what we've been used to doing. So let me start right here at the very beginning, right here on line 94. We're looking at equality. So let's take advantage of that string compare function, right? So we're going to compare this string with the right-hand side object string. And if they're equal to 0, then they're the same. The not equals is exactly the same, except I'm just putting a bang in here. I'm just saying, I'm negating that result. We could certainly call this guy, but it's simple enough just to negate what we get back here. The less than is the same idea. I'm using stood string comp again, and I'm checking to see if the value returned was less than 0, and I'm returning that result. Greater than, exactly the same way. So you can see how trivial these methods are to implement because the stood string comp function is really doing all the work for us. Now, the make lowercase, we saw this in the slides, and we saw this in some of the code examples that we did as well. What we need to do here is allocate a character buffer right here, an array of characters on the heap. That's the length of the string that we're in question plus 1. Then we need to copy the string over to buff, and then just loop through that buffer area and basically make all those characters lowercase, right? And we're using the stood2lower function right here to simply make the lowercase version of that character. I'm creating the temporary object, which I'm returning. And don't forget to delete the buffer as we mentioned in the slides. Otherwise, we'll leak that memory, and that's not something we want to do. The concatenate method is very, very similar. We're creating an area on the heap. This time it has to be big enough for both strings plus 1. So we're taking the length of str and then the length of right-hand side str and adding 1 to them. I'm copying the string to the buffer, and then I'm concatenating the other string, the right-hand side string, to that, creating a temporary object and returning it, and deleting my area again. Very, very common pattern that you can see. Now let's talk about plus equal. Since we've already overloaded the concatenation operator, let's take advantage of that. So you can see this basically becomes really one line of code. The return doesn't even count because we've got a return. So what we're saying here is that the current object is equal to the current object plus the right-hand side object, right? So this right here will call this operator that we've already overloaded and take care of everything for us. So this becomes a very trivial method once we've overloaded the concatenation operator. Here is the repeat. And what I can do here is I can take advantage, because remember, multiplication or repeating is just a bunch of additions. So what we can do here is we can take advantage of that. So we can create a temp object, just an empty temp object, and then just loop n times and add this to the temp object, right? Which is exactly what we expect. We're incrementing this so many times. And then we just return the temp object in this case. We could do it all in code. You can do it like that if you like. One's going to be a little bit more efficient than the other, but this works really well, and this is very, very readable and modifiable code, which is my preference right here. Here's the repeat and assign. Same idea as the plus equal. This is the star equal. So this equals this times n. We're going to call the overloaded star operator, or repeat operator in this case, to do it all for us. So this method becomes trivial again. Okay. And now let's take a look at the last couple of methods here, the pre-increment and the post-increment. They both make the string uppercase. The difference is in the semantics. So let's take a look at this one right here, pre-increment. This one is dead simple. We've got an object. It's got an str pointer that points to a character array on the heap. To do is loop through that character array and make everything in there 2-upper. That's it, and then we return the current object. There's no need to copy anything, move anything over. It's the same string we're pointing to. We're just simply making it uppercase. And in the case of the post increment, remember the post increment is using that int right there, which is just a placeholder. It's unnamed. We don't even use it in here. It's only used by the compiler behind the scenes. This returns an object by value. So what we're doing is we're making a temporary copy of the current object. That's what this is doing right here. Then we're calling the pre-increment function, this guy right here. That's going to increment that string, make it uppercase in this case, and then we return the temporary object that we saved. That was the old value. So these are the semantics for post increment. It's going to be a little bit different than the pre because I've got to return the old value, right? That makes sense because what we're assigning is the value, then we're incrementing the string. So there you go. That's a real simple implementation for all of these operators. It may have taken you a while. That's okay. That's part of the learning process. I remember when I first did operator overloading, it's hard to wrap your head around whether you're returning references or values and what exactly is going on here. The last thing we'll do is let's take a look at main, and you'll see some test cases here. And what I'd like to do, I'll just run this real quick. And right there is our output. And then it says enter a string to repeat. So let me just enter a string that looks like -00 I'll put 3 zeros, just something that we can really see. And this is testing the extraction operator as well. And how many times would you like to repeat it? Let's say I want to repeat it 5 times. And there we go. And I'll get back to this output in just a second. But let's go back to our main here and walk through this. You can see right here that I've got my string A, which is Frank, my string B, which is Frank, and I'm saying is A equal to B. And this will print out true or false because I've set this modifier right here on the stream. So A obviously is equal to B, so we expect a true, and that's what we have right here. Is A not equal to B? Well, that's false, so we get the false. And then we set B to George, and we use some of the other comparison operators in addition to the ones we just did. So in this case, Frank is definitely not equal to George, right? So we expect this to be false, which it is right here. Is Frank not equal to George? That's true. Is Frank less than George? That's true. And finally, is Frank greater than George? That's false. So you can see that output right over here. Okay. Now we'll get to some other ones. In this case, I've got S1 is Frank, all uppercase. And I'm using the unary minus right here to make it all lowercase. And then I'm outputting S1. And so you can see we expect lowercase Frank, and that's what we have right here. The next is using the concatenation operator. So remember S1 is lowercase Frank, and we're just saying tack on 5 asterisks to that. Concatenate 5 asterisks to the end of that. So we expect this to be Frank followed by 5 asterisks, and you see it, the output right there. And then we're doing it again, except this time we're using plus equals. So I'm saying S1 plus equals, I think 5 dashes again. In this case, dashes, not stars. So what we expect is S1, which is right here, Frank 5 asterisks, and we want to append those dashes to it. So the output is something like this, is what you see right here. Okay, now we're going to use the repeat operator right here. We're simply saying S2 is 1, 2, 3, 4, 5, and give me 3 copies of that and assign it to S1. So what we expect is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, just what we see right here. Okay, let me scroll this up just a little bit so we put all this on the same screen. So we're right about, okay, so that's better. So now I've got S3 is A, B, C, D, E, F. And all I'm saying is give me 5 copies, in this case, of S3, and just put it right back in S3. So we expect 5 copies of A, B, C, D, E, F, and that's what we're getting here. You can see the 5 copies of that string. Now we're using the insertion and extraction operators. We're testing those. So we've got a couple of variables here, repeat string and repeat times. And we're just simply asking the user, enter a string to repeat. And we're using the extraction operator to read that right into repeat string. That's our own overloaded extraction operator. So I typed in dash, 3 zeros and a dash. And then how many times would you like me to repeat this? I entered 5 times. And I simply wrote repeat string star equals repeat times. So give me 5 copies of that. And then I'm displaying it right here. 1, 2, 3, 4, 5 copies of that. Then the next line just gives me 12 copies of what I just did. So that's going to give me 5 times 12. It's going to give me 60 of these guys printed out here, which is just a really simple test. And then finally, the last tests for the concatenation operator are right here. I've got repeat string is just repeat me. And then I'm simply outputting repeat string plus repeat string plus repeat string. So I expect 3 copies of that to display. And there they are. Repeat me, and repeat me again. Okay. There we're chaining the concatenation operators. And notice that here we're creating actually a temporary unnamed. So you can uncomment the move assignments and the move constructors, and you can see how that's happening efficiently. Here we're saying repeat string plus equals repeat string plus times 3. So we're basically adding this time, right? So we're taking this repeat string, which is repeat me, give me 3 copies of it, and then adding it right back to repeat me, which had 1 copy in there already. So we expect to end up with 4 copies. We have 1, 2, 3, and 4 right here. And then the last several test cases are the post and pre-increments. So we'll do the pre-increment first. In this case, I've got Frank. Let me scroll that down just a little bit right there. So in this case, I've got a pre-increment. My string is Frank with an uppercase F. And I'm saying pre-increment S. So I expect Frank to be uppercase when I output it, and that's what I'm getting here. I'm setting S back down to lowercase and outputting it right there. I'm saying my string result pre-increment S. So when that happens, I expect both S and result to contain the uppercase Frank, which is exactly what's happening here. And then finally, we'll test the post increment where we're setting S to Frank and just simply incrementing S. We should get, remember, post and pre-increment all alone in the statement mean the same thing. So in this case, I've got Frank as uppercase, which I'm displaying. I'm making Frank lowercase, and then I'm testing the post increment in this context here, which means assign the lowercase version to result and then increment S. So result we expect to be lowercase, S we expect to be uppercase, and there you go. Okay. So a lot of talk with the test cases, but they're important that you understand what they're supposed to do. When we look at the challenge solution 2, we won't go over these again since we went over them here. But that's pretty much it. Implementing these as member methods is pretty straightforward. It's just a matter of understanding, when we're changing str and we've got the right-hand object as well, do we return a reference? Do we return by value? And that's it. If you have questions, please let me know. Hello everyone, welcome back. In this video, we'll go over the challenge solution 2. This is the solution for the overloaded operators using non-member functions. So I'm in the section 14 workspace in the challenge-solution 2 project. And you can see my header file now. From the private modifier down, it's exactly the same. The only thing that's changed is that I've declared prototypes for my overloaded operator functions, and they are all friend functions. Now, we don't have to do that. We can certainly not have friend functions and work through getters and setters and so forth. But for the purposes of this video, I'm making everything a friend, so I've got access to everything that's private in this class, which is really just that string pointer right here. Okay. Now, as you can see, when we have something like operator minus, in this case, where we're overloading the unary operator, there's exactly 1 item in the parameter list. And when we have something that's binary, we've got 2 parameters in the parameter list. So it's a little bit different from using member methods. And that's about it. Now what we do is we basically have to implement these functions, and you'll see they're very, very straightforward. Same idea as with the member methods. So let's go to the implementation file here. And we'll start with the equality operator. Now we don't have, remember, in all of these cases, we no longer have a this pointer. There's no object dot operator method because they're non-member functions. So we don't have that this pointer. But we do have another object. And in this case, we have left-hand side and right-hand side. And all we want to do is compare the left-hand side string with the right-hand side string. And you can see that we're doing that right here in the string compare function. We're comparing left-hand side string to the right-hand side string. And if we get back a 0, they're the same. And that's what we're returning. So we're returning true false here. Same exact idea. The not equal operator is exactly the same thing, except I'm negating the result right here with the bang. For the less than and greater than overloaded operators, you can see that the code is almost exactly like it was in the member method version, except that I don't have a this on the left side. I've got an LHS or left-hand side object. Okay, so let's take a look at make lowercase. In this case, In this case, this is a unary function, so I've just got one argument right here. And what I'm doing is, same thing I did before. I create an area in memory to copy that string into. And what I'm going to do is make it lowercase, and that's what I'm going to do here. I've allocated enough space for that object string's length plus 1. Then I copy that object string character by character into buff. And then I simply loop through buff and make each character its lowercase equivalent. When I'm done with that, I construct an object that I'm going to return right here, and I construct it based on buff. Return it, and don't forget to delete the buffer as we always do so we don't leak memory. The concatenation operator, same idea. I've got the left-hand side and the right-hand side. So obviously you're going to have left-hand side plus right-hand side. So we need to allocate another character buffer here. That's the length of both those strings added together plus 1. So you can see here we have left-hand string. Here we have right-hand string. We copy the left-hand string over, and then we concatenate the right-hand string onto that. We create the new object here based on that new string that's concatenated now, and we return it, and of course we delete the buffer as well. That's it, really straightforward. Now they get really, really simple to implement because we've got our plus equal, right? Our concatenate and assign. Well, we can implement that based on our concatenation because plus equal simply means left-hand side equals left-hand side plus right-hand side. So we can express that directly, which leads to very, very readable code here. The repeat operator or the star operator that we're overloading, same idea. Remember, repeating something just means adding it over and over. So we'll take advantage that we've already overloaded that concatenation operator right here on line 44. We're using it right there. So given n, we're just simply going to loop that many times and say temp equals temp plus left-hand side. Do it again and again and again. And we're just basically tacking on that string to itself over and over and over. When we're done, we return temp. Our star equal operator or repeat and assign operator works the same. In this case, it's a binary operator. It expects an object and then the star and then an integer is how many times you're going to repeat it. So we'll do the same thing. We'll take advantage of the fact that we've already overloaded the repeat operator or the star operator in this case. We'll simply say left-hand side equals left-hand side star n. That will call this. It will take care of it. And then we return left-hand side so that we can keep assigning. And the last two that are left are the pre-increment and post-increment operators, which just make the strings uppercase. So the semantics for the pre-increment is simply just increment that string. It's really straightforward. The string belongs to obj, right? Remember, this is a unary operator, so we only have one object here. And obj has an str pointer that points to a character array on the heap. So all we're doing is just looping through that character array, one item at a time, one character at a time, and we're setting the ith item of that object string to the uppercase equivalent of it. And then we just simply return the object when we're done. So you can see we're actually modifying obj here, which is exactly what you would expect with a pre-increment. So the post-increment is very similar. We need to keep a copy of the original object. So we're doing that right here. We're creating a copy temp based on object, which is the one that's being incremented. Then I'm doing a pre-increment of object, which takes care of making all the characters uppercase. And then I'm returning the old object. So you can see that this line right here actually modifies the current object. And this line right here returns a copy of the original object, which is exactly what the semantics are of post-increment. I wrote a comment here, as I mentioned before, make sure you call pre-increment and not post-increment. If you call post-increment, this method here will be called over and over recursively, and you'll never be able to break out of it. So that's it. If we run this, we should have exactly the same output as we had before. Let's try it. Enter a string to repeat, and we'll do the same string I entered before, dash 3 zeros and a dash. And I believe I said 5 last time. I'll do that again. And there we go. We've got our 5000 strings. We've got 60 of these now, and the rest of the code is exactly the same as it was. All right, so congratulations. I hope you did well on this challenge. You can say now that you're no longer C++ beginner programmers, that's for sure. Yeah, you've learned a lot about the way C++ works behind the scenes, operator overloading, the constructors, the move assignments, the regular copy assignments. So you've learned a lot. The next step is to learn about inheritance and polymorphic functions, and that's where we're going to go. And I should mention one last thing is when you look at these test cases that I created, these aren't really test cases. They're just little pieces of code that exercise some of those methods that we wrote and functions that we wrote. When you do testing, you really want to do proper testing using unit testing, using some frameworks such as Unit Test ++ or something like that. So keep that in mind. We're doing this just to keep it simple and not have to learn other frameworks in order to learn this framework. So I'll see you in the inheritance section. In this section, we'll learn about one of the most useful features of object-oriented programming languages, inheritance. Conceptually, inheritance is easy to understand. However, inheritance in C++ can be very complex. We'll keep it simple in this section so that the basics of inheritance in C++ are clear and you can have the foundation to study more advanced concepts in more advanced courses. First, we'll look at what inheritance is and why it's so useful. Think reusability. And then we'll discuss some of the terminology and notations used when talking about inheritance. Aggregation is also a reusability mechanism, and we'll see the difference between inheritance and aggregation, since many times we can use aggregation instead of inheritance to achieve what we want and avoid unnecessary complexity. Then we'll get into the syntax of inheritance in C++. We'll learn how to derive one class from an existing class and discuss the 3 types of inheritance provided by C++. You may recall when we talked about the public and private class access modifiers in section 13, I mentioned that there was a 3rd type of access modifier named protected. Well, protected is used in the context of inheritance, and we'll see how it can be useful in that context in this section. Then we'll look at constructors and destructors and see how they work when we've got inheritance hierarchies. With inheritance, we can create new classes that modify the behavior of their parent classes. So we'll see how that works and how it can be useful. Finally, we'll talk about what class hierarchies are, and we'll do a short introduction to multiple inheritance. Once we understand the basics of inheritance in this section, the next section will really open up the power of C++ when we talk about polymorphism when it's used with inheritance and polymorphic methods. So let's head to the next video and see what inheritance is all about. In this video, we'll see what inheritance is all about. In object orientation, inheritance provides a method of creating new classes from existing classes. These new classes contain the data and behaviors of the existing classes. So, as you can see, that allows us to reuse or inherit data and behaviors that already exist. More importantly, we're reusing behaviors that have been tested and have already been used in existing applications. That's great, but it wouldn't be very useful if I only inherited data and behaviors and that's it. But with inheritance, we can modify the behaviors however we like to make our newly created classes unique. So the new class is based on an existing class, but we can tweak it so that it does exactly what we want it to do. And we can do this without modifying the source code of the original class we're reusing. This is important since that class has already been tested and it's probably being reused by other applications, so we really don't want to modify it at all. Of course, inheritance must make sense. We don't want to reuse a class employee and create a new class planet that contains the data and behaviors of an employee. Let's see some examples of classes that are related somehow. In many applications, when you're designing your solution, you can identify classes in your application that are related to one another. Sometimes the relationship is clear, and other times the relationship might be less clear. This slide provides some examples of related classes. In a game application, we might have player, enemy, level boss, hero, and superplayer classes. These classes may have attributes in common such as health, XP, their position in the game world, and so forth. In fact, maybe the classes are all specializations of that player class. In a banking application, you might have different types of accounts. Some may have specialized business rules for withdrawal, deposit, minimum balances, interest rates, and so forth. But again, maybe all accounts have a balance and provide the withdrawal and deposit behaviors. Usually we can find commonality among these classes, and we can leverage that. In a graphics or drawing application, we may have many different types of shapes that we can draw, such as lines, ovals, circles, squares, and so forth. Depending on our application, maybe we can identify common attributes that all shapes have. Perhaps their color, they must be drawable, you should be able to rotate and transform them. And as you can see in the last example, maybe we have an application for a university personnel system. You might have person, employee, students, faculty, staff, administrators, and so forth. You get the idea. Related classes are all around us when we develop software. Sometimes it makes sense to extract out common elements of related classes and model them on their own so we can reuse them. Let's look at the account classes in more detail. Here we can see that our application has several different types of accounts. We have a basic account that has a balance and a way to deposit and withdraw funds. We also have a savings account object that also has a balance, but an interest rate as well. And the deposit and withdraw behavior might be a little different from those in the account class since they have to consider the interest rate. A checking account also has a balance, but maybe you have to keep a minimum balance and there are per check fees. So the deposit and withdraw behavior for the checking account will be different from both the savings account and the regular account. Finally, maybe we have a trust account that has a balance and the deposit functionality just like an account. But the withdrawal only allows 3 withdrawals per year of a maximum of 10% of the account balance. You can see that these types of accounts are very different, but they also have some common attributes and behaviors. Let's see how we could model these accounts without any inheritance or any reusability. What we could do here is we could create 4 independent classes: account, savings account, checking account, and trust account, and implement them all totally independent from one another. Sure, this will work, but we'll surely have code that's duplicated across these classes since some of the behavior and some of the data will be common. Let's see how we can use inheritance to allow us to reuse the account class. We'll look at proper C++ syntax for inheritance in a few videos. For now, let's just look at this from a conceptual view. We have an account class that models a balance and provides a simple implementation for withdrawal and deposit. Now we can use inheritance to create a new class savings account based on the account class. So the savings account will inherit balance and the implementations of withdrawal and deposit provided by the account class. And the idea is that now we simply add the interest rate attribute to the new savings account class and implement its own version of deposit and withdrawal. The same idea applies to the last 2 examples. A checking account is created using the account class as a base, and then it adds what it needs and modifies the behaviors to meet its requirements. Finally, the trust account adds an interest rate and implements the logic in the withdrawal method that supports the business logic. You can see that these classes are now interrelated. In this case, the savings account, checking account, and trust account classes depend on the account class, and we have an inheritance hierarchy. In this case, it's rooted at the account class. We'll talk more about inheritance hierarchies in an upcoming video. So now that we understand what inheritance is, let's go over some of the terminology and notation used in the next video. In this video, we'll learn some of the terminology and notation used with inheritance. The terminology we use is pretty straightforward, but it's important that it's clear since you'll be using it throughout your career as a C++ developer. First, let's review inheritance. As we've already seen, inheritance is the process of creating new classes from existing classes. It's a mechanism that allows us to reuse existing code. When we use inheritance to create a new class, there may be several classes involved. In this course, we'll mainly talk about single inheritance. That is, when we create a new class based on another single class. Multiple inheritance is when we create a new class from 2 or more other classes. The classes that are involved in the inheritance relationship also have terms associated with them. The base class is the class being extended or inherited from. This class is also referred to as the parent class or superclass in the inheritance relationship. The derived class is the class that's being created from the base class. This class will inherit the attributes and operations from the base class. And this class is also referred to as the child class or the subclass. You can see in the diagram the commonly used notation used to express this inheritance relationship. We draw a solid line between the base class and the derived class with a closed, unfilled arrowhead or triangle pointing to the base class. This is a UML class diagram and can also show much more information about the classes we're modeling. A very important concept to understand is that of an is-a relationship with object-oriented programming and inheritance. When we use classic or public inheritance, our derived classes are generally subtypes of their base classes. This implies an is-a relationship. So a circle is a shape. A savings account is an account. This very simple concept will provide us with a great deal of power. We'll learn how to leverage this is-a relationship in the next section of the course when we learn about polymorphic functions. Generalization is about combining similar classes into a single, more general class based on the class's common attributes. The more general class is obviously more abstract and can therefore potentially be reused more easily. Specialization is the opposite of generalization. This is about creating new classes from existing classes, and these new classes generally add attributes and operations to the already inherited ones. As programmers and designers, we use both generalization and specialization to create inheritance hierarchies. Inheritance hierarchies is how we organize our inheritance relationships so that we can more effectively organize and reuse our code. Let's see a simple example. In this example, we have classes A, B, C, D, and E, and we have public inheritance. That is-a relationships between derived and base classes. You can see that class A is not being derived from any other class. This class is often referred to as the root class in the hierarchy. B is derived from A, C is also derived from A, D is derived from C, and E is derived from D. You can see the class hierarchy in the diagram. Notice that the higher up we go in the hierarchy, the more general our classes are, and the lower we go in our hierarchy, the more specialized they are. Also notice the is-a relationships. In this example, B is an A. C is also an A, since they're both derived from the class A. And E is a D, because E is derived from class D. Now notice that E is also a C, since inheritance is transitive. In fact, in this example, E is also an A. However, class B is not a C. There is no inheritance relationship directly between B and C. Let's look at a more concrete example. In this example, we have a root class person that's the most general or abstract class in this class hierarchy. We can see that student is derived from person, so a student is a person and inherits the attributes and operations of the person class. We also see that employee is a person, and faculty, staff, and administrators are derived from employee, so they are employees. In fact, they're also persons. But notice that a student is not an employee in this class hierarchy. Also notice that the is-a relationships are not bidirectional. For example, a person is not necessarily an employee because they could be a student. You can see how useful a class diagram can be since it provides a high-level structural overview of the classes and their relationships. In the next video, we'll look at another way of reusing classes in C++ called composition and see how it differs from inheritance. In this video, we'll look at how we can use both inheritance and composition to reuse existing code in our projects. We've already seen what public inheritance is and how it can help us create class hierarchies that provide general and specialized functionality. Public inheritance creates an is-a relationship between the derived and base classes, and with inheritance we automatically inherit all of our base classes' attributes and operations. And we can see examples like an employee is a person, a checking account is an account, a circle is a shape. However, sometimes we want to reuse existing classes, but the is-a relationship really doesn't apply. For example, suppose that all persons have an account. I can't really say that a person is an account or an account is a person, since that doesn't make sense. Instead, we can use composition to model this relationship. Composition creates a has-a relationship between classes. For example, a person has an account, a player has a special attack, a circle has a location. You get the idea. Using a combination of inheritance and composition, we can express complex relationships between classes and leverage code reuse. Let's see an example. In this example, we have the person hierarchy we saw earlier. Note the inheritance relationships are modeled with the triangle pointing to the base class of the relationship. As we mentioned in the last slide, it wouldn't make sense to introduce another inheritance relationship between person and account since the is-a relationship just doesn't apply. So we use composition instead. Notice the association between person and account. It's modeled as a solid line, no inheritance triangle this time. UML provides several different types of notations to model associated classes that don't have an inheritance relationship. These are aggregation, association, and composition. You can learn more about these in an object-oriented design course, but we'll use the term composition to simply mean it has a relationship, and we won't be concerned about whether the account object can logically exist without being associated with a person object. So what we're describing here is that a person has an account. That's exactly what we want. So does a student also have an account? Yes, because a student is a person. What about a faculty member? Yes, because a faculty member is a person. Notice that we create the association at the most general class in the hierarchy where it applies, since it will also apply to its derived classes. We've actually been using composition all along. When we model class data members, we're using composition. Many times the instance variables are primitive types, so we don't include them in class diagrams, but the concept is the same. So when do you choose inheritance over composition? Many times it's easy to decide. If the is-a relationship doesn't make sense, then don't use public inheritance. Other times it's not so clear. A rule of thumb when using inheritance is to step back, look at your design, and be sure that the inheritance is appropriate. If you can model a relationship with composition, then you should consider doing that first, since inheritance adds more complexity to your design. In this case, an inheritance relationship between student and account simply doesn't make sense, so we use composition. Here's how the class person might be declared using composition. Notice that it's pretty much what we've been doing so far in this course. Composition is a common design pattern for reuse, and you'll see it used much more frequently than inheritance. But we can use both inheritance and composition together to create powerful frameworks that allow us to reuse existing code. Okay, so in the next video, we'll see what the syntax of inheritance looks like in C++. In this video, we'll learn the C++ syntax for deriving classes from existing classes using inheritance. First, we start with the class declaration for the base class. This is the class that we'll be creating the new class from. This class will have its own member data and methods, as we've already learned in this course. Then we declare the new class derived in this case, followed by a colon, then an access specifier, and the name of the base class. The access specifier can be public, private, or protected. If you don't provide an access specifier, private inheritance is used. Let's see what the access specifiers do. C++ allows for three types of inheritance: public, private, and protected. This is very different from many other object-oriented programming languages. Most other object-oriented programming languages only support public inheritance. Public inheritance is the most common form of inheritance, and it's the type of inheritance that we'll most often see used in C++. Public inheritance establishes an is-a relationship between derived and base classes, and it's the type of inheritance we'll focus on in this course. Private and protected inheritance establish a derived class has a base class relationship and is often used to implement one class in terms of another. Private and protected inheritance are beyond the scope of this course. Let's see an example of deriving a savings account class from an account class using public inheritance. Notice that we're assuming that we already have an existing account class and it's got its own member data and methods, and we want to reuse it. Now, suppose we want to create a savings account class that has much in common with an account class, but it also has some more specialized behavior. We can declare the savings account class, then provide a colon followed by the public access specifier, and finally the name of the base class. This establishes an is-a relationship between savings account and account. Now a savings account inherits everything in the account class, and it's free to implement its own specialized behaviors based on the behaviors it inherited from account. Of course, we now have two classes in our application, so we can create account objects as in this slide. We assume that we have a noargs constructor and that the deposit and withdraw methods handle deposit and withdraw funds to an account. We can create account objects on the stack or on the heap via a pointer and call these methods as we need. We also have a savings account class, so we can create savings account objects. In this case, the specialized deposit and withdraw methods of the savings account class will be used. So, as you can see, conceptually, inheritance is pretty simple. However, the nuances of inheritance can get very complex. Let's head over to the IDE and create account and savings account classes, and then we'll learn about protected member access specifiers in the next video. Okay, so I'm in the CodeLite IDE. I'm in the section 15 workspace in the deriving our first class project. And what I've done is I've created a real simple account hierarchy with two classes, and it really does nothing. It just has a couple of deposit withdraw methods that just say, hi, I'm deposit, hi, I'm withdraw, just so we can see them being called. And then what we'll do is we'll tweak this just a little bit so that we can add some attributes so you can really understand what's going on here. So let's take a look at the account class first. This is our base class. Notice that there's nothing going on here. Everything's public. We'll worry about protected and private in the next couple of videos. But right now, all we've got is a deposit method, a withdraw method, noargs constructor, and a destructor. Okay, so let's take a look at the implementation. And as you can see, the constructors and the destructors are just there with no code. Our deposit method just simply says account deposit called with whatever amount we called it with. And the withdraw method says account withdraw called with that same amount. So can't get any easier than this. So now what we're going to do is we're going to derive a savings account from an account. So what we'll do is we'll create a savings account header as well as implementation files. And you'll notice right here in savings account, we're including account.h, right? We've got to include that header file. Otherwise this class, the compiler won't know what an account is. And here's the syntax: class savings account, that's the class we're deriving, and then public account in this case is the base class. And you can see that this class is also really simple. It's got a noargs constructor, it's got a destructor, and it's got its own version of deposit and its own version of withdraw. And the implementation, again, the constructor and the destructor don't have any code in the body. The deposit simply says savings account deposit called with amount. That way we tell the difference between when the account deposit method is called and the savings account deposit method is called, and the same for withdraw. Okay, good. So now let's take a look at our main. It's just a real simple main that exercises some of these classes. So what we'll do here is we'll create an account object right here named ACC. And again, this is an account. This is our base class. This is not using inheritance right here, right? This is just instantiating a base account. And then I'm going to call it deposit and withdraw. And what we expect there is for the deposit and withdraw methods of the account class to be called. And we'll do the same thing here with a pointer, just so you can see that it works exactly the same way with a pointer. Then what we'll do is we'll do the same, but with a savings account. So we'll create this object right here, savings account, and it will be a savings account. And we'll call the deposit and the withdraw methods for the savings account. And what we expect there is to see the output saying savings account deposit, savings account withdrawal. Okay. And again, we're doing down here with the pointer. So I'm going to build and run this, and we'll take a look at the output. And then what we'll do is we'll modify these files just a little bit so that you can really understand what's going on behind the scenes. Okay, so there's my output. And I'm going to move this just next to the main so we can see exactly what's going on. Here we go. So we're creating this ACC object, and we're calling deposit and withdraw on it. And you can see right here, we're calling the account deposit and the account withdraw. That's exactly what we expect because ACC is an account object. In this case, there is no inheritance going on. I'm simply using a base class as I've used all along. And down here, you can see these last two statements right there for the account is just using the pointer. Okay, so now let's take a look at the savings account. So here's the savings account right here. And I'm creating a save account object right here, and then I'm saying saving account.deposit, saving account.withdraw. So in this case, I expect the savings account versions of those methods to be called, and you can see that that's exactly what's happening here. Okay, so again, the account is the more general class, the savings account is the more specialized class, and since we've got those methods that we've specialized in the savings account class, those are the ones that are being called right here. Okay, so hopefully that's clear. Now let me make a couple of small changes and then we'll run this through the debugger so you can see the structure of these classes. So let's go into the account class. And what we can do here, and again, I'm going to keep everything public for now. We'll change that in the next videos. What I'm going to do here is I'm simply going to create a double balance and a string name, just for a real simple name for an account. And let me include the string header. Okay, so now we're saying that all accounts have a balance and all accounts have a name. We obviously need to initialize those. I'm just going to initialize balance to 0 and name to something like an account. So we can do that in our implementation file right here. We can do it right here in the noargs constructor. We can simply say balance is 0 and name is an account or something, anything really. Okay, so that's it. So now we'll go into our savings account and we'll say, okay, a savings account will also provide its own version of functionality. Remember, this is the specialized class. So let's say that a savings account has an interest rate and it's a double. So obviously we'll initialize that as well. We don't want it to have garbage data. So we're going to come into our implementation file and we'll do that right here using an initializer list. We'll say interest rate, and I don't know, let's say it's 3% interest. Okay, perfect. Now, if we run this, we should get exactly the same output because nothing's being changed. Output statements really aren't displaying interest rate or name or anything else. So let's just be sure that it runs. There's our build, there's our run, and again, nothing here has changed. But let's take a look at this in the debugger. So let me close this up real quick, and I'm going to go back to my main. And what I want to do is I just want to put a couple of breakpoints here. We'll put a breakpoint right here on line 14 where we're actually creating that account object. And we'll put another breakpoint right here on line 29 where we're creating the savings account object. Okay. And what I want to do is debug this, and I'll start it. And I'm really not interested in the output. What I'm interested in here is the local variable. So that's really what we're going to concentrate on. So here on line 14, I'm just about ready to execute that line, and that's going to instantiate or create that account object. So I'm going to go next. Now it's created. Let's take a look at it. There's ACC. It was just created. You can see the balance is 0 and the name is an account. Remember, the name is a C++ string. Perfect. Now I'm going to come down here to line 29. I'll just keep hitting next until I get to it. And what's going to happen when I get here is I'm going to create a savings account object right here. So I'm going to press next. Now that savings account object has been created. It's called save_account. I'll refresh this and let's take a look at it. Remember what account was? 0 an account. Now let's look at savings account. Notice that savings account has an interest rate, right? That's what it brought to the table. But it's also an account because we've got inheritance. So everything that was in my parent is in me. So there's the account part of me being a savings account. And you can see that the account part of me is 0 and the account name part of me is an account. Okay, so hopefully you get some insight into what's really going on here. We really are inheriting all that information from our parent. So let me just draw this out so to be really clear. Suppose that this is ACC right here. That's ACC. That's that object right up here. And it's an account. And it has two local variables, right? Balance and name. And we're not going to worry about what they're set to. You can kind of see that over here. And it also has access to those two methods, right? Deposit and withdraw, as well as the constructors and the destructor, but I'm not worried about those right now. I'm just really concentrating on these two methods. So the account knows about its methods. Now down here, I've got a savings account. So let me create that, and I'll just draw a big box. And this is savings account. That's the name of the object. And its type is savings account. That's this guy right there. Okay. Now, savings account, remember, is an account. So it's got an account part inside it. And that account part is going to look just like this guy right here. It's going to have a balance, right? It's going to have a name. It's going to have access to those deposit and withdraw methods. I'll just write them here. And those are the deposit and withdraw methods for the account class. But then our savings account class adds an interest rate, and it's got its own versions of deposit and withdraw. Okay, so conceptually, this is really what's going on, and you can obviously see it right here. You can see that it's got the account part of it right there. Now, obviously, the methods aren't here, and the methods aren't going to be copied in every single object. They're going to be in one place. But think of it conceptually this way, and I think you'll be good to go, because this is really what's happening behind the scenes. So when we say that a savings account is an account, it sure is, right? There's the account part of me. Now, a couple of things. We need to talk about what in here is accessible to the savings account. How do we initialize the account part of us? So this is where we're headed with the next few lectures, because we really need to be able to know, what can I access from these methods? Am I able to access these guys right here or not? I'm not sure, right? It all depends on our access modifiers. And also, I need to be able to instantiate or initialize that account part of me. Okay, so that's what we'll do next. In this video, we'll learn how the class member access modifiers work with inheritance. We'll also learn about the protected class member access modifier. We've already seen the public and private class member access modifiers, and we know how they work. Well, C++ provides a third access modifier named protected. We define protected data members and methods exactly as we do public and private. We provide the protected keyword followed by a colon within the class declaration. All data and method declarations that follow the protected block will have protected access. So, protected class members are accessible to all methods of the class itself. Protected class members are also accessible by any derived classes that have been derived from the base class. However, protected class members act like private members, so they're not accessible directly from objects of either the base class or of the derived class. So you can see the protected class members act very much like private class members unless there's inheritance involved. Let's see the syntax once more so we can discuss exactly what's available to the derived class. Here you can see that we have a base class, and that base class has public, protected, and private class members. We'll use three integers, a, b, and c, each within a different access modifier, to understand how inheritance works with access modifiers in the next few slides. Since C++ provides three types of inheritance, we have to look at each type individually, since the access depends on the type of inheritance involved. In the case of public inheritance, public class members are inherited, and they're also public in the derived class. Protected class members are inherited, and they're also protected in the derived class. Finally, private class members are also inherited. However, the derived class does not have access to them. Any attempt to access base class private class members from the derived class will result in a compiler error. This is the most common form of inheritance used in C++. You can see that the rules make sense. Public is public, protected is protected, which means that no matter how deep the class hierarchy goes, the protected class members will be accessible by all derived classes. Finally, something marked as private in the base class implies that the developer of the base class doesn't want to grant access to those class members. Now let's look at protected inheritance. Remember, this is not is-a inheritance. The public base class members are protected in the derived class. Protected base class members are protected in the derived class, and private base class members are not accessible from the derived class. Finally, let's look at private inheritance. Again, private inheritance is a inheritance. So in the case of private inheritance, the base class public and protected class members are private in the derived class, and the private class members are not accessible from the derived class. This may seem confusing and a lot to remember, but it's really a very logical approach to inheriting class members. As mentioned previously, inheritance in C++ is a very complex topic. We'll concentrate on single public inheritance in this course. Now let's head over to the IDE and walk through an example using access modifiers and public inheritance in live code. Okay, so I'm in the IDE. I'm in the section 15 workspace in the protected members class access project. And what I've got here is a real simple class similar to the one that we created on the slides, where I've got a base class that I'm declaring right here, and it's got a public integer a, which I'm initializing to 0, and a method called display. I've also got a protected integer b and a private integer c, both of them initialized to 0. Now the first thing we'll look at is this line right here, line 11. Obviously member methods have access to everything in the class, so there's no problem here accessing a, b, or c, regardless of their access modifier. So this will be just fine. Something else I wanted to note was that if we have a friend of this base class, right, a friend function or a friend class, then it will have access to public, protected, and private information in this class. Okay, so let's look at this first at the object level before we even get into inheritance. Here we have a base class. Why don't we create a base object? And it's right here on line 31. I'm creating an object called base, and its class is base right up here. Okay. We've got those three integers, a, b, and c. Now let's access them all. So let's say base.a is 100, base.b is 200, and base.c is 300. Okay. Now what do we expect? Well, we've been through this before with public and private. The only difference here is protected. We expect base.a to be okay, right? It's public in base, so the objects have access to it. And we expect base.c to give us a compiler error, right? Because it's private, we don't have access to private data from our objects. This is nothing new. This is what we've learned all along. Now, there is no inheritance in here, right? Because we're only dealing with that base class right now. There's no derived class yet here. So in this case, I also expect a compiler error because as far as the compiler is concerned, the protected and private access modifiers really are the same when it comes to objects. So this object base has no business messing with B or C because they're protected and the other one is private. So if I compile this, if I try to build and run this, I should get two compiler errors, and you can see them right there on the red arrows right here. One says B is protected and the other one should say C is private. Okay, so that makes sense, right? That's working with objects. So let me comment these two lines and we'll move on now. Okay, so now let's talk about inheritance. Right here we've got our base class just as before. Now I'm creating a derived class. I'm deriving this class publicly from base, so I'm inheriting everything in base, and I'm using those rules that we saw with public inheritance. So A is public in my parent, so it's public in me. B is protected in my parent, so it's protected in me. C is private in my parent, so I inherit it, but it is not accessible. Okay, so it's important to understand that C is indeed inherited, and we'll look at that when we walk through the debugger, when we step through it. You just don't have access to it from within derived. It makes sense that it's part of you since it is part of your parent. Okay, so now, what do we have access to here? Well, we should have access to A and B, right, within our derived. We should not have access to C. So why don't we write a real simple method here. We'll just call it void access base members, let's say. And this won't do anything. We'll just access those things and see when we get compiler errors. So we're going to say A equals 100, let's say right here. Now again, we expect this to be okay because A is public in my parent, it's public in me. We also expect B equals 200 to be okay because it's protected in my parent, it's protected in me. This is a member function, it's got access to it. This is the problem here. If I say C is 300, C is not accessible. So we expect a compiler error here. Okay. Again, remember, C is there. If you need to access C or modify C, you can't do it directly from derived. You'll have to go through some getter function or setter function provided in the base class. But we'll talk about that later. So let's compile this now, and we expect to get a compiler error right there on line 28, and that's exactly what happens, right? C is not accessible. So you can see how these rules apply. Now I'll comment that out, and we'll do one last thing is we'll come down here now. And remember, so what we did was we created base object and tried to access those three data members. Then we created a derived class and saw what the access was here. Now we're going to do it from a derived object. So let's do that. Let's say derived, let's just call it D. And we'll do the same thing. We'll say D.A is 100, D.B is 200, and D.C is 300. Okay, so take a look at A. I'm accessing the A data member in the derived class. Well, let's move up here just a little bit. A is going to be public, so I should expect that to work. But look in B and C, protected and not accessible. I don't have access to protected data, and I certainly don't have access to something that's not accessible. So we expect this line to be okay, and we expect both of these to give us compiler errors right here. All right, so let's give this a build and run. And there you see everything else is clean. I'll scroll up just a little bit, and there you can see the compiler errors. And it says, just like you would expect, this is protected in this context, and this guy is, oops, sorry, I forgot a semicolon. Let me do that one more time. Make sure we get the right compiler errors. There we go. So we still got the same two compiler errors, but they're different errors now. So in this case, B is protected, so we don't have access to it. And down here, C is private, so we certainly don't have access to it. Okay? All right, so that's really what I wanted to show you in this video. You can see that this makes sense. All these protected data members will be inherited all the way down the hierarchy, so you've got access to them throughout. Okay, so the last thing I want to do is I want to put a breakpoint right here on line 42, right where we're creating that derived object D. And I want to debug this and step through it, mainly just so we can see what D looks like. Okay, so I'm right there at line 42. I'm going to step, and I've just created that object. And let's refresh this over here. And first, let's look at base. Our base object, which you can see right here on line 36, has an A, B, and a C in it. That's exactly what we expect. B and C are 0, and A is 100 because I set that to 100 on line 37, as you can see right here. Okay. But now what about the derived object? What would you expect that to look like internally? Well, it is a base, right? Because we're using public inheritance. You expect A, B, and C to be in there. And that's exactly what you have. There's your base part, and there's A, B, and C. So that derived object D has a base object within it. It seems obvious, right? But a lot of students get this confused because of that one rule that says private elements are not accessible. Somehow they sometimes think that not accessible means you didn't inherit it. And that's not the case. You can see it's really here, right? You can see that that C is there. It has to be there since you are one of your parents. So we're not deleting stuff. We're not disinheriting stuff. So we're getting everything from our parent. So just because we don't have access to it doesn't mean it's not there. I want it to be really clear on that because I see students misunderstanding that a lot. All right. So in the next video, we'll talk about constructors and destructors and the order that stuff happens in with inheritance. In this video, we'll learn about how constructors work when we use inheritance. We know that a derived class inherits data and methods from its base class. Before C++ can initialize the derived object, it must initialize the base part of the derived object. This makes sense since the derived class might use base class information during its own initialization. So, since constructors are responsible for object initialization, when a derived object is created, first the base class constructor executes, and then the derived constructor executes. Let's see a simple example with no args constructors. In this example, we have a base class that has a no args constructor that simply displays base constructor. And we have a derived class that inherits publicly from base. The derived class also has a noargs constructor, and it displays derived constructor. Now let's create a base class object and a derived class object and see how the constructors are called. First, let's create a base object from the base class. In this case, there is no inheritance involved, so we expect the base class constructor to be invoked, and that's exactly what happens. Now, if we create a derived class object, this is where things change. In this case, we have inheritance since the derived class is a base class. So C++ initializes the base part of the derived object first. And you can see on the right-hand side of the slide that the base constructor is invoked first, and then the derived constructor is invoked. Now let's look at how destructors are handled. Class destructors are invoked in the reverse order as the constructors. So the derived part of the class must be destroyed before the base part is. Again, this makes sense. So when a derived object is destroyed, first the derived class destructor executes, then the base class destructor executes. Each destructor should free any resources that its own class constructors allocated. In this slide, we added destructors to the base and derived classes. The destructors simply display base destructor or derived destructor when they're invoked. So let's create those two same base and derived objects now and see the output. First, let's look at the base class object. In this case, again, we're not using inheritance at all. So the output on the right side of the slide is exactly what we expect. First, the base constructor is invoked, and then the base destructor is invoked, and the object is destroyed. Now let's see what happens when we create a derived object. First, the derived object must be initialized, and we know that the base part must be initialized before the derived part. So you can see that the base constructor is invoked, and then the derived constructor is invoked. Now, when the object is destroyed, the opposite happens. First, the derived destructor is invoked, and then the base destructor is invoked. This order of construction and destruction occurs in the same manner whether you have 2 classes or 10 classes in the hierarchy. Finally, let's talk about a few important topics in inheritance and what is not inherited automatically. A derived class does not inherit base class constructors, base class destructor, the base class overloaded assignment operators, and base class friends. However, we can invoke base class constructors, destructors, and overloaded assignment operators from the derived classes. Sometimes you'll see a using base scope operator base directive in the body of a derived class. This was introduced in C++ 11 to allow explicit inheritance of base class constructors. There are lots of rules associated with this. For example, default, copy, and move constructors are not included. Each inherited constructor has the same access specifier as its corresponding base class constructor. If you provide an overloaded constructor in the derived class, then the base class overloaded constructor is not inherited. A base class's constructor default arguments are not inherited. So you can see there's a bunch of rules. These are just a few. However, the using statement can be useful and save a bit of typing, but I prefer not to use this feature and write out the constructors I need in my derived classes and invoke the base class constructors as needed. It isn't that much more typing, and it's very clear to programmers that come after you to modify your code exactly what you're doing. Let's head over to the IDE, and I'll show you how all this works in live code. Hello, so I'm in the section 15 workspace, and I'm in the constructors and destructors project. And what we'll do is we'll step through the debugger and we'll see exactly when these constructors are called. So we absolutely understand, the order that things happen in and what isn't inherited in this case. So here I've got a base class that has an integer attribute named value, and it's got a simple noargs constructor here that sets value to 0. It's got an overloaded constructor that expects an integer and sets the value to that integer, and it's got a simple destructor. And all of these just say what they're doing: base noargs, base int, base destructor. We also have a derived class, which is derived publicly from base, and it adds its own attribute, doubled value, which is just that value doubled, 2 times the value. And it's got its own constructors here and destructor, but I've commented all of them out for now, and what we'll do is we'll uncomment them as we go. So let's start with a simple example. We're here in the main, and let's create a base object, and we'll just call it B. Really, really straightforward. We're not using any inheritance at all here. We're not using derived. We're only dealing with base. So let's review that and make sure that that's very clear what's going on. So if I step through the debugger here, what we've got going on is, and let me move this screen over here to the right. So what we've got going on here is we're right here on line 26. We're just about to create that base object. Now what we expect is for the base noargs constructor to be called, to set that value to 0, and then to display noargs, right? And then when it goes out of scope, we expect the base destructor to be called to clean it up. That's really what we've seen up to this point in the course, and it should be pretty straightforward at this point. So let's step through, and you can see right now we're on line 26 right here. As I step through, now I'm coming up to line 11, which is our base noargs constructor. It's going to initialize value to 0 and then just simply display base noargs constructor. And that's exactly what happened. Now B goes out of scope, so we expect the base class destructor to be called. And let me step through here. There we go. Now we're on line 13, and you can see the destructor is being called, and obviously the value is 0, right? It was set to 0 by the constructor here. So at this point, we get the destructor called and our program is complete. Okay, that's pretty straightforward. Now what we can do is we can just change this just a little bit. And what we'll do is I'll comment this out just to keep it in the code so when you guys can play with it on your own. What we'll do here now is we'll just say base, we'll call B again, and this time with 100. And I'll move the breakpoint down to here. Okay, so now what we're doing is we're creating a B object, which is a base class object, and we're providing the 100 as an initializer. So what happens here? Well, in this case, again, we're not working with derived yet, so we're not using inheritance. We expect the overloaded constructor here on line 12 to execute, which expects an integer. We expect it to set the value to 100 in this case, and then just display base int overloaded constructor. When the object goes out of scope, we expect the destructor to be called. Okay, so let's do that. And we'll get these base examples out of the way so that we can definitely work on the derived examples and understand it better. Okay, so I'm here on line 27. I'm going to step through. Here I am on line 12. That's exactly what I expected. I'm providing an integer, so that overloaded constructor right here that expects an integer is called. It's going to initialize value to 100, which is what I'm passing in. And if I look at B's value, there you go. You can see the 100. Now the object goes out of scope and the destructor is called right there. So you can see the base class destructor was called. Okay, so that's real simple examples using base object. Now let's create some derived objects. So for our first example, what we'll do is we'll comment that line out. And what we'll do is we'll just simply create a derived object. We'll just call it D. And we'll provide no initialization information. Okay. So what do we expect to happen? Well, look at all these constructors here. They're all commented out. So when we don't provide a constructor, we get a default constructor, right? A default no args constructor. That's going to be called in derived. But because we're in derived and it's derived from base, we need to create our base part. So automatically the base class's default constructor right here will be called. So in this case, what's going to happen is that this value will be set in my base part, but this double value will never be set because I'm not using my own version of this no args constructor. Okay, so let's run through this one and we'll run the debugger here. And you can see what's going on here. I'm right on line 28. I'm just about to create that derived object. Now, obviously the derived object's default constructor is going to get called. It's not here, right? That's because it's compiler provided. And it's going to call the base class constructor. You can see right there. You can see how it almost really just skipped our own default constructor, the derived class. It didn't really skip it. It actually got called. It's just not doing anything because it's compiler provided. So in this case, I'm setting value to 0 and saying base no args constructor right here. And now I'm back. But now look at the state that derived is in. You see derived's base has a value 0, right? That's exactly what we expected because the base default constructor was called. But this doubled value was never set, so I've got garbage here. Okay, so hopefully that makes sense. Now, what we can do is to fix this is we can uncomment out this guy right here. So now we've just uncommented our own no args destructor. So let's run this again now. You'll see exactly what happens. Okay, so now in this case, again, I'm on line 28. I'm just about to create that derived object, again, with no information here, no initialization information. So I'll step through. This time, our own version of our noargs constructor gets called. Right? And what's going to happen right now is the base constructor gets called, because before I start executing anything in this derived constructor, the base part of me must be initialized. So you can see when I select step here, now I've invoked that base class default constructor. It's going to set value to 0 and say base noargs constructor. Then I come back down here to the constructor, which sets my doubled value to 0 and then displays that message. That happened kind of quick. I think I double clicked. So what happens here is, look at my D object now. The base part is 0 and the doubled value part is 0. Okay, so there you can see that we're really chaining here, and we're taking care of our own attributes, and that's what you really want. You want the base class to handle its value. You want the derived class to handle its doubled value. Okay, so now let's do another example here. And again, I'll comment this out, so I'll leave it in there so that you can play with it. We'll create a derived object D, and let's pass in 1,000 to it. And I'll move the breakpoint down here. Okay, so now what do we expect? Well, we expect our derived classes overloaded integer constructor to be called. This guy right here. It's commented out right now. So this won't compile, right? As far as the compiler is concerned, it doesn't know anything about this. And remember, these constructors are not inherited. If this constructor up here on line 12 was inherited, then that would be called. And we'll force that in a minute. But for now, let's just compile this, and you'll see that we do get a compiler error right here that says no matching function call. So basically, it can't find that constructor because it's not there. So let's uncomment that out and tell it that it's there. Now what do we expect? Well, now what we expect is when we execute this line here on line 29 and we want to create that object, what's going to happen is the constructor here on line 21 executes, but what's going to execute up here? What we really want is for this guy to execute, right? This one on line 12, the overloaded integer constructor. But that's not going to happen because I'm not explicitly calling it. We'll learn how to do that in the next video. What's going to happen here is that the base class default constructor right here is called. Okay, so let's walk through this. Okay, so again, I'm on line 29. I'm just about to create that D object. And you can see now that line 21 executes, right? That's my overloaded constructor that expects an integer. That's exactly right. So now the base part of me needs to be initialized. The compiler is not going to guess as to which one of these to call. So it's simply going to call the noargs version and set that value to 0. And when I step through this, you can see right there the noargs version of the constructor is being called. It's set the value to 0. You can see right there, base noargs, then the derived constructor gets called and finishes off by initializing its doubled value to 2 times x. And if you look right now at the state of this D object right here, you can see that the base is indeed 0 because that constructor took care of it. And the doubled value is 2,000. We probably wanted the value to be 1,000, not 0. But we didn't do that because we really don't know how to call these constructors yet. Like I said, we'll do that in the next video. Okay, and then obviously the destructors get called. All right, so what if we didn't have this right here? I'll comment that out. We saw that didn't compile a second ago. But what we could do is we can use a using statement, and we could just say using base. And what that will do is it will allow us to inherit the non-special constructors from my base class. And this is a non-special constructor. You can think of the special constructors as a default, as a copy constructor, that kind of thing. So now this will be inherited. So this line right here, what it'll do is, since that's inherited, it matches. So this will be called. And again, that has a problem, right? Because it's not going to deal with the doubled value. So let's run this through the debugger and we'll walk through this. And we're right here now. We're creating that derived object. You notice it compiled, right? Before it didn't compile. Well, this time it compiled because I'm inheriting this one. So it's available in my derived. So it does match that integer, right? So when I execute this, you'll see what happens is that this guy gets called right here on line 12. There you go. So control is right here now. So I'm going to initialize the base part of me to 1,000. But now look at the state of D. My base is correct, 1,000, but my doubled value never got initialized, right? because I simply inherited that. And that's one of the issues with using automatically inheriting your non-special constructors. It'll take care of initializing the base part of you, but it won't take care of initializing the derived part of you. So you really should do that yourself. And as I said, we'll learn how to do all that in the next video. But it's important that you understand this behavior first. And then I'll just uncomment these last two out, and then you'll see the whole thing happening. So at this point, let's run this one final time. So right here, we're creating a derived object D with 1,000 as an initializer. And what we expect is line 22 to be called. That's exactly correct. Now, obviously, behind the scenes, what's going to happen is the compiler is not going to guess as to which constructor to call in the base class. So it's going to call the no args. And you can see that happening right here. That'll set value to 0, display the message. Then we come back, and that will set double value to x times 2. So in this case, you can see I've got 0 and 2,000, again, which is not what I want. But then the destructors get called, and you'll see what happens here. First, the destructor for the derived gets called, and then the destructor for the base gets called. So the destructors happen in the order opposite from the constructors. Okay, now this isn't really what we want. We really would like this to be 1,000. Value 1,000, double value 2,000. And like I said, we'll learn how to do that in the next video when we learn about calling our base class constructors explicitly from the derived constructors. In this video, we'll learn how to invoke base class constructors and pass in arguments from the derived class. Remember, since the base part of a derived class must be initialized first, then we know that some base class constructor must be invoked to do that initialization. So in this video, we'll learn how to control exactly which base constructor will be used. We can determine which base constructor to be used based on the arguments that we want to pass to it from the derived class. So let's see how we can do this. In this example, we have a base class, and let's assume that that base class has a no args constructor and an overloaded constructor that expects a single integer parameter. Now we have a derived class, which is derived from base, and the derived class has a constructor that has a single integer parameter. We can invoke the base class's overloaded constructor in the derived constructor's initialization list as shown in this slide. That's it. It's pretty simple and clear syntax. In this case, we're passing the integer x to our base class constructor when it's invoked. Following this, we can have initializers for the derived class's attributes as needed. Finally, we have the code in the body, but remember, this code executes after both the base and derived parts of the derived object have been initialized. If we don't explicitly invoke the base overloaded constructor, then the no args constructor will be invoked automatically, since remember, the base part must be initialized. So let's see the complete example. Here we see the base class declaration. Pretty standard code. The base class has an integer attribute named value, and it has two constructors. The first constructor is the no args constructor, and it initializes value to 0 and displays base no args constructor. The second constructor is an overloaded constructor that expects a single integer parameter, and it initializes value to the integer x, and then it displays int base constructor. Now let's see the derived class. The derived class is derived from base using public inheritance, and it has an integer attribute named doubled value. It also has two constructors. The first constructor is the no args constructor. Note that in its initializer list, it explicitly invokes the base no args constructor, and then initializes its own double value attribute. Finally, it displays derived no args constructor. The second constructor is the overloaded constructor that expects an integer parameter. This constructor also invokes the base class overloaded in constructor in its initializer list, and then it initializes its own doubled value attribute to 2 times x. And finally, it displays in derived constructor. Note that we could have implemented the overloaded constructors as delegating constructors, but I wanted to keep the display messages clear so that we could follow the calls. So now let's create a few objects and see what's called. First, let's create a simple base object with no parameters. In this case, the base no args constructor is called. In the second example, we're creating a base object, and providing an integer initialization argument. This will invoke the overloaded int base constructor as we would expect. Now in the third example, we're creating a derived object with no parameters. This will invoke the derived noargs constructor, which in turn will invoke the base noargs constructor from its initialization list. Once the base part is initialized, then the rest of the derived noargs constructor executes. So you can see the output is what we expect. First, the base noargs constructor, then the derived noargs constructor. The last example works in the similar way. We're creating a derived object with an integer initialization argument. So the derived int derived constructor is invoked, and then we explicitly invoke the int base constructor from it. So the first int base constructor executes, and then the int derived constructor. Of course, all these objects will be destroyed by the destructors when they go out of scope. You can see that we have complete control as to which base class constructors to invoke from our derived class constructors. So let's head over to the IDE and see this behavior in live code. Okay, so I'm in the IDE and I'm in the section 15 workspace in the base class initialization project. This project looks very similar to the one we did in the previous video. However, I've spread out the code a little bit more just so it's easier to see in the debugger what's going on. And what I'm doing here is I'm explicitly calling my base class initializers from my derived class. So you can see here that I've got a noargs constructor in my derived class, and I'm explicitly calling my base class's noargs constructor right here. Similarly, in the overloaded integer constructor from my derived class, I'm calling my base class's overloaded integer constructor. Okay. That way I've got explicit control over how my objects are being created. Not just my part, but my base part as well. So let's run through some examples. We won't do the base ones because those haven't changed at all. We'll just worry about the derived ones. So in this case, let's create a derived object and we'll call it D. And we'll provide no initialization information here. So we'll run the debugger and step through it. So we're here on line 40. And we're just about to create that derived object D. Again, I've got no initialization information, so I expect my noargs derived constructor to be called right here on line 26. And if I step through it, you can see that that's exactly where I'm at. But now in this case, I'm explicitly invoking my base class constructor, also the noargs constructor. And I'll scroll up just a little bit, so it's going to be right there on line 11. So what's going to happen now is, and it's important to understand the order here, before my attributes are initialized, right? Doubled value is my attribute right here. I'm a derived class. Before my attributes are initialized, before the body of the derived constructor is initialized, the base part of me will be initialized. So in this case, when I step through, you'll see that it transfers control up to here on line 11, and the base noargs constructor is called. It'll set that value right here in the base to 0. And it will display base noargs constructor. Then I come back to where I left off, initialize doubled value to 0, and you can see that that will indeed be 0 here. Now they're both 0, right? The value in the base as well as the doubled value that just got initialized to 0 right here in the initializer list. Then we display derived noargs constructor, and our object is constructed. So when it goes out of scope, the destructors will be called in the reverse order, so let's do that. You can see right here the derived destructor is being called, and that executes, and then we come up to here and execute our base destructor right here. And we'll display that as well. Okay, so there you go. That's a real simple example of how we can invoke our base class initializers. Now I'll comment this out, and what we'll do now is we'll do the same thing, but we'll do derived D, and we'll use an initializer of 1,000. So I've moved the breakpoint to this line 41, and what we'll do now is we'll start the debugger again. And we'll walk through this example. So what do we expect in this case? Well, on line 41, we're creating a D object, which is a derived object, and we're using 1,000 as an initializer. So we expect this constructor right here on line 30 to be invoked because it expects, that's the overloaded integer constructor. So let's step through and you'll see that that's exactly what happens. But now, before we initialize our own variables, before we do anything in the body of the constructor, our base needs to be initialized. So in this case, I'm explicitly invoking my base class constructor with the variable x that was passed into me. So what's going to happen here is this constructor right here on line 14 will be invoked. So let me step through that, and you can see that's exactly where we are. The value will be set to x, in this case 1,000, and then I'll display the message. Then I come back to my derived overloaded constructor and finish off here. What just happened was that my doubled value was initialized to 2,000, and I'm just about to display this. So at this point, my object has been fully initialized, and if I look at D, you can see that the base part of me is 1,000 and the doubled value part of me is 2,000, which is exactly what we wanted, and that's the issue we had in the previous video, that we couldn't get that quite to work that way. And of course, as I destroy this object, the derived destructor gets invoked first, and then the base destructor gets invoked, and our program is complete. Okay, so there you go. That's a real simple example of how to initialize the base part of us when we're using inheritance. In the next video, what we'll do is we'll look at the way that copy and move constructors and overloaded assignment operators work with inheritance. In this video, we'll learn how copy and move constructors and overloaded assignment work with inheritance. As we've seen, copy and move constructors and the copy and move assignment operators are not automatically inherited from the base class. First, let's remember that you may not have to provide these operations at all. Depending on your class and its composition, the compiler provided versions may be all you need. However, we can explicitly invoke these special constructors and the overloaded assignment operators in our base class from the derived class if necessary. First, let's look at the copy constructor. If we need to copy a derived object, then we must ensure that the base part of that derived object is also copied. If that base class has a copy constructor, then we can explicitly invoke it in our derived copy constructor's initialization list. This is very similar to what we did with our non-special constructors in the previous video. The only part that might be confusing is that the base class constructor expects a reference to a base object, but we have a derived object in the derived class. In this case, the derived object is referenced by the variable other. So we can invoke the base class and pass in other. How does that work? Well, remember, we have is_a inheritance, so a derived is a base. And since a derived is a base, we can pass in a derived to a method that expects a base. In this case, the compiler uses slicing and slices out the base part of the derived object. Slicing can sometimes cause issues, but in this case it's fine, since what we want to do is copy the base part of the derived object. Let's see the entire process in context. In this example, we have our base class, and it has an integer attribute named value. And let's just focus on the copy constructor. We construct the new object based on the other object, and we simply copy other.value to this.value and display a message to the console. You may be wondering why we need a copy constructor at all in this example, and you'd be absolutely correct, we don't. The compiler provided copy constructor would be perfectly appropriate here. However, for instructional purposes, I'm writing the copy constructor so that we can see exactly what's being called. Okay, so now let's see the derived class. Here's the derived class. Notice that it's derived publicly from base, and it adds an integer attribute named doubled value. The derived class has its own copy constructor that expects a ref to a derived object that will be copied. In this case, we're explicitly copying the base part of other by invoking the base class copy constructor in the derived copy constructor's initialization list. Again, notice that we pass the other object, which will be sliced to yield its base part. Once we copy the base part, we can take care of copying doubled value and then display a message to the console. The move constructor works the same way. Now let's see how overloaded copy assignment works. Here's our base class again, and it has an overloaded copy assignment operator. In this method, we check for self-assignment, and then we assign the right-hand side's values to this object, and we return this object. This is exactly what we've learned already and done previously. Now let's see the derived class. Here's our derived class, which is publicly derived from base. As before, it adds a doubled value attribute. It also has an overloaded copy assignment operator. In this method, it's important that we assign the base part of the derived object and then take care of the doubled value. So after we check for self-assignment, we call our base class's overloaded assignment operator and pass in the right-hand side object that we want to assign. This will take care of assigning the base part. Then we simply set doubled value to the right-hand side's doubled value to complete the assignment of the derived part. Finally, we just return the this object. Note that if we don't explicitly call the base class's overloaded assignment operator, then the base part will not be assigned. Again, the move assignment works in a similar manner. Okay, so let's recap. Often you don't need to provide your own copy, move constructors, or overloaded assignment operators. If you do not define them in the derived class, then the compiler will create them automatically and call the base class versions for you. If you do provide them in the derived class, then you must invoke the base versions explicitly yourself. Finally, be careful when you use raw pointers and dynamically allocated memory, especially if both the base and the derived classes have raw pointers. If so, you'll likely want deep copy semantics for both the base and derived classes. So let's head over to the IDE and we'll step through this example. Okay, so I'm back in the IDE. I'm in the section 15 workspace in the copy constructor assignment operator project. Now this project is very similar to what we've seen before. I'll scroll up here and you can see we have a base class that has an integer attribute called value. And then we've got a noargs constructor, an overloaded integer constructor, a copy constructor here, and an overloaded copy assignment operator. And these are exactly like we've seen before. And we also have a destructor, of course, down here at the bottom. What we're doing here is when we get noargs, we'll set value to 0. When we get an integer, we'll set value to whatever integer we get. In this case, here's my copy constructor. Again, the compiler provided one would have been great, but I want to make sure that you see how these things are called. So in this case, I'm just copying the other's value to this value. And the same thing with the overloaded copy assignment operator. I'm checking that we don't have self-assignment, and I'm just assigning the right-hand side's value to this value. Okay, great. Now let me close down this derived, so we'll get to the derived in a little bit. So if we run this, here's a real simple main, and I've got a breakpoint right on line 65. The first thing we want to do is we want to create a B object, and we're providing an integer as an initializer. What we expect there is that the overloaded integer constructor fires, and that's exactly what will happen. Then we've got a copy constructor because we're creating a B1 based on a B. And then finally an assignment operator. And this is copy assignment here. This is an L value. Okay, so let's walk through this. And this should be pretty much review from what we've done before. I just want to make sure that you understand the base part before we do the derived part. All right, so I'm right here on line 65. I'm just about to create that object right here, B. So let's step through this, and we expect the base overloaded integer constructor to be called. And that's exactly where we are right here on line 16. We'll set the value to 100, which is what X is right here. And we'll display int base constructor. And that's it. We've just constructed this object B. Let's take a look at it real quick. You can see its value is 100. And that's a base class object. Now we're going to construct B1, which is also a base class object based on B. So we're going to call the copy constructor. And you can see the copy constructor right here on line 19. So let's do that. And I double clicked, but you'll see what I mean. Here we're in base, and we set this value to the other's value. And we're going to display base copy constructor here in a second. So let me execute that, and that's it. So now you can see that B and B1 are indeed copies of one another, and we use the base copy constructor to do that. Finally, we're going to say B equals B1. In this case, B already exists, so this is not a constructor. This is copy assignment. So we expect this method right here on line 24 to be called, because that's my copy assignment operator. So I'll step through this. There it's called. We'll just say base operator equals being called. It's not self-assignment, and I'm simply assigning the right-hand value to this value and returning the object, and I'm done. Okay, so you can see exactly what's happened, exactly what we expected, right? Now we're going to unwind because these objects are going out of scope, so we expect B1 to be destroyed first and then B to be destroyed second. So the first destructor is the one for B1, and we'll execute that. There you can see the output right here. And then the destructor for the B object executes, and our program's done. Okay, so now let me comment these lines out. And what we'll do is we'll uncomment these lines and we'll go through this code in a sec. I'm going to move that breakpoint down to line 69. And let's take a look at our derived class right here. I'll expand it. So here we have a derived class that is derived publicly from base. It adds its own attribute, doubled value. Remember, it gets value from base, but we've added doubled value. And here I've got a noargs constructor, and it invokes the base class's noargs constructor because we want to make sure that this will happen automatically, but I'm just doing it explicitly here. Then we've got the overloaded int constructor for the derived, and what we do here is we call the overloaded base constructor for an int right here. And when that's done, then we take care of initializing our own stuff, which in this case is doubled value, which we simply initialize it to 2 times x. And then we've got our copy constructor right here. It expects a derived. And what we do here is we call our base class's copy constructor and we pass other. Other is a derived. Remember, base expects a base, but since a derived is a base, we can certainly pass other in here. And when we go through the debugger in this case, I'll show you the slicing and how it works. Then we initialize our part and we're done. And then finally, we've got the assignment operator, the copy assignment operator, where we check for self-assignment. And this line is really important here. What I'm doing here is we're calling our base class's overloaded assignment operator and we're passing in the right-hand side. Again, that method in our base class expects a base object here, right? A ref to a base object. What we're doing here is we're passing in a derived. So the same idea, we're going to get slicing there. Then once the base is assigned, I take care of assigning the part of the derived that really this method is only concerned about. And we return this and we're done. Okay, so let's take a look at the main real quick. Here we are, it's very similar to the example with the base. Here we're creating D, which is a derived class object, and we're using the initializer, the integer initializer, so it'll call the overloaded constructor. Then we're copy constructing D1 from D, and then finally we're going to do copy assignment from D1 to D. Okay, so I think I think you get the picture of what's going on. It'll definitely make sense now when we step through it. So let's start the debugger and step through this example. So we're right here on line 69. We're just about to construct that D object. We expect this constructor right here on line 43 to execute. That's the overloaded constructor that expects an integer. So I'll step in, and that's exactly where I'm at. Now I need to construct the base part of me. So I'm going to invoke my base class's overloaded constructor and pass in x to it. So you can see that that's what's happened now. I'm now in my base class's constructor, which is going to take care of initializing that base part of me. So we'll do that. We'll display base constructor. And you can see now that I'm on line 45. So I'm back in my derived constructor. It just initialized the base. It initialized double val. And now it's just going to do a simple display statement. And we're good. So we've just created that D object. And you can see the D object looks like 100 for my base value and 200 for my doubled value. Okay, so now let's look at the copy constructor. That's what's being called here. Remember, we're constructing, let me scroll up just a little bit here. We're constructing D1 based on D. So what we expect to be called is our copy constructor right here on line 47. So let's do that. So I think I double clicked. What really happened was that our derived copy constructor got called, and then it immediately called our base copy constructor, and we passed in other. Now remember, other was or is a derived object here, but now I'm up here in my base class copy constructor, but look at other. You can see what I passed in. Now it's 100, right? But other originally had that doubled value as well, so that got sliced out. And the only piece that we're interested in is the base part of that object. So that's what's happening here. So we'll continue executing this. Now we just copy constructed our base, and when we come back right here on line 48 and 49, we've set doubled value, and now our derived copy constructor is done. So you can see that the derived copy constructor, and you'll see that on the output right here, you see that the derived copy constructor invoked the base copy constructor, and it passed in that derived object to it, which got sliced. Okay, so Last thing left to do is the assignment operator, the copy assignment. So now we're going to say D equals D1 or assign D1 to D, right? So we're here, we expect line 52 to execute right here. That's our copy assignment for a derived. So I'll click this, I'll try to click it once. Good. So now we're on line 53 now. We're simply going to display derived operator equals. We're going to check for self-assignment. And now what I want to do is I want to copy the right-hand side to the left-hand side, but only the base part. So in this case, I want to call my base class as overloaded operator and pass in right-hand side. So now take a look at right-hand side. Right-hand side is a derived, right? So it's got a base and it's got its derived doubled value here. But watch what happens when I call that method right here. You'll see I'll transfer control to it. And this is where I'm at right here on line 25. Look at that object now. Look at right-hand side. Notice that now it's a base now. So it just got sliced, right? That doubled part is not part of a base, so it gets sliced out. So now we just keep executing. We're going to execute the base operator equal, which assigns the right-hand side's value to the left-hand side's value, or this in this case, since it's a member function. And we just assigned the base part. We're now on line 57. We're going to take care of the double value part of us. And we are done. That's it. Pretty straightforward. Now, obviously, these values are going to be the same because we just assigned them, and they both have a base part and a derived part. Now they're going to go out of scope, so we need to unwind and destroy these objects. So the destructors will be called in the reverse order of the constructors, right? So the first destructor that will be called is the one for D1 here, and we'll execute that, and you can see that the derived destructor executes, followed by the base destructor right up here on line 32. There we go, and then the same thing will happen with the next object. And our program is done. Okay, so this gives you some insight into the way that the derived constructors and copy constructors work. You can see it really makes sense. The only thing that might be a little confusing at the beginning is that, for example, our derived copy constructor and operator equal expect a derived, and the base class versions expect a base. Same here. But that's where the slicing comes in. We can certainly pass a derived into here because the derived is a base. Okay, so that covers it. If there are any questions, please let me know. One of the most powerful features of inheritance is that base class member functions are available to the derived class. A derived class can directly invoke base class methods. A derived class can also override or redefine base class methods. This concept will provide us with a large amount of power when we use polymorphic functions in the next section. In order to redefine or override a method, you simply provide a method in the derived class with the same name and signature as a method in the base class. Let's see an example. Here we'll both use and override a base class method. Suppose we have an account class, and it has a deposit method that simply increments a balance by an amount. Now we have a savings account class, and it also needs a deposit method, but its behavior will be slightly different in some way. We can override the account class's deposit method in the savings account class by providing a specialized implementation using the same method signature. Now, when the savings account objects deposit funds, this specialized method will be invoked. But since the accounts deposit method does some of the work that we want to do in the savings account deposit method, we don't have to duplicate code. We can simply call the accounts deposit method from within the savings accounts deposit method. You can see the syntax makes sense. We must prefix the method call with the account class, so the compiler knows that we're calling the deposit method in the account class. It's super important that we don't try to do the actual deposit in the savings account method. Instead, let the account class do what it knows how to do. If the base functionality for deposit ever changes, it won't affect our savings account deposit method, since all it's doing is delegating this to the account class. Let's finish up this video by talking about static binding. By default, C++ does static binding of method calls. All that means is that the compiler determines which methods are called based on what it sees at compile time. Static binding is super efficient, and that's why it's the default in C++. So, if the compiler sees that a B is declared as a base object, and we call b.deposit, then the compiler will call the base class's deposit. The same is true for a derived object. If D is a derived object and d.deposit is called, this results in a call to the derived class's deposit method. While this is very efficient and fine in most cases, there are times when we'd like the binding to take place at runtime. We'll see that in the next section. Let's see a couple of examples next. In the first example here, you can see that b.deposit will call the base class's deposit method because b is a base object. And d.deposit will call the derived class's deposit method since d is a type of derived. But consider the last two lines of code. In this case, we have a pointer, ptr, to a base object. But we create a derived object on the heap and assign it to the pointer. This is perfectly valid since the derived is a base. But now if we call the deposit method through the pointer, the compiler will call the base class's deposit method because it sees that pointer is a pointer to a base class. But perhaps it would make more sense to call the derived deposit method in this example, since the actual object pointed to is a derived object. As I said, we'll learn how to achieve this kind of dynamic binding in the next section, but it's very important to understand that by default, C++ uses static binding. Okay, so I'm in the IDE, I'm in the section 15 workspace in the Redefining Base Class Methods project. And what we've got here is a real simple account class, and we'll derive a savings account class from it, similar to what we did in the slides, and we'll do it from scratch. That way you can see how this works with using and redefining base class methods. So let's take a look at the account class. We've got a friend here that allows us just to put account objects on a stream and display them really easily. And what we're modeling is the balance, right? That's the whole idea of an account. It models a balance, and it's a double in this case. And then we've got some public methods here. We've our noargs constructor. We've got a constructor right here that's overloaded where you supply the balance. And then we've got a deposit and a withdraw method. Now the deposit and withdraw functionality is dead simple, right? Give me an amount, I'll deposit it. Give me an amount, I'll withdraw it. The only thing we're checking is to make sure that there's enough balance so that we can withdraw the funds. Okay, so that's it. Let's take a look at the implementation. Now you'll notice that there are no copy constructors, move constructors, overloaded assignment operators, and so forth. We don't need them. We're modeling a double, and it really doesn't make any sense to include them. The compiler provided ones are perfectly adequate. So let's take a look at the source. And again, you can see real simple stuff here. What I've got is my noargs constructor right here. And when that is invoked, then all I'm doing is I'm calling my regular overloaded constructor right here, and I'm passing in a 0 to it. So I'm delegating to it. And at this point, that constructor just simply sets the balance to balance, right? Simple as that. The deposit method increments the balance by whatever amount was passed in. The withdraw method expects an amount. We want to make sure that there are sufficient funds. If there are, we're just going to subtract the amount from the balance. Otherwise, we'll just display a simple message, insufficient funds. And here's my overloaded insertion operator. Okay, so there you go. Simple stuff. Now, what we'll do is let's take a look at our savings account. Okay, so here's the savings account class header file. We're including account header file. And a savings account is an account. So you can see the inheritance right here, class savings account, public account. We're using is a inheritance here. And a savings account is an account, so it's going to provide a balance just like the account. But what it does add is an interest rate. So the interest rate is used when users deposit funds. So if you deposit $1,000 and we've got a 5% interest rate, the amount that you deposit will be $1,000 plus $50. So we're giving folks really good bonuses here. I wish my bank account did this. So anyway, so that's what we're going to do. Now the withdraw method doesn't specialize. So the idea there is that we can use our parents or our account's withdraw method as is. We don't have to do anything. We don't even have to declare it in here because we'll automatically inherit it. All right, so why don't we start doing this class right here? So let's start writing the code for this class right here. first thing we want to do is we want to declare that friend of ours. Might as well get it out of the way. And it's going to return a std output stream reference, its operator, and the insertion operator. And what does it expect? Well, it expects a std out stream by reference, and I'll just call that OS. This design pattern here you'll see over and over used in C++. And in this case, it expects a savings account object, right? And we'll call it account by reference. So that's the prototype for that. We'll implement that in the C++ file later. Hopefully I don't have any typos. I'll deal with typos after when we compile. That way we don't waste a lot of time now. That's it. So now what do we want to do? Well, we have to add what we add, right? We're adding an interest rate. So we'll use a protected keyword here, and we'll supply our interest rate, which will be a double. And I'll just call it int rate. Okay, that's it. And now what we'll do is we'll provide some public methods. In this case, our constructors. So it'll be a savings account constructor. That'll be a noargs constructor. We'll also supply a savings account constructor. In this case, that will expect the balance, which will be handled by the account part of me, and the interest rate, which will be handled by me being the savings account class. And we also have to handle the deposit method because we're redefining it, overriding it. So in this case, we want the same function prototype as we had in our parent. So it's deposit, and I believe it was double amount. That's it. Notice withdraw is inherited. Okay, and the functionality that we're using to withdraw funds in the account class is all I need in the savings account class. All right, so now let's implement this. There's only a few methods to implement, so it should be pretty quick and pretty straightforward. Here you go. I'm including my savings account header file, and let's do the noargs constructor. Actually, let's do the second constructor first. The savings account, the overloaded constructor, and it's this guy right here, and it expects a double for balance and another double for the interest rate. Let me fix that typo here. So those are the two parameters in this particular constructor. Now, what do we want to do here? Well, we want to initialize the account part of us, right? So we want to invoke our account part constructor, right? Our parents constructor, and that expects just the balance. That's all it knows about. It doesn't know anything about the interest rate. And then once that's initialized, I can come back and take care of the interest rate and initialize that. There is no body to this constructor. You could just leave it like that. If you want to type something like, cout constructor called, that's fine. But we really don't need to do anything else here. Okay, so now, how about the noargs constructor? Well, let's do that one. That one's pretty easy to do, right? So here's my noargs constructor. It expects nothing. Now, what do we want to do here? Well, the simplest thing to do is just to delegate to my overloaded constructor, right? So what I want to do here is delegate to my savings account overloaded constructor up here. And what I want to pass into it is 0.0 for the balance and 0.0 for the interest rate. And that's it. That'll take care of that. So my two constructors are done. We don't have any destructors or copy constructors or anything like that. So let's worry about the deposit method, right? So let's say void, and it's savings account. It's my deposit method, and it expects a double, which is the amount to deposit. What we want to do here is we want to increment that amount by that interest rate, as I said. So what we want to do is we want to figure out how much do we need to deposit. So let's say amount. That's that same amount right here. We could use another variable name if we want, but this works just fine. A local variable, amount equals amount plus, and we'll say amount times the interest rate divided by 100. That'll give us the percentage, and that should do it. We could have said amount plus equals as well to be a little clearer. Now we know how much we need to deposit. So rather than do it ourselves, let's just let the account parent part of us do it. So we'll say account. It's got a deposit method in there, and we'll pass in the amount that we want it to deposit for us. That's it. And then finally, we'll implement the friend overloaded operator. So this returns a ref to an O stream, and we're overloading operator, our insertion operator. Again, std stream by reference, and we'll call it OS. And we've got a const savings account ref. Okay. And all we're doing here is we're saying, we're putting onto that output stream, we'll say something like savings account balance. And we'll put the account's balance on here. Followed by the interest rate and the interest rate for the account. And we know it's got it because it is a savings account right here. That should do it, and we want to return that OStream. All right, so let's compile this and see if we've got any typos. We probably do. And there's one right here. Okay, cool. So we have a run. Let me show you the main real quick. And you'll notice one thing right away. It wasn't a lot of work to do this, right? That's the whole point of reusing. All I had to do was create these constructors, right? Override that deposit method. The rest is just came right in. The withdraw method I didn't have to touch because I'm inheriting it from my parent. So let's take a look at the main real quick. And I just wrote a couple simple test cases here where I'm creating an account A1 with $1,000 in it, and I'm displaying it. And I'm depositing $500 into it. I'm withdrawing $1,000, and then I'm withdrawing $5,000, and I'm going to get insufficient funds. So let's build and run that. And you can see here, we've got 1,000, 1,500, 500 insufficient funds, and we still have 500. Okay, and then we've got some test cases down here that work with these actual savings accounts that we just created. So let's run those. And you can see here now that I've got a savings account with a balance of 1,000 and an interest rate of 5. I've got, after the deposit, notice that 1,000 was deposited, but 1,050 was deposited because that was our specialized deposit method. So now we've got a balance of 2,050, same interest rate. I'm going to withdraw 2,000, which leaves us with a $50 balance right here. Then if I try to withdraw 1,000, obviously I've got insufficient funds, and then I display it again, and we still have 50. Okay, so there you go. That's an example of reusing an account class, and we're reusing the withdraw method 100%, right? And if you look again at the deposit method, we really are reusing it. We're actually calling it right here. And all we're doing is tweaking the amount that we want deposited and then just sending it right up. Now, one thing I should mention, we overloaded the insertion operator here to work with the savings account simply to display the interest rate, right? If you send in a savings account object to this guy right here in the account class, remember a savings account is an account. What will happen here is the object will get sliced and it will only print out the account's balance, not the interest rate, because the compiler is going to slice that part out. So the only reason that we're implementing this guy right here on line 18 in the savings account CPP is so that we can see the interest rate. So what we'll do in the next video is I'll give you the beginnings of an account class hierarchy. And in the challenge, what you'll do is add some more accounts to this that have, more specialized behavior so you can get some experience with inheritance. And remember, all of this is using static binding, which is real important. In this video, we'll see a simple example of multiple inheritance in C++. Multiple inheritance occurs when a derived class inherits from two or more base classes at the same time. The base classes may belong to unrelated class hierarchies. The class diagram on the right shows an example of multiple inheritance. In this case, the class department chair is derived from both faculty and administrator classes. So if we use public inheritance, then a department chair is a faculty member and a department chair is also an administrator. The C++ syntax for multiple inheritance is simple. We declare our derived class and then provide a comma-separated list of the base classes that it's derived from. In this case, department chair is our derived class and its base classes are faculty and administrator. We're only showing public inheritance here, but we could also use the other types of C++ inheritance. Multiple inheritance is beyond the scope of this course, and it can be very, very complex in practice. There are some compelling use cases for multiple inheritance. However, in many cases, we can refactor our design so that the multiple inheritance can be avoided, and many times we end up with a better design. This isn't because there's anything wrong with multiple inheritance. The problem with multiple inheritance is that because it can be so complex, many developers don't fully understand it, and therefore may misuse it. More often, you see multiple inheritance in class libraries and frameworks that you might be using. Hello everyone, I'm in the IDE in the Section 15 workspace, and I'm in the Challenge project. And before I go over what the challenge is for this section, I'd like to go over the account class that has been modified slightly. And this is the account class hierarchy that we're going to use for the challenge. So I'd like to go through it in detail so that you understand exactly what's going on. It's very, very similar to the account class that we've been using all along, but I've made a couple of changes to it. So why don't we start here at the account class. You can see I've got my account header file and my account implementation file. But let's talk about this account class. As you can see, there's my class account, and I've got my overloaded insertion operator, which allows me to put accounts on a stream really, really easily. Then I've declared these two const expressions, and think of these as constants that are available only to the class. They're within the class scope. Sure, we could have defined these outside of class scope, but then what we do is we pollute the global namespace, and we really don't want to do that. And the reason we're doing that is because we're providing default parameter values in the constructor here. So you can see that we've got default name here as well as default balance here. So by using these, I can do it like this, and I can just change them in one place. The other option is just to do the constructor like this, just like we've done before, where I supply the default parameter unnamed account and the balance is 0. Okay, so again, you could do it either way. I kind of like doing it this way because it gives me all my constants in one place. They are within class scope, and you can decide whether you want to make them private or protected or public, and you've really got a lot of flexibility. So there's my constructor, and obviously we've got an account. In this case, I added the name, right? The name is a std string, a C++ string. So in this case, what an account is, it's got a name and it's got a balance. So here's my constructor. It expects a name and a balance. If we don't get a name, we get a named account. If we don't get a balance, we get 0 for the balance. And at this point, we've got our deposit withdraw, and I've just put in a get balance method here, which could be handy to use. I don't think I'm using it in the code, but you may want to use it. So I've got a deposit method and a withdraw method. Real basic functionality here, right? Simply add whatever is given to you to the balance and withdraw whatever is given to you the balance, assuming that we don't run into a negative balance when it's over. So just like we've seen before. Now, let's look at the implementation for this. So we'll look at account CPP. So here's account CPP, and it's going to be, again, very, very familiar implementation, I think. So here you've got your account constructor. Notice that it expects these two parameters, and those have defaults associated with them. So in this case, this constructor fires, and I'm just setting my name and my balance to whatever was passed in. Real simple constructor. Here's my deposit method. It's expecting an amount. You can see the amount right here. If the amount is less than 0, I'm returning false. This is one of the little changes that I made to these methods. Notice that deposit and withdraw both return true false values, right? A Boolean. So this will return true if the deposit was successful, false otherwise. Same here. This will return true if the withdrawal was successful, false otherwise. This is a pretty rudimentary way of doing error checking because you're just returning true false. There could be a lot of different reasons for failure, and we'll talk about that when we talk about exceptions and exception handling. But for now, this will serve us just fine. So here's my deposit method. Given an amount, if the amount is less than 0, I'm going to return false because that really doesn't make sense. I don't want to deposit negative amounts, which would be kind of like withdrawals. If the amount is not less than 0, then I'm simply incrementing the balance by the amount and returning true, successful. Here's my withdrawal, same idea. I'm getting an amount to withdraw. I'm checking to see if I subtract that from the balance, if I still have a balance, in which case, if I do the withdrawal and I return true, it was successful. Otherwise, I return false right here. All right, here's my get balance, which simply returns the balance. Notice that's a const method. And then the very last function down here is my overloaded insertion operator, which is a friend of this class. it expects a stream, and it expects an account. And all it displays is the account, followed by the account name. Notice that I have access to these guys because I'm a friend. So all it's displaying is the account name and the account balance. So hopefully that makes sense. You can walk through it and study it a little bit before you start the challenge. And like I said, I'll explain the challenge in the next video. So now let's take a look at our savings account. We've got two classes in this hierarchy. We've got an account and we've got a savings account. So here's my savings account. And notice that a savings account is a type of account. So that's kind of a clue as to what we're going to do, right? Right here, public inheritance. So it's an account, but what it does is it adds an interest rate. And you can see the interest rate right here. It's a protected data member. And the withdrawal is the same as a regular account. So you can see that the withdrawal isn't here, right? There's no need to override withdraw because the account's withdrawal works just fine. It's all we want to do. We have no specialization for that. So I commented right here, inherits the account withdraw method. The deposit does specialize. It's a little bit different. So the amount supplied to the deposit will be incremented by the amount, I should say here, sorry about that, I will fix that, by the amount times the interest rate divided by 100, right? So if the interest rate is 5, then that would be 0.05, which is 5%, times the amount, and we're going to put that right back in. Okay, that's pretty much it here. The rest is pretty self-explanatory. I think I've got three constant expressions here. The first one is unnamed savings account, which is my default name. Notice that it's right here. If it's not supplied, that's it. My default balance and my default interest rate are over here. And right here, again, you don't have to do this here. You can simply put them in right in here, 0000 and unnamed savings account right here. This has got to be cpplusplusforbeginners to do this kind of thing. And let's see what else. What else do we have? We have the constructor, which expects all three of those guys, as I said. And I've got my deposit, which I have to override to support this kind of deposit behavior. Okay, so one of the things that hopefully you'll notice, and this is one of the ideas with inheritance, is that as you derive classes, you really should have to do a lot less than the previous class did, right? Which makes sense, because after all, what we're doing is we're specializing, we're not redoing. So let's take a look at the implementation for the savings account. So you see it's not a lot of code here. And that's the whole idea. I mean, if you find yourself writing a lot of code in the specialization classes that you're deriving, then either it's a really complex derivation or something's not quite right. So let's take a look at the constructor. Here you can see the constructor. It expects a name, a balance, and an interest rate. And remember, a savings account is an account. So I need to take care of that account part of me. So right here, I'm invoking my base class's constructor. And I'm passing in name and balance. Remember, that's what an account has, a name and a balance. So I'm going to let the account class take care of that. It knows about that. Those are not my instance variables here. I'm only putting in the int rate. Once that's done, I'll come back and I will initialize the interest rate to whatever is passed in right over here. And that'll do it. Notice that none of these constructors have bodies to them. Well, I shouldn't say that. They do have bodies to them. You can see the body right here. There's no code in the body. You can simply put cout statements in there if you want to see them execute. Also, there's no destructors, there's no copy constructors, there's no overloaded assignment operators because we don't need any of those. The balance is a double, the interest rate is a double, and the name is a stood string. They know how to take care of themselves, so we don't have to worry about that. We don't have any raw pointers here. All right, so now let's take a look at the deposit method. Here's the deposit method. You can see we expect an amount to deposit, and we're going to increment that amount by the amount itself times the interest rate divided by 100. That's what the business logic says. Once we know the amount that we want to deposit, it's right here, then we really don't want to do that ourselves. We want to ask our account class to do it for us. So we're going to call the deposit method in the account class, which is right here. And you need to put this piece right in front here. Otherwise, the compiler will call this method right here, and you're going to end up with recursion forever. Okay, so be real careful about that. You want to be sure that you call the account class's deposit method. And we pass in the amount. That's it. And notice something else here. This returns a Boolean. Right? Well, I'm returning whatever my base class's deposit method returned to me. And so if it failed over there, I'm just returning fail here. If it worked over there, I'm returning true here. Okay, so again, we're leveraging on the fact that all of these deposit and withdraw methods will return Booleans. Notice there is no withdraw method because we're inheriting our parents. It's public in the account, so it's public in me, so I've got access to it. And here is the overloaded insertion operator for a savings account. I mentioned slicing before. If we don't provide this and we pass a savings account into the account overloaded insertion operator, it'll slice and this piece here won't print. It'll still print name and balance because all accounts have names and balances, but this piece here, this is what my savings account brings. So this will just display savings account, the account name, the account balance, and whatever the interest rate is in percent there. Okay, perfect. So now I wrote a little bit more code just to make our lives a little easier. And it's right in these two files right here. I created two files. One is called account_util.header file and an account_util implementation file. And these are utility functions that we're going to use with these classes. They're not part of the class. They're simply utility functions. Let's take a look. Let's take a look at the header file. Okay, so I've got some simple utility helper functions for the account class and the savings account class. You'll see a lot of duplicated code here. And a lot of this duplicated code is going to go away in the next section when we talk about polymorphic functions. But here we're doing everything statically, so we've got to do it this way. So take a look at this. I've got a display function. Now remember, these are regular functions. These are not class member functions. These are just plain old global C++ functions. It's called display, and it expects a vector of accounts, right? A bunch of accounts by ref. Then I've got, and all that does is just loops through them and displays each one of them. And I'll show you the code for that in a moment. These are just the prototypes that we're going to use in main. Here I've got a deposit, and all that's going to do is give me a list, or a vector in this case, of account objects. And I'm going to deposit this amount into all of them. So this is going to really be nice for us to test our code. Same thing here with withdraw. Withdraw $1,000 from all of these accounts that I send you. Okay. So those are the ones for the account class. These are the ones for the savings account class. You can see that I've got savings accounts here and accounts here. Okay. Also notice that the names are the same: display, display, deposit, deposit, withdraw, withdraw, right? So we're overloading here. We're using what we learned a long time ago when we talked about functions. We're overloading the functions. The compiler can tell them apart because of this first argument right here. This is a vector of savings accounts. This is a vector of accounts. Okay, so let's take a look at some of the code for this. Like I said, it's a bit long and repetitive, but hopefully you'll get the idea. Here's the display. So if you send me a vector of account objects by reference, and again, this is const because I don't want to modify it, I'm just displaying it, then I'm just going to print out this line accounts, and then I'm going to loop and say, use a range-based for loop, and for every account in that vector, I'm just printing it out just like that. That's using the overloaded insertion operator. And that'll display them real nicely. Here's the deposit. In this case, I don't want this to be const as we did over there, up top here, because I do want to modify it. And it's as simple as loop through the accounts. For each account, deposit that amount into it. If it came back true, that means the deposit was successful, and I just display deposited however much amount to whatever account. If it fails for whatever reason, I'm just saying failed deposit to this account. And last method here is the withdraw. Same idea. I want to withdraw this amount from all of the objects in that vector. So all I'm going to do is loop through. I'm going to call the withdraw method on each account, and if it comes back true, then the withdrawal was successful, and I'll display I withdrew $1,000 from each account. If it fails, I'll say that as well. Okay, so you can see it's pretty standard. It's nothing we haven't done before. The only thing that's different maybe is the organization that we're doing. So I've got those three functions for account, and then I've basically got the same three functions for savings account. You can see savings accounts right there. So it's really pretty much the same. The only difference is that this deposit and this withdrawal right here will use the specialized versions of deposit and withdraw from the savings account. So that's it. Let's look at the main. here's my main, and it's not that long, but we're a lot going on here though. Notice that I'm including account util.h, right? Because I need those utility functions. And let me scroll up just a little bit and you can see what's happening here with account. I'm creating a vector. We've used the vector before. We'll learn more about the vector and the list and other things when we talk about the C++ standard template library, but we've used vector, so we should be pretty familiar with it. So I'm creating a vector here called accounts, a vector of account objects, and I'm just simply creating an empty account, right? That's going to be an unnamed account with a 0 balance. I'm creating another account called Larry with 0, Mo with 2,000, and Curly with 5,000. And I'm pushing those accounts at the back of that vector. So all we're doing there is creating a vector and creating 4 account objects and putting them in the vector. Once we're done with that, we're going to use those utility functions. So you can see this is where it comes in real handy. Display the accounts, deposit 1,000 into each one of those accounts, and withdraw 2,000 from each one of those accounts. So that's going to deal with accounts, and then we're going to do the exact same thing with savings accounts. So in this case, I've got a vector of savings account objects, and I'll call it save accounts. And the same idea, I'm going to create a savings account object that's empty. I'm going to create a savings account object that's Superman, another one for a Batman with 2,000, and finally Wonder Woman with 5,000 and 5% interest. Okay, these get the default values for both the balance and the interest, these guys right here. And this guy gets all 3 default values, right? It's going to be an unnamed savings account with no balance and no interest rate. And then we'll do the same thing with this, saving, display, deposit, and withdraw. You can see that we've got the same code here and here, but different functions will be called because of the overloading. So let's run this and you'll see the output. And hopefully you'll see why I did use those utility functions, because it's just going to make our lives much, much easier and make our main very clear. So let me run this. I'll build and run. And here you can see the output. I'll scroll to the top, and right here, I'm displaying the accounts. And this is what you're seeing here on the right side. Account unnamed account, that's from this guy right here. Then we see Larry with no balance. Then we see Mo with 2,000. And then we see Curly with 5,000. Then I call the deposit function. And what that's going to do is it's going to loop through all these 4 accounts and deposit $1,000 into each one. So you can see here I'm deposited, all of them returned successful. So I deposited 1,000 to the unnamed account and its balance is now 1,000. I deposited 1,000 to Larry, he's 1,000. Mo is now 3,000 and Curly is 6,000. And then what I'm going to do is I'm going to withdraw $2,000 from each one of those accounts as I loop through them. And I'll scroll this up just a little bit. And here you can see that right now I'm withdrawing $2,000 from the unnamed account, but the unnamed account only had a $1,000 balance, so it failed. And the balance is still 1,000. I tried to withdraw $2,000 from Larry. Well, Larry only has 1,000, so that failed as well. And I tried to withdraw 2,000 from Mo and Curly. They have enough balance, so Mo is now 1,000 and Curly is now 4,000. And now the savings, let me scroll up just a little bit so you can see it better. Here now we're doing it with same thing but with savings accounts. So I'm creating 4 savings account objects in this case. The empty one, Superman with 0, Batman with 2,000 and 0, and Wonder Woman with 5,000 and 5% interest. And then I'm displaying them. You can see them being displayed here. I'm displaying the unnamed savings account 0, Superman 0, Batman 2,000 0, and then Wonder Woman 5,000 and 5% interest. Then I'm calling the deposit method for each one of those guys again in the loop using the utility function. And what's happening is I'm going to deposit $1,000 into each one of those accounts. And notice that I'm depositing 1,000 into unnamed, right? So now it's got 1,000 balance. I'm depositing 1,000 into Superman, so it has 1,000. I'm depositing 1,000 into Batman, so it was 2,000 up here. Now it's 3,000. Notice it had a 0% interest rate, so we didn't get that extra little bonus that we want. But in this case, I'm depositing 1,000 to Wonder Woman, and Wonder Woman has got a 5% interest rate, so you can see that indeed took that into account. So it's really using that specialized deposit method. And then what we'll do is we'll withdraw some $2,000 from each one of those accounts. In this case, it's going to fail with the unnamed account because the unnamed account only has a balance of 1,000. It's going to fail again with the Superman account because it also only has a balance of 1,000. But with Batman and Wonder Woman, it'll be just fine because Batman had 3,000 and Wonder Woman had 6050. So you can see that now we've got 1,000 in Batman and 4050 in Wonder Woman. Hopefully that makes sense and that gives you an idea of these classes. Study these, look at them, play with them, run through the debugger, throw some statements in there. And what we'll do, I think you know what we're going to do. We're going to add a few new classes to this hierarchy, and I'll talk about that in the next video when I talk about the actual challenge. Hello everyone, welcome to the Section 15 challenge. That's the inheritance challenge. This is a very challenging challenge. You're no longer beginning C++ programmers, that's for sure. This challenge involves extending a class hierarchy by adding a few more classes, and I'll talk about them in just a second. And it also involves understanding someone else's code, which is, something that happens in real life, or actually more often than not, you're modifying someone else's code. We don't write our own code from scratch very often out there. So this is part of the challenge. Before you attempt this challenge, watch the video previous to this video, where I go over the classes that are in this project. I go over the account class and the savings account classes in detail. If you haven't done that, I encourage you to do so now, and then come back and give the challenge a shot. So let me go over the challenge and tell you what's involved. First of all, I'm in the Section 15 workspace in the challenge project. This is your starting point. This has an account class and a savings account class that's derived from the account class. Everything's working, the tests are there, the utility functions are there, and so forth. So you're provided with these two classes, as I mentioned here. You're provided with the account class and the savings account class. The savings account class is an account, so we're using public inheritance. So in this case, we have an account that has a name and a balance, and then the savings account is an account, and it adds an interest rate. And as I mentioned, watch the previous video and you'll get a good understanding of exactly how the deposit method works and the withdrawal methods work and so forth. Also, I created some account helper functions in the account util header and CPP files that make it easy to display, deposit to, and withdraw funds from a vector of accounts and savings accounts. And that's what I'm using in the main driver, just to make it a little easier. Otherwise, your main gets really, really convoluted and you're always checking for, was this a successful deposit or was this a successful withdrawal? And the code just gets really nasty to follow. So what's this challenge about? Let me just scroll up just a little bit. And so this challenge is we're going to add two classes to this hierarchy. The first class you see right here, it's a checking account class. And we want to add that to the inheritance hierarchy. So we want this to be a derived class of either account or savings account, you decide. A checking account has a name and a balance, and it has a fee of $1.50 per withdrawal transaction. So every time we do a withdrawal, we're going to assess a $1.50 flat fee. The trust account is the other account I want you to add to the hierarchy. And again, you decide whether it belongs under account or under savings account or under checking account. And for that matter, is the checking account under a trust account? So you figure out what the hierarchy is. It's pretty straightforward, I think, once you sit down and think about it. So a trust account has a name, a balance, and an interest rate. But the trust account deposit works just like the savings account deposit, except when we've got deposits that are $5,000 or more, we'll get a $50 bonus by the bank. The trust account withdrawal is also different. It only allows 3 withdrawals per year, and each of these must be less than 20% of the account balance. You don't have to keep track of calendar time, as I mentioned here, so just make it fail on the 4th attempt. To withdrawal, sorry, I'll change that. That should be withdrawal. I'll fix that in the spec. Okay, so the 4th withdrawal will fail. So what are some hints? Well, reuse existing functionality. That's the whole idea behind inheritance, right? It's all about reusability. So don't reinvent the wheel, don't duplicate code. Reuse as much as you can. Think about what the base class will be for each of these new classes that we're going to add. Also, I've created those helper functions in the account util file. You may want to add the trust account and checking account versions to them. I would recommend that you do that. That just makes it much easier to use these things in the main, but you don't have to. You can just test these in the main. It's up to you. As always, have fun. You're no longer beginner C++ programmers, that's for sure. Once we delve into the world of inheritance, this is no longer beginning C++. This is more intermediate C++. So congratulations that you made it this far in the course. And the last thing is, if you want more practice with operator overloading, you can overload the plus equal and the minus equal so that they do deposit and withdrawal, which can be handy. Okay, so that's it. I'll be back in the next video with my solution, but give this a shot. And as I said, don't get frustrated with this. This is not an easy challenge. There's a lot going on here. And just take it one step at a time, do one class at a time, implement one method at a time, test as you go, and before you know it, you've got a great solution. All right, so good luck, and I'll see you in the next video. Welcome back. I hope you enjoyed the Section 15 challenge. I'm going to give you my solution here, and we'll walk through it. As always, there's a lot of different ways to do this, so if your solution is different from mine, it's probably just fine. So I'm in the Section 15 workspace in the Challenge Solution project. So I didn't change the account or the savings account classes at all. So why don't we start with the checking account class? This is one of the new classes that we added. So let me open up the checking account header file, and let's go through this real quickly. Now, in this case, the checking account doesn't add any new attributes, right? So a checking account is an account. I chose to derive this from account because the checking account has the name and it's got a balance. The only difference here is that when we withdraw, we're doing a $1.50 flat fee check fee. Okay? So other than that, it's really, really very similar. We've got our constant expressions here, which are just our compile time constants. Here we've got our constructor that expects a name, and if it's not supplied, we'll use our default here, a balance, and that's it, right? The per check fee is not a per object thing. This is a class thing. So this is why it's a static constant expression. If it was on a per account basis, then obviously you'd want that to be an attribute and you'd want to pass it into a constructor. So we've got that. We've got our withdraw method because we need to override the behavior for withdraw to deal with the per check fee. The deposit method is fine. We don't need to change that at all because the way we do deposits is the same way that an account does a deposit. Hopefully, one of the things that you noticed when you derive these classes from existing classes is the amount of code you have to write is really minimal in many cases, right? Because all you're doing is specializing. The other thing we did here was we created that overloaded insertion operator that works with a checking account. That just makes it really easy to display those. Okay, so that's it. Let's take a look at the implementation. And as you can see, there's really very little code here. First of all, let's look at the constructor. So there's my checking account constructor. It expects the name and the balance. And I need to initialize the account part of me, right? Because I'm derived from account. So here I'm invoking my base class's constructor, and it's the one that takes care of name and balance. So I'm just passing it over. And when this comes back, we're initialized, right? At that point, that's all. That's all we need for a constructor here. Now, what about the withdraw method? Well, here we're definitely overriding the withdraw method. And so here's the withdraw method for the new class, my checking account class. It still expects an amount to withdraw. And all we're doing is we're saying, okay, whatever that amount is, I'm just adding the per check fee to it, which is $1.50 in this case. So whatever I want to withdraw, I'm just adding the $1.50. And then I'm letting the account class do the withdrawal, just like we've done before. And again, I'm returning what it returns. So if it fails, I'll return false. If it succeeds, I'll return true. And then the last thing we'll do is our output operator here, our insertion operator. This time it expects a checking account. And actually, we could have used a regular account here, right? Because we're not really adding anything in this class. So even if it got sliced, that's okay because we're not adding anything at all. So that's it. That's a pretty simple implementation of that checking account. Now let's take a look at the trust account. So here we have our trust account, and you can see that the trust account is derived publicly from a savings account. And that's because a trust account has a name, a balance, and an interest rate. So a lot of the savings account behavior will be perfect for that. I'm overloading the insertion operator here for a trust account as usual. And now this code looks a little lengthier, and the reason for that is all these constants here. They're handy, right? Here's our default balance, here's our default interest rate. You probably could make that 2 or 3% or something just to get some more interesting results, but I'll leave it at 0. There's the bonus amount for a deposit that's over $5,000. There's the threshold that's $5,000. the maximum withdrawals is 3, and the most we can withdraw is 20% of the account's value. So all that information is right in here in these constants. And the only thing that the trust account really adds is, besides the business logic, of course, is this attribute right here, the number of withdrawals. So we'll set that to 0 when we create a trust account object. And then every time we do a withdrawal that's successful, we'll bump it up by 1. And then when we do a withdrawal and it's greater than 3, we'll just fail right there. Pretty simple. Okay, so here's my constructor. It expects, as usual, a name, a balance, and an interest rate. You can see that right there. And it's got these defaults right up here that it defaults to. Here's my deposit, which I obviously need to override because I get a $50 bonus whenever I deposit $5,000 or more. And here's my withdrawal, which again I need to override because our business logic says I'm only allowed maximum of 3 withdrawals per year. And each one is up to a maximum of 20% of the account's value or balance. Okay, so that's it. Let's take a look at the implementation file now. And here's the implementation file for the trust account. You can see our constructor is up here. We're receiving the name, the balance, and the interest rate. And all of those guys are really in my savings account part, right? So I'm invoking my base class constructor right here, and I'm passing in name, balance, and interest rate. Let it take care of initializing itself. When I come back, I do need to take care of my attribute, which is number of withdrawals. So this is my responsibility, and I'm setting that to 0 right here. Okay, so now let's take a look at the deposit. So here's the trust account deposit method. Again, it expects an amount. And all I'm looking for is that bonus threshold, which is $5,000. So if the amount deposited is greater than or equal to that bonus threshold, which in this case is $5,000, then we're just incrementing the amount to deposit by the bonus amount, which is the $50. Simple as that. I invoke my base class's deposit method because the savings account knows how to deal with the interest rate on the deposit, and I'm returning right here what it returns to me. And then the last thing we'll do is our withdraw method. Again, the withdraw method is important because it's got some business logic here. So I want to check, and again, here's the amount that I want to withdraw. So if the number of withdrawals is greater than or equal to the max withdrawals, which was that constant, which was 3, or the amount to withdraw is greater than the balance times the threshold, right? So that's the 20% right here. If either one of those guys is true, we don't do the withdrawal, we return false. Otherwise, we increment the number of withdrawals and we call our savings account withdraw method and pass in the account and pass in the amount to withdraw. So that's it. You can see that we really aren't writing a lot of new code. We're specializing, we're tweaking, we're refining, if you will, our behavior based on our business logic. And then the last thing is this overloaded insertion operator for a trust account. In this case, I'm also displaying the number of withdrawals just so that we have that information. Okay, so that's the trust account. So we've got our 2 new accounts in the hierarchy now. So the next thing I want to show you is that account util file and the functions that I modified in there. So let's look at the changes I made to the account util files, and you can see that right here I've added the function prototypes for the checking account class and the trust account class. You can see that all this code is really similar, and you're going to love what's going to happen in the next section. We're going to be able to get rid of all of this and just create one version that works for all of the accounts once we use polymorphic functions. But for now, let's just do it this way so that we really understand what's going on. Again, remember we're doing static binding right now, so the compiler is binding the method calls to the actual types of the objects that it sees at compile time. So there are the function prototypes for these guys. It's very similar to what we did before. And the implementation file right here, same idea. I'll just scroll down just a little bit, and you can see here are the helper functions for the checking account class right here on line 64. And if we scroll down a little bit further, we've got the helper functions for the trust account class. And as I said, they're all exactly the same except what's inside that vector. Okay, so now let's look at the main finally. Here's the main, and the beginning is exactly the same as it was before, right? I mean, you remember we had the accounts test right here, so we put in some account objects into a vector of accounts, and then we called display, deposit, and withdraw for those accounts. We did that both for a regular account and a savings account here. And now we're just going to do the same thing again for a checking account. So you can see here I'm creating a vector of checking account objects, right? That's my template argument right here, checking account, and it's check accounts. And I'm creating an empty checking account, one for Kirk, one for Spock, and one for Bones, let's say. I don't want to give Spock 2 accounts. And that's it. Then we're going to call display for check accounts, deposit 1,000 into each one of those accounts, and withdraw from those accounts 2,000. And then finally, we're going to do the trust account. And the trust account, same idea. I'm going to have a vector of trust account objects, and I'm going to create 4 of them again. I'm going to construct this one with no initialization, just like I've done before. And then we'll create Athos, Porthos, and Aramis, the 3 musketeers, and we'll create some accounts for them. We'll display them, deposit into them, and withdraw from them, just like we did before. And then the last thing I'm doing is I'm simply calling withdraw 5 times. So I'm looping 5 times, and I'm calling withdraw on those trust accounts. So I expect those to fail, right? Because I'm only allowed to withdraw 3 times maximum, and I can only withdraw 20% of the balance. So I should see a lot of failures here. So let's run this, and there's going to be a lot of output to go through. And you can see we have a clean compile, no errors, no warnings. And I'll scroll up here because there's a lot of output to go through. And this is what we had earlier, right? When we created just the regular accounts here, we created 4 of them, Larry, Moe, Curly, and an unnamed account right up top. We're going to display them. That's what you're seeing right here. Then we're going to deposit 1,000 into them, and that's this piece you see right here, depositing 2 accounts. And then we're withdrawing 2,000 from them. That's the piece you see right here. The first 2 fail because there's insufficient funds. So that's pretty straightforward. That's exactly what the default code was in the challenge. So is this. Here's my savings accounts. And let me just scroll up to so we can see that right here. So we're creating those 4 savings accounts for Superman, Batman, and Wonder Woman. There they are. When we display them, we're depositing $1,000 into them here, and then we're withdrawing 2,000. So of course the first 2 will fail because there's insufficient funds, just like before. Now here's the checking. The checking is a little different now because our withdraw methods add a $1.50 service fee or a per check fee, right? So here we've got a checking account for an unnamed checking account. We've got Kirk, Spock, and Bones, and you can see them right here. Right here is our display, right? There's an unnamed checking account with 0 balance. There's Kirk, 0 balance, Spock and Bones, 2,000, 5,000 respectively. I'm depositing $1,000 into each account. And then I'm going to withdraw 2,000 from each account. Exactly the same as we've done before. So the first 2 are going to fail. And you can see that the numbers now are a little different, right? Because we are subtracting the $1.50 per check fee here. And these 2 don't because the withdrawal failed. But in this case, we did withdraw, so we're assessing the $1.50 fee. So you can see that indeed the specialized withdraw method is being called. Now, finally, we've got the trust accounts. So there's our code for the trust accounts, and I'll scroll that up right about there. So here I'm creating Athos, Porthos, and Aramis and an unnamed trust account right here at the beginning. And we're creating some different balances as well as interest rates. And then we're just displaying the accounts, and that's what you're seeing here, right? The unnamed trust account with 0 balance, 0% interest rate. It has no withdrawals yet. Here's Athos, Porthos, and Aramis, and you can see their information right here. Notice how all of them have 0 withdrawals because we set that in our constructor. Now we're going to call deposit on each one of them and deposit $1,000. You can see that that's successful all the way through. You can also see that we've got the bonus coming in here. So finally, we withdraw $3,000 from each account. The first 2 will fail. The first one because we don't have sufficient funds. The second one because we are exceeding our 20% limit. But the third and fourth one are no problem at all. You notice the withdrawals here are now 1, whereas the withdrawals on the failed ones are 0. And then what I'm doing is I'm just calling that same withdraw function 5 times. So there's once right here. You can see the number of withdrawals increasing and increasing. And finally, everything fails as we expect right here because we've exceeded the 3 withdrawals. Okay, so that's it. I'm sure your solution is different from mine, and that's okay. Take a look at my solution. Maybe yours is better. If it's better, post it. If you find a bug in mine, let me know, please, and I'll be glad to fix it. So I hope you enjoyed this challenge. I hope you understand a lot about inheritance. In the next section, we're going to crank up the level in inheritance, and we're going to talk about polymorphic functions with inheritance, and that's going to make all of this even easier. So stay tuned for that.